to go top down, but you do need more space. Back in the day, decades ago, space was really expensive. And so you know what? It might have been better to not use merge sort, use bubble sort or selection sort even, or some other algorithm altogether. Nowadays, space is relatively cheap, and so these are more acceptable trade-offs. But it totally depends on the application. The very last thing we thought we'd do is show you an actual comparison of some of these sorting algorithms. It's about 60 seconds long, and it will compare for you selection sort, bubble sort, and merge sort in parallel, simultaneously, with some fun sorting music, showing you ultimately what it really means to be an O of n squared, or better yet, big O of n log n. Selection on the top, bubble on the bottom, merge in the middle. That's it for CS50. We'll see you next time. This is CS50, and this is week 4. And if you think back a few weeks ago already, in week 0, we started talking about like what images are. And we talked about representation of images as this grid of pixels, and each pixel has like some pattern of bits that defines its color. Well, it turns out today we'll take a deeper look underneath the hood at how things like images and so much more is actually implemented using just these zeros and ones, and how now, as a programmer, you can actually harness that, for better or for worse, to better understand and better manipulate what's going on inside of a computer's memory using a language like C. In fact, even this bowl of stress balls that we keep happening is just a photograph, of course. But if you think back to week 0, if you sort of enhance this image, like they do in the movies, it actually doesn't work out the way you would think from Hollywood. As I continue to zoom in and zoom in and zoom in on a screen like this, you'll see that, yes, it gets bigger. But if it gets too big, what do you start to notice? The so-called pixelation. And indeed, you can see the individual dots. So Next time you watch some show or movie on TV that has this sort of notion of enhancing, there's actually a finite limit there. You can only enhance so far as there's actually information there. But once you zoom into a certain level like this, that's all that's there. You're not going to see the glint of the suspect in some crime drama in their eye just because you've enhanced the image. There's only a finite amount of information actually there. But we'll see today, too, that by understanding what's going on inside of a computer's memory, we can start to represent and even create and code more interesting things. So for instance, here is a bitmap, if you will, which is a term of art. A bitmap is a type of image. And it's a map of bits in the sense that you have this coordinate system of up, top, down, left, right, at least in this artist representation here. And suppose that maybe we all decide as the world that 1 shall represent the color white and 0 shall represent the color black. What might this map of bits, this bitmap, actually be? Can you see through it? Yeah. It is indeed a smiley face. So an amazing eye. If I actually turn all of the ones to white just to visualize this, you'll see indeed this is what was embedded there. But of course, on our computer monitors and phones, we have this grid of squares, this grid of pixels. So indeed, if you were to actually see on your screen a smiley face, like a black and white one at that, what's probably going on underneath the hood is just some pattern of zeros and ones and maybe single bits, 1-bit color, if you will, where 1 here represents white and 0 represents black. So if you kind of like this thing, it turns out you can do pretty beautiful, pretty interesting, pretty artistically inclined things. If you go to this URL at your leisure, cs50.ly/art, it'll actually redirect you to a Google spreadsheet that we've made in advance. And we've kind of shrunk the rows and columns to resemble a grid of pixels, tiny little squares, all of which are white by default, not unlike this easel here that we have a couple of volunteers working away at. In fact, would you guys like to come forward for a moment and say a quick hello before we come back to you?
Hello, my name is Daniel. I'm from Chicago.
Welcome to Daniel. And?
Hi, everyone. I'm Adam, and I'm from Trinidad and Tobago.
Nice. Well, welcome to you both. Thank you. You'll see that in their hands are actually a whole bunch of pixels, Post-it notes that we've handed them in advance. So if you don't mind, we'll come back to you in a couple of minutes and see what they've created, if you will, on this grid of white paper, much like you could create on this Google spreadsheet. In fact, feel free to send us your creations, if so inclined, via the URL you'll get at cs50.ly/art. Now, let's come back to week 0, where we defined some of the building blocks for images. We talked about RGB, which is just red, green, blue. And it's just one of the systems, a popular system via which you can represent any color of the rainbow using some combination of red and green and blue. And if any of you are artistically inclined or have used Photoshop or similar programs, you might typically have some means of selecting a color via some grid like this. But down here, notice there's explicit mentions of the types of color systems in use, RGB. And in fact, here you see 0, 0, 0. And up here under new, you see the color black. And that implies that if you have no red, no green, no blue, well, that indeed would represent, by convention, the color black. By contrast, if we play around with Photoshop or any similar program, if you have a lot of red, a lot of green, and a lot of blue, for instance, 255, 255, 255, like really crank it up to the max value you can represent with 8 bits per week 0, well, then it turns out you get the color white here. And we can play with these numbers endlessly. For instance, if we use 255 of red, but 0 green and 0 blue, not surprisingly, the square at the top of the screen becomes, of course, red entirely, because it's all red and no green, no blue. If we change it instead to 255 for green, but 0 for red and blue, of course, we get green. And then lastly, if we crank up the blue, but leave red and green as 0, we, of course, get blue. But all this while, down here highlighted, is something that maybe some of you have seen before, like some combination of numbers and letters. If any of you have made personal web pages or used programs like Photoshop, you might have used these so-called color codes. So indeed, the world has this convention whereby using 6 digits, or sometimes 3, you can represent a little more succinctly some amount of red, green, blue. And you'll see here, maybe by inference, that if RGB is 0, 0, 255 respectively, perhaps where we're going with this is that 0, 0, 0, 0, FF is just an alternative way of expressing the exact same idea. No red, no green, and a lot of blue. But why is that? And in fact, we'll come full circle here to introducing something that we could have done in week 0, but it doesn't really solve a problem then. But today, as we focus more on images and on memory itself, turns out understanding these patterns is pretty useful. So back in week 0, we talked, of course, about binary. And binary, by implying 2, only gives you 2 digits, 0 and 1. You and I, as humans, almost always use the decimal system in normal conversation, dec meaning 10. So we have 0 through 9 instead. If a human like us wants to count up as high as 10 or 11 or 12, we don't have a digit per se for 10, 11, and 12. We start reusing digits. So it's 1, 0, 1, 1, 1, 2, and so forth. But in other systems, not binary, not decimal, but systems called hexadecimal, hex implying 16, there are actually more digits than these, which might come as a surprise. It's not pairs of digits, like in decimal, single digits. And frankly, it doesn't really matter what the digits are, because at the end of the day, these are just symbols that you and I immediately associate with some notion of math, but just strokes on the screen that represent some actual value. So it turns out that by convention, when you want more than 10 digits, 0 through 9, you start using letters of the English alphabet, A, B, C, D, E, and F. And you can represent them in lowercase. It's case insensitive, so it doesn't really matter. You might see it in uppercase or lowercase. But this is how you can count beyond 9, not using decimal, but using indeed something called hexadecimal. If we get really technical, this is also known as base 16. And it's the same idea as week 0, where instead of using base 2 for binary, base 10 for decimal, use 16 as the base for hexadecimal. And so if we run through just some simple examples here, in the world of hexadecimal, your columns are just powers of 16. 16 to the 0, 16 to the 1, 16 to the 2, and so forth. But in the world of hex, we usually, at least thus far and today, we'll see just pairs of digits like this. So here, for instance, is the 1s column and the 16s column, if we multiply that out. So if you wanted to represent the number you and I know in the real world as 0, in hexadecimal, it would just be 0, 0. If you want to represent the number 1, it would be 0, 1. And from there, we get 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. Now things get potentially interesting. In decimal, it would obviously become 10. But in hexadecimal, it just becomes 0a and then 0b. Which is to say, if I rewind, after 9 comes in hexadecimal. If I pronounce it in decimal, this is how you'd represent 10. This is how you'd represent 11, 12, 13, 14. And then lastly, in hexadecimal, the 16th value is f, which is just always going to represent 15. So how do we connect this to some of the past math? Well, once you get to 0f in hexadecimal, if f is the highest you can count, just like in decimal, 9 is the highest you can count, what comes next? If this is 15, I claim, how do I represent 16 in hexadecimal? With what pattern of symbols? What pattern of symbols for hexadecimal? Yeah. So 1, 0, not 10, even though you might read it like that as a typical human, but 1, 0. Because why? Well, even if this is completely new to you, the whole column system, the places are exactly the same intuitively. So you need a 1 in the 16's place and a 0 in the 1's place. And we won't count all the way up to 255, but if we count a little higher, this would be 1, 0, aka 16 in decimal. This would be 1, 1, aka 17 in decimal, and then 18, 19, 20, and so forth, dot, dot, dot. And we can count all the way up to FF, because if F is the biggest digit in hexadecimal, FF is indeed as high as we can count. And if each F represents 15, well, let's just do the math like in week 0. So 16 times F plus 1 times F is how all of us learn to do math in grade school, even though not in hexadecimal. That's, of course, 16 times 15 plus 1 times 15. Multiply that out, you get 240 plus 15. And ergo, you can count as high as 255 using 2 hexadecimal digits. Now, this is not the kind of thing where this is going to be an interesting exercise mentally to ever convert in your head. Generally, you'll get used to the fact that after 9 comes A, and the biggest digit is F. And you'll just start to see patterns like this in the worlds of Photoshop, web pages in a few weeks, and beyond. But why is hexadecimal useful? Why are we complicating the world and adding on top of decimal something else? Well, it turns out that a single decimal digit, like F, the biggest one, for instance, is 15. And here, let me just propose a bit of mental math. How many bits do you need to represent the number 15 in binary? If you've got the 1's place, 2's place, 4's, and so forth, how many bits total? So fewer than 5 to count as high as 15, I think. But close. Someone else? Seeing a hand? Yeah. So 4 bits, I think, suffice. Because if you want to count as high as f, that is to say 15, I think if you have 4 bits, you can do that. Because if over here is the 1's place from week 0 for binary, this is the 2's place, this is the 4's place, this is the 8's place, do out some quick math. So 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So it turns out that by convenience, hexadecimal digits can just be represented consistently with 4 bits, or fewer, but 4. And 4, of course, is half of 8, and 8 is like everywhere. Like 8 bits is a byte, which is, again, just a convention we've seen. And so the reason that you see hexadecimal in the world of Photoshop and eventually web pages is it actually just maps really nicely to expressing binary numbers more succinctly with a fixed number of digits. So for instance, anytime you see 1111, 1111 in the world as binary, you know what? That's a little tedious to both say and write. You can represent more succinctly any group of 4 1 bits more succinctly in hexadecimal as just f. So 1111, 1111 in binary more succinctly and more commonly now in the world of Photoshop, memory, images, and the like is represented more succinctly as FF. And that's why, because it just maps really nicely to 4 bits. And so we can be a little more succinct. So any questions on hexadecimal, which is just another way of representing information, but using the same grade school approach? Yeah. Good question. If you represent 15 with f, it would use 4 bits. So base systems are really just a way for us humans on paper or on screens to represent information. If f represents the decimal number 15, the computer underneath the hood has to use 4 bits to represent it. So 1 hexadecimal digit, by convention, always implies 4 bits underneath the hood. So therefore, if you have 2 hexadecimal digits, like 00, that means 80 bits underneath the hood, like for red or for green. If you see FF, now we know that's 4 1 bits and another 4 1 bits. And if we do out the math, that's 255. That's why in Photoshop, 0000FF means no red, no green, and 255 of blue. And it's just way more succinct than writing out like, what, 8 plus 8 plus 8, 24 zeros and ones. And it's just cleaner than even using decimal when you're using units of 8, which, again, computers just use everywhere. So it's just another system. It's not one you need to dwell on very much. But again, it's fundamentally no different from binary or decimal. We're just using a slightly different base. No? All right, well, we had this blank canvas here. And I think, are you two perhaps ready to reveal for the world what you've created? Do you want to go ahead and I'll swivel it around for you. All right, here we go. Big reveal. And today's pixel art. A round of applause if we could. Very nicely done. Well, thank you both. If you want to come up after and tear this off and bring it home, you're welcome to. And keep the post-it notes too. Well, thank you to our volunteers there. Let's now translate this to really more technical world where we're going to see and consider it more often. Because in fact, sometimes when you've had error messages over the past few weeks from Clang, the compiler, you might have even seen evidence of hexadecimal. We didn't call it out. It wasn't useful to know at the time. But it turns out a lot of programs and a lot of code uses hexadecimal for those reasons of more succinct representation. So for instance, where else might we see it? Well, here's that picture we keep pulling up of our computer's memory. And each of these squares in this grid represents a byte, sort of top left to bottom right in the computer's memory. But again, just an artist's representation. A few weeks ago, I claimed that each of these bytes can be numbered, of course. Like this is byte 0 at top left, then byte 1, then byte 2, then byte 2 billion if you have 2 gigabytes of memory. And so we could just number them like this, 0 through 15 on up. 16, 17, 18, and so forth. But per the reasons earlier, it's just more common in computer systems and in software to actually use hexadecimal just to describe the locations of, the addresses of things in memory. So instead, a typical programmer or computer scientist would call these first 16 bytes 0 through F. Just because, but that's because it's a predictable number of bits. So if we keep going beyond that, you would get not 10, not 11, not 12, but in hexadecimal, 10, 11, 12, and so forth, all the way down on the screen to 1F. And if I shrunk this down or had a bigger monitor, we would see eventually 255 bytes later from the start, 255 as well. But there's a potential problem here with using hexadecimal in this way. There's an ambiguity. Can anyone imagine what can go wrong if we use hex to just simply describe locations in memory like this? Yeah. Yeah, like 1, 0 might also be 10. And, maybe if you're, really thorough, OK, wait a minute, it can't be 10 because here's f over here. So it's obviously not decimal. But why create potential confusion, especially when you're collaborating, building something with someone? We want to avoid that ambiguity. And so the convention humans decided on years ago is that if you want to make clear that a number is in hexadecimal, just by convention, you prefix all of the digits with 0x. The x is not like another character. It's not like a 17th character. It's just a human convention of putting 0x to imply here comes hexadecimal. And now it's unambiguous. So now we see 0x10 obviously is not 10 as we know it in decimal, but rather it's the number that comes after a single f. So it's really the number in decimal 16. So 0x, anytime you see it, that's just a visual cue that what is ahead is actually hexadecimal. So let's now start playing around with this information. So here's a super simple line of code from like week 1 where I'm just declaring a variable n, and I'm defining it to be the value 50. And this is out of context. We probably need a main function and all of that. But let's just rewind to week 1 where we actually saw code like this and do something useful with a line of code like this. So let me go over here to VS Code. And in VS Code, I'll create a program called, how about addresses, since the goal of this, the goal here is to just play around ultimately with a variable like n. And let me go ahead and do this. I'll include, how about standard io.h. I'll do int main void, so no command line arguments for now. Int n gets 50. And now so that we can do something mildly useful with it, let's just go use printf and print out with %i and then a new line, whatever that value of n is. So this is not going to be interesting per se. It's just week 1 stuff where I'm defining a variable and printing it out to the screen. So let me go down to my terminal window and do make addresses. No errors, so that's good. I'll do /addresses, and of course I should see the number 50 here. Now what's going on underneath the hood? Let's translate now code to really what's going on underneath the hood of the computer. So if this is our grid of memory, I don't necessarily know as the programmer, and I definitely don't care as the programmer where exactly it's ending up in memory. That's the whole point of using code. Let the computer figure this out. But at least conceptually, I know that by declaring a line of code like that, the number 50 ends up somewhere in the computer's memory, and it's assigned the name n, a symbol n, via which I, the programmer, can refer to it. And I very deliberately used 4 of these squares. For what reason? What might be the reason for using 4 squares specifically? Yeah. Yeah, so an integer is 4 bytes. At least most of the time on modern systems, an integer is 4 bytes. On an older computer, it might just use 1 or maybe even 2 bytes. But here, by convention, we're almost always going to see 4 bytes. I don't know if it's going to end up here. It might end up over here. But for now, who cares? I just know that the computer can store the information in this way underneath the hood. So let's now introduce another feature of C that we haven't had occasion to use just yet that's going to allow us to start poking around the computer's memory, for better or for worse. And this is one of those situations where you're about to acquire a skill, a power that can actually come back to bite you. Because once you know how to start poking around a computer's memory, you can do very powerful things. And next week, we'll see what you can build in a computer's memory. But you can also screw up pretty easily and cause more of those segmentation faults that a few of you have already suffered. So with that said, let's just stipulate that, you know what, I don't care necessarily where the 50 is in memory, but I know it exists at some address in memory. And just so I have an easy address to pronounce, let's just suppose it lives at 0x123. So that's the address in memory in hexadecimal by convention, and that just happens to be where it ends up when I write that line of code. But it turns out C has some other operators we can use. When we've seen the asterisk before, the star, and we've used it for multiplication. But today we're going to use it for something more powerful. And we're also going to introduce an ampersand, which allows us to do something as well. The ampersand operator is going to allow us to get the address of a piece of data in memory. Like by literally putting ampersand before the name of a variable, C will tell you what address that variable lives at. Maybe it's 0x123, maybe it's 0x456, who knows? But that will give you back the answer. The star does the opposite. It sort of means go there. So using the star, otherwise known as the dereference operator, I can actually go to a specific address if I want. And we'll see what this means in code. So how can I leverage this in some mildly interesting way to start poking around, but eventually we'll use this primitive to build more interesting things. So let me go back to, say, VS Code here, and let me go ahead and do this. I'll clear my terminal to start fresh, and I'll introduce another format code for printf, %p. And for now, just take on faith that it is %p because, but %p is going to allow me to print the address of a variable if I additionally tell C, get the address of n. So I'm changing %i to %p, and that's just something you have to do when printing addresses for now. But I need to change an ampersand in front of the variable name, so I don't print n, the number 50. I print out something like OX123. And it's not going to be as simple as that. We'll see on the screen, though, where it actually ended up in my code space's memory. So here we go. Down in my terminal, make addresses again to recompile. And now /addresses should reveal not the value of 50, but the address of 50. And there it is. It's pretty long. It's not quite as simple and pretty as OX123, but there's the OX, meaning here's a hexadecimal address, and it's 7F, FC, C784A04C. Suffice it to say, your code space, and even your Macs and PCs nowadays, have a lot of memory. That's why, in part, this address is so big, not as small as the thing on my slide. So this, at the moment, isn't that useful yet, but it introduces us to a concept that we'll now call pointers. And pointers are admittedly one of the more challenging aspects of C. And if in future life you tell friends that, oh, I took a class called CS50 and we learned C, like you'll probably get kind of a look at people like, why did you learn C? Or like, oh, C was hard. And it's largely because of this topic, which isn't to say that it's that hard to wrap your mind around, but it's definitely very different. And it's not a feature that you can harness in higher level languages that we'll see in class 2, like Python and Java and the like. C is about as close to the computer's hardware, so to speak, that you can get before things get actually scary. The so-called assembly language we saw in week 2 when I had to link and compile and assemble and all of that, like that gets really low level. And you really have to be an expert with the computer's CPU or brain to understand that. But with C, you can actually poke around the computer's memory and do powerful things with that. But again, with great power comes responsibility. It's very easy to break programs by misusing memory or just having a bug that touches memory in some way that you don't intend. So pointers, at the end of the day, are pretty much what we just saw. A pointer is really just a variable that contains the address of some value. A pointer is a variable that contains the address of some value, or more simply, it's fine to think of it as an address. A pointer is an address of something in the computer's memory. Now, what might we do to actualize this? Well, here's 2 lines of code. It turns out, by using our 2 new operators today, I can declare an int, call it n, and assign it a value like 50, just like before. If I want to store the address of n in a variable and not just print it immediately via printf, I can declare a variable, for instance, called p, but I could call it anything I want, like any variable. But because it's an address, it's not int p. It has to be int star p, so to speak. And the star here on the left-hand side of the equal sign is just a clue to C that means p is going to be a pointer. That is, p is going to be the address of what? The address of an integer. Now, technically, it's still an integer itself, right? Because an address is just a number, whether it's 123 or OX123. So this is really just a semantic difference. So int star p just means that this variable doesn't contain any old number, like 50. It specifically contains a number that is the address of something else. So how can I now use this? Well, let me go back to VS Code, and let me propose that we add a line of code like that. So instead of just directly printing out that value, let's go ahead and define a second variable called p that's of type int star p, set it equal to ampersand n, and then this time, let's not just print out ampersand n, let's actually print out the value of p. So the only 2 new things here, if I zoom in, are I've used not only the ampersand on the right to get the address of n, I'm now using the star on the left to tell C that p is still a variable as always, but it's a pointer. It is the address of some other value like this. And I'm still going to print it with the same format code, %p, so that doesn't change. So let me go ahead and zoom out and do make addresses and /addresses. And there it is, exactly the same thing. Now, in and of itself, not that useful yet, but the fact that you can now access the addresses of things in memory means that we'll be able to build things and construct things and link things together by knowing where they live, so to speak. So any questions on this technique thus far? Yeah? A good question. On line 6, must it be star, p, and ampersand? And in this case, yes, because what am I doing? On the left, and I'll get rid of the equal sign for now, this would give me a variable called p. That's not an integer per se, but that's the address of an integer. But without the equal sign, I'm not storing anything in that variable. So by adding the equal sign and then ampersand n, I am explicitly figuring out with ampersand what the address of n is, which already exists per line 5, and tucking it away in this new variable called p. Other questions? Yeah? Good question. Every time I run the program, it uses up a different piece of memory. Short answer, yes. Computers, though, long story short, also have something called virtual memory. So if you run it again and again, you might actually see the same addresses on the same Mac or PC or cloud-based server. But we'll see in a bit where, at a high level, it's laid out. But it will always exist at some address. Good question. Yeah? Correct. Ampersand n is the address of n, and int star p is a pointer called p. And honestly, in an ideal world, if C were made today and not decades ago when humans were first creating languages, ideally, we would just have a data type called pointer. And then this would be a little less complicated because it would literally be what it says. The humans who invented C didn't do this, but this is the idea. So pointer is not a legitimate word in the code. It is a term of art in English. But this is really just the idea. But the way you express pointer as a data type is a little more cryptic as int star p here. But notice, in line 7, when I print out p, I don't use a star. I don't use an ampersand. Why? I literally just want to print the value of p. And we've been doing that since week 1. If you want to print a variable, just describe the variable by its name. No special syntax. Any other questions on this thus far? What's the advantage of using pointers? With pointers, we'll see today some applications of them. Really, the idea is going to come to fruition next week when we're going to create what are called data structures in memory, where we can build not just, for instance, one-dimensional data structures like an array. We'll see next week we can actually create the equivalent of two-dimensional data structures or even three-dimensional data structures by using these addresses and sort of linking things together. And we'll see the beginnings of that this week. But for now, focus, at least for now, on just really the syntax and what these building blocks can do for us. Does the p pointer have to be point to an integer? Short answer, no. And we'll come back to this. For now, for the sake of discussion, we're only dealing with integers, like the number 50. You mentioned strings or characters. Absolutely. We're about to go there soon. So you can use the address of anything you want in the computer's memory. So in fact, let's translate this now to just the same picture, just to help you wrap your minds around what these two lines of code really fundamentally are doing. So if I come back to my grid of memory here, let's plop the number 50 in the variable n at the bottom right, like it was before. So this is that first line of code as before. But with the new second line of code, as soon as I create p, what do? Well, first, remember that n lives somewhere in the computer's memory. Usually, I don't care precisely where it is. But for the sake of discussion, let's suppose it's at 0x123, which is easier to say than where it actually ended up. And now, what is p? Well, p is just another variable. And variables live in memory, too. So let me just hypothesize that p lives up here. And it turns out that p, once you assign it, the value of ampersand n means that c will take a look at the variable n, realize, oh, it lives at 0x123. And what goes in the value of p is literally 0x123. So again, it's still an integer, which is confusing. But it's technically an integer being used as an address. And now just a prompt here. Notice that this pointer is pretty darn big. It's like 8 squares. What's the implication of that? Because I did that deliberately. How big must a pointer apparently be in most modern systems, would you say? OK, good. Computers today are very big. You have gigabytes of RAM in your computer. You therefore need big pointers to be able to point at memory that's conceptually pretty far away. So to be clear, how many bytes does a pointer apparently take up? Well, it seems to take up 8 in total. Integers by convention nowadays are usually 4. Pointers, though, nowadays are typically 8 in this case. So I'm drawing it in a manner consistent with the reality, even though at the end of the day, it's not really that interesting what values are in here. In fact, let's emerge from these weeds. I don't really care what else is going on in my computer's memory at the moment, because I've only got those 2 lines of juicy code defining n and defining p. So let's hide all of the other squares. And honestly, I mean it when I say that programmers need to know that a variable exists somewhere in memory and needs to be able to get that address using like the ampersand, but you're never going to printf like I did the actual address. Like it's not generally interesting unless you're debugging your code, but you're not going to like start typing out crazy OX numbers in your code to move things around. You just need to know that the computer can figure out where things are. So frankly, by that logic, who cares that it's OX123, right? Tomorrow it could be OX456 or something else. So one of the ways to think of a pointer is literally as a variable that points at something else. And indeed, in this case, p, yeah, technically it has an address, and yeah, technically it's OX123 in the story. But honestly, who cares? I just need to know that using p, I can get to the value n. And so what are these addresses? And in fact, if Carter wouldn't mind joining me up here for a moment, what are these addresses? Well, just like in our human world, we have mailboxes, even though you might not check it very frequently nowadays. But to get physical mail, every home, every business has a unique address. The Science and Engineering Complex is 150 Western Avenue, Austin, Massachusetts, 02134 USA. And theoretically, that uniquely identifies that building in the world. Well, here we have 2 mailboxes. Over here, we have a value n that happens to live, I'll claim, at address OX123. And then over here, I claim there's another address called by name p. I don't actually care where it is, even though it definitely exists somewhere in the computer's memory. But if this is p, which is a variable, and that's n, another variable, ideally, this mailbox would be twice as big because of the number of bytes using, but Home Depot only had identical size mailboxes. But here is p, one variable. There is n, another variable. If I open up this mailbox, what should I find inside of it based on our story thus far? Like what value will I pull out dramatically in just a moment? Yeah, I think OX123. Now, using this, you can kind of think of this as like X marks the spot, no pun intended, where I can now like walk around the computer's memory and find my way to that location by sort of following the treasure map. Or if I want to more dramatically, thanks to our little Yale foam finger here, you can think of it more abstractly as p is just pointing at n. OK, that's not going over well. So let's switch over to the Harvard one. So p is pointing. So p is pointing at n, and so it turns out we will be able to write code now that will do the equivalent of me walking over to n. But for now, Carter, if you want to reveal what's in the mailbox, we should see, indeed, the number 50. So that's really all that's, oh, I feel Carter's waiting for applause. So like really, well, nicely done. Thank you. So that's just like a physical metaphor of what's going on here. In one variable, we have an address, and that variable by convention is called a pointer. In the other variable, per week 1, we just have a value like n. And you can, yes, follow the map and walk yourself to that particular address. And we'll see how to do that in code. But what's really interesting is this abstraction, that pointers literally, or really, I guess, figuratively, point at some other value in memory. All right, questions then on pointers in this form. Can pointers point to each other? So yes, there's things called double pointers. We're not going to see them anytime soon, but using star star, you can express an address of an address. But we won't see that just yet. Other questions on pointers? Yeah, in front. Are arrays, so to summarize, are arrays then pointers? So short answer, there's a relationship, and we'll come back to that in a little bit. But arrays are technically different from pointers, but we're going to be able to blur the lines a little bit by using one like the other. But let me come back to that in just a bit of time. All right, so if we have now this mental model, if you will, of like what a pointer is in memory, I think we can start to peel back a layer of simplification that we've been assuming for the past few weeks since week 1. So a string, recall, is a sequence of characters. And so if you want to create a string that says hi in all caps and an exclamation point, we do string s equals quote unquote hi. And we can hard code it like this, or we could use getString. But for now, just assume that I hard coded it into my code to always say hi in all caps with an exclamation point. Well, what does that look like in the computer's memory? Well, let's stop looking at the entire memory. Let's just focus on really what's going on. Once you create a string called s and store in it hi, you know that a couple of things are happening. H and I and the exclamation point are ending up in the computer's memory. We know from week 2 that this thing, the so-called null character, NUL, aka \0, is also being added for you. And it's somewhere in memory. At the moment, I don't really care where. I drew it at the bottom right. Yes, it has an address. But for now, it just ends up somewhere. And in fact, here's a little visual cue as to how this happens. In C, anytime you use double quotes to give you a string, you can imagine that the double quotes are like a clue to not only store hi exclamation point, but also put the null character there for you. And this is in contrast to what? Chars, if you want individual characters, what syntax did we use instead? So single quotes. Single quotes do not add magically a \0. They literally just store one character. So again, strings have always been a little special. You get an extra byte for free so that you know where the string ends, and functions like stir compare can then find their way there. So in memory, it might indeed look a little like this. And if we assume that there's going to be somewhere in memory, these things are going to be somewhere in memory, we can address them per week 2 by way of the name of the variable. So if s is the name of the variable, s bracket 0 is how you would refer to the first letter, s bracket 1, s bracket 2. And if you really want, s bracket 3 would get you at the null character at the very end. But what is s? So technically, in this line of code here, not only is the computer giving you memory for hi exclamation point \0, it turns out that s itself must take up some amount of space, right? Because s is the variable. And every time we've talked about variables thus far, I've given you a rectangle on the screen in which to store its value. So let's assume, for the sake of discussion, that the h is at 0x123, and I is at 0x124, exclamation points at 0x125, and the null character is at 0x126. Well, what then is s? Well, s is just going to be some other variable, and I'll draw it somewhat abstractly without all of the other boxes up here. And I'll claim that the name of this variable is s. But it turns out, what is s really? How do strings really work? Well, s is a variable and has been since week 1. But when you define it, what the computer is doing for you automatically is when it knows you want to store hi exclamation point, it puts that somewhere in memory. The computer then figures out for you what's the address of the very first character. And it stores that address, and only that address, in the variable you created on the left-hand side of the equal sign. And that's enough. Like, to represent a string with 3 letters of the alphabet or punctuation, you don't need 3 variables. You just need one. You just need to know the beginning of the string. Why? Why is it sufficient for a variable to only store the first byte's address and not all of the byte's addresses? Exactly. Because of the design of strings, per week 2, we always null terminate them. So it suffices to only remember the first byte's address, because from there you can sort of follow the breadcrumbs, byte after byte after byte. And until you see the new line, the null character, you know that all of those characters are apparently part of the same string. So this is what's been going on in the computer's memory all since week 1. And in fact, if we abstract this away, you can really think of s as being just this. Really a pointer to that chunk of memory. So in fact, what do we have here? Well, to recap on the code here, on the left-hand side, string, that's what ensures that we'll actually be able to store a string in a variable called s. We're going to have on the right-hand side, though, the actual value. So let me switch back to VS Code here, and let me change my code to no longer involve integers alone. So I'm going to add the CS50 library, just so that I can use some shortcuts in there, cs50.h. And then in my main function, I'm going to go ahead and do this. String s equals, quote unquote, hi in all caps, exclamation point. And then I'm going to go ahead and print out, using %s as always, \n, the value of s. So this program at the moment, not interesting at all. It's just week 1 stuff again. /addresses indeed prints out hi. But it turns out that now that I know this, what's really been going on underneath the hood all this time? Well, here's that same line of code that defines the variable called s. And it turns out, anyone want to guess what string is actually a synonym for? String, it turns out, is kind of a white lie we've been telling since week 1. There is no such thing as string as a keyword in C. It's technically a CS50 thing, yeah? It's a pointer to a character. So really, all this time, we've kind of been lying to you. There is no string, quote unquote. It's actually char star. And if I may dramatically, here go the training wheels. Like, OK, that didn't land very well. So what have we been doing? Well, it turns out that string is a much easier way conceptually to think about what a string of characters is. Like, my God, if we had to start in week 1 by having you type char star, like, yeah, you might get past it. But like, this is just way too much ugly syntax, not intellectually interesting at all. So we abstracted away what a char star was in the first week of C by telling you it's actually called string. Now, string is a term of art. Like C programmers are in any language will use the word string to mean a sequence of characters. But in C, it's not technically a word unto itself. It's rather a synonym that we ourselves created in some form. So in fact, how did we do this? Well, think back to just last week. Last week, I proposed that it'd be really nice if we had a person data type, which the creators of C did not think of decades ago. But that's OK. We can define it ourselves. What did we do here? Well, we're using syntax like this. Recall that we defined a person to be what? To be this structure. This structure, using the new keyword last week, struct, means that a person is just a name and a number. And it could have been other things. We just kept it simple. But how did I associate person with that structure? Well, we claimed that it was this value here, typedef, which, as you might expect, defines a data type. So what did we do as CS50 back in week 1 without telling you? Well, we could have done something like this. Like int itself is a little cryptic, and maybe we should have, to keep things even simpler, said, hey, everyone, turns out you can define integers in C. And if you wanted to do this, well, if you want to create the keyword integer as a data type, you can just typedef it to int. So typedef creates the word on the far right, integer, and creates a synonym for it, in this case called int. So what did we do in week 1 without telling you? We have a line of code like this in the CS50 library that associates quote unquote string with, more cryptically, char star. And this is why in week 1 onward, anytime you use the CS50 library, you can write the word string as though it's a real C data type. And that's just because we wanted to have this abstraction, these training wheels on for the first weeks, so we don't have to get in the weeds of all this crazy memory stuff. We can sort of talk about strings at a higher level. But that's all they are. Strings are the address of the first character in that sequence of characters. Questions now on any of these details? Yeah? Good question. What about the strings library, which we have used? Unrelated. So it does not define the word string. Everything in there actually relates to char stars. And so in fact, if you've used the CS50 manual, which is just our user-friendly version of the actual manual pages for the official language C, you'll see throughout that now, if you start poking around or turning off less comfortable mode, you'll actually see that we've changed any mentions of char star in the official documentation for these first weeks to just string, to simplify it. But underneath the hood, C does not know the word string per se as a keyword, but it's absolutely a concept that like every program in the world knows about. And in fact, in other languages, in Python, for instance, there will actually be a proper string, although it's not going to be called string. It's going to be called str, S-T-R for short. Questions on these strings here? Well, let me propose there's one other feature of this syntax that we can now leverage as follows. Let me propose that if we go back to the previous version of my code here, wherein, let me switch back to VS Code in just a moment. I'm going to rewind in VS Code to the integer version of my code from before. And most recently, it looked like this. Before, when we were using integers only and not, in fact, strings at all. Let me propose that there's this other feature of C that we can use that actually allows us to go to an address. So at the moment, let me just rewind and do make addresses to remind you what this program did when it was using integers alone. And there's that address. Why? Because on line 7, notice, I'm printing out the value of p, which is a pointer. So of course, it's going to look like an address. But let me zoom out now and make one change. Instead of printing out p, how can I use today's second new operator, not the ampersand, but the star, to actually go to that address? Well, what I can actually do on this line of code is this. If I want to print out the actual integer 50 that's in that variable, or equivalently at that address, I can go to p here and not print p literally, because that's just an address. I can now say star p. And star p means go there. More technically, dereference p. That is, follow the treasure map to the actual address and do what Carter did, open the mailbox and print whatever was in the mailbox, which recall was the actual number 50. So let me try this. Let me recompile the code. So make addresses. OK, let me clear my terminal window. /addresses. This time, I shouldn't see the OX anything. I should see just the number 50 in this case. And here, too, is kind of an unfortunate design decision. Certainly pedagogically, I would say in C. If I zoom in on this code, star is unfortunately being used in 2 different ways. In an ideal world, they would have used 3 different symbols to make this more semantically clear. But this is what we're stuck with. So in line 6, when you declare a pointer, that is a variable that stores an address, you put the type of variable that you want to point at, then a star, just because, and then the name of the variable. And then on the right-hand side, you actually get the address of whatever using ampersand. But when you want to go to an address, you want to dereference a pointer, you don't use int again. And we've never done that, right? Once you declare a variable, you never again mention the data type. But in the world of pointers now, if you want to not print out p, but go to whatever address p is storing, you use star p here. So a good visual indicator would be when you declare a pointer, that is, make it exist in your program, you have to declare the data type with the star. But when you use a pointer, you just use the star. In an ideal world, this would be a completely different symbol. But again, this is what we have. Questions now on that syntax? Yeah? Why can't we just do the ampersand here, are you saying? It was still a little quiet. So strictly speaking, we do not need line 6. So this is really for pedagogical sake that I am defining a separate variable p and then printing it out. At this point, though, I'm just kind of going in circles, if you will, because more simple would have been what I would have done in week 1, which would be get rid of p altogether, get rid of p here, and just print out n, right? But today, we're just giving you this new building block, this new syntax via which you can figure out the address of something and then reverse the process later and actually go to it as well. Other questions on what we've done here with these pointers? All right, well, let's context switch back to the string now and see what more we can do with this here. In the case of our strings here, let me refine this to zoom out. Let me delete the integer-related code here. Let me do string s equals quote unquote hi in all caps. Let me go ahead and for the moment include CS50.h at the top so that indeed I can use the keyword s, or string rather. And let me go ahead now and do something more than I did last time. Last time I did printf of %s\n, and then I printed out s. And again, I'll recompile this just for clarity. Make addresses, /addresses, that just prints out hi. So that's, again, week 1 stuff. But now that we have this other bit of syntax, we can do some interesting things too. So for instance, suppose I want to print out not s itself, but what if I want to print out the address of s? Like at what memory location is s? Well, I can change my %s to %p, which now we know p is for pointer. So %p means print out the value of a pointer. That is an address. And here, I can actually print out s itself. But why that is, we'll see in a moment. Let me do this. Here go the training wheels. String does not technically exist, but it does if I'm using the CS50 library. But if I get rid of the CS50 library, as I'm metaphorically doing by taking off the training wheels, I can't use the word string anymore. And in fact, let me make this mistake deliberately, as you might have accidentally in past weeks. Here's the error message I get if I forget the CS50 library. Use of undeclared identifier string. Did you mean standard in? It's trying to be helpful, but it's not, because I didn't mean standard in. So indeed, this is confirmation that C does not know the word string exists, at least as a keyword. Exists as a concept, but not a keyword. So I could fix this by adding back the CS50 library, but that's kind of a step backwards educationally as instead of a step forward. What could I do instead to fix this now if the training wheels are now off? Yeah. Exactly. Replace string, quote unquote, with char star instead. So I'm going to go ahead and change this to char. Technically, you can put the literal star here, the asterisk, or you can put it there, or you can put it here. By convention is to do what I'd done from the beginning, put the star next to the name of the variable as opposed to anywhere else. Let me go ahead now and sorry, I meant to add the spaces there. You could do this too, but this would be the most normal convention. So now let's do this. Make addresses. Compile's OK now. /addresses, what should I see? Hi or something else? Feel free to just call it out. So still high, you say? Someone else? A memory location. All right, so it could be one of the two options, right? Either I'm going to see the string or I'm going to see a memory address, though I do in fact see a memory address, and this one's quite different from the integer one. But does anyone now want to explain why you were correct? Why am I seeing the address down here and not high? It's subtle, yeah. Exactly, because I left my %p there, which means, hey, printf, show me a pointer. But this is where printf is smart and has been smart since week 0. Humans who invented printf decades ago wrote code that notices that, OK, %s means to treat the following value, not as just an address per se that gets printed literally, but print it, as with the mailbox demo, as sort of a treasure map that leads you to the address of a character. So simply by changing one character, %p to %s, and if I now do make addresses again and /addresses, this now is identical to week 1, but hopefully makes sense because %s is just a clue to printf that means go to this address in s, we'll print out every character there and thereafter until you see what? The null character, and then stop printing anything more. And this is why high has printed since week 1. Today we can see the address %p, but this combination of having access to addresses and the null terminator is all the information printf needs to actually do something more useful by printing the actual strings. Any questions now on this approach to %s? Yeah, in back. Oh, so why is it traditionally being used in this way? Honestly, the word string has been around for decades. It's not a keyword you should be able to type in C unless you're using a library like CS50s. And so %s just means string. So even though it doesn't exist as a keyword, %s connotes string. And humans decades ago, like today, just kind of know what that means. So they could have chosen any letter of the alphabet, but s sort of makes the most sense. All right, well, in back. Other question? Good question. Before, let me zoom in. I did not use a star before the s. Why? Well, it's subtle here, but printf was invented years ago to know, given an address, like in the variable s, printf knows to go there. So if we looked at the source code that some human wrote years ago for C, we would likely see the actual asterisk that you're referring to. Printf is taking on the responsibility for going to s. If you were to do star s here instead, an asterisk and then s, that would now be literally a character. Because if I say star s, that means go to the address in s, and all you're going to find there is a single character. What printf wants to know is not what is the character there, what is the address of that character. Why? Because printf needs to walk through the rest of those characters looking for the final null character. And in fact, let me see with a bit more syntax if we can highlight this a bit more. Let me do this. In addition to printing s, let's try out our syntax in another way. Let me print out with %s. How about not s here, but let's print out some addresses. %s \n, close quote. And then let's print out, how about this? The first character in the string s would be called s*0. But how do I get the address of the first character in s? Well, I could technically just use today's new primitive. I can just add an ampersand. That always gives me the address of some value. So when I end this thought and clear my terminal window and run make addresses, still compiles. When I run addresses in just a moment, any guesses as to what I will see line by line? This will print out two things. And you don't have to remember what the actual number was. But at a high level, what will be printed now? The same thing twice. Why? Well, when I run this, what I'm printing here, and let me zoom in at the bottom, I indeed see two really long addresses, but they're in fact the same. Why? Well, that's because, again, if s is the address of a character, as implied now by either the CS50 word string or the actual phrase char star, well, then s is just an address. By contrast, per week 2, s*0 is a char. Always has been a char, a specific char. But if you want the address of that char, you just add the ampersand. Well, it turns out that strings, per the definition we keep emphasizing, is just the address of the first character in a string. So of course, if you do this, you're going to see the exact same thing. And if I do this a bit more, generally you don't want to copy paste, but this is just for visualization's sake. Let me print out all of the characters. So another, and let me change this to print out the address of bracket 1, bracket 2, and bracket 3. So all 4 characters, HI, exclamation point, and the null character. Notice I'm using %p for all of them. So if I now do make addresses and /addresses. Now notice, and this is kind of cool, the first two are indeed still the same, but what's noteworthy about the other values on the screen? Yeah, they're consecutive. Each of these is just 1 byte away. Even if you're not good at hex yet and there's a crazy number of digits here, who cares? They're all the same except for the last ones. 4, 4, and then 5, 6, 7. And this confirms what I've been claiming for weeks, is that in an array, all of the characters are back to back to back, contiguous, 1 byte away. So with just this ampersand, with just this star, like, it's actually a pretty cool tool in the toolkit to have, because you can start to poke around what's actually going on inside of the computer's memory. And in fact, if we do this, I can introduce one other cool trick here, if you will. Let me propose that we can actually now do arithmetic on pointers. And you don't have to. You'll see a simpler way to do this. But now that you have perhaps this underlying understanding of where things are in memory, and it's just addresses, we can actually do something kind of neat. We can do something like this. Let me go back to, how about the string version of this with hi. And let me do this instead. Let me clean this up a bit, get rid of some of these lines of code, and let me do this. Let me print out %c, %c, %c. Let me get rid of all these ampersands. We're going to roll back to like week 2 stuff. Just to be clear, when I compile and run this version of the program, and I'll zoom in, what should get printed on the screen? This is just week 2 stuff now. No pointers per se. Yeah? Just HI exclamation point, 1 per line, because I have all of these \n. So let me do that. Let me go down here, make addresses, enter. OK, pretty good, /addresses, and indeed HI exclamation point. But now, if you're getting a little more comfortable, and it's fine if you're not yet today, but over the coming week or weeks, as you get a little more comfortable with the equivalence of addresses with our definition in the past of arrays and strings and all of this, you can start to play around. And I can do this instead. If I want to print out the first character in the string, I could do, like week 2, s bracket 0. Like, that will always work, and you can keep using that. That's not a CS50 thing. It's just a convenience in C. But I could technically print out not s, because s is an address, but what would be the syntax I could use to say print out the character at s? Any instinct? How can I say go to the address in s? It's one of 2 possible answers today. So of our two new operators today, we have the ampersand and the star. Which one will lead us to what is at an address? So the star. So in fact, if I want to print out what is at address 0 at the address s, I can just do star s. And if you really want to get fancy, how do you print out the second character that's immediately to the right of it, so to speak? Well, you can go to with the dereference operator. And do you want to answer this one? S + 1. Ergo pointer arithmetic. Like, you can do math, simple addition, subtraction, whatever, on pointers if you want. And you can do this here too. So star, if you want to pluck this one off too, how do I print out the last character, the third? S + 2. Right? Because if you know and understand that, like, a string is just a sequence of characters, every character is just a byte, and these bytes are back to back to back, you can just go wherever you want in the computer's memory. And here, I can do make addresses again, /addresses, and voila, we now have hi exclamation point. So we haven't printed out anything new, but again, just by using these 2 new operators, the ampersand and the star, you can figure out the address of something, and you can go to the address of something. OK, question in back. Indeed, it ends up being the exact same. And so I might have used this term before, the ampersand technique, the square bracket technique, where you do s bracket 0, s bracket 1, s bracket 2. That's actually what we would really call syntactic sugar. Like, it works, and you can use it. You should use it. It's nice and simple. But the square bracket notation underneath the hood is essentially being converted to this, which this is not fun, right? Like, this is when you want to show off to your friends, like, you know how to do cool stuff in code. But this is not as readable as just s bracket 0 and 1 and 2. But that's all that's happening underneath the hood. And so again, this is why in CS50 we spend time on some of these lower level building blocks, because if you assume that indeed your computer's memory is just this grid of bytes, and you have now the code ability in code to get an address and go to an address, you can start doing anything you want. And you can poke around a computer's memory at any location. And herein lies the danger. Like, I'm kind of on the honor system right now that if my string is hi, exclamation point, it's kind of up to me to go to the first byte, the second, and the third. But I could get kind of crazy now. And if I want to see what's going on in the computer's memory, I mean, there's nothing stopping me from doing like s plus 50. And let's see what's there. So make addresses, /addresses, hi, and then, OK, nothing, it seems. Well, how about 5,000 bytes away? Let's just poke around what's inside of the computer's memory. So make addresses again. Make addresses, /addresses, enter. OK, still nothing there. Let's try 50,000. All right, make addresses, /addresses. OK, there we see it. So you've probably done this, some of you, by accident, because you probably went too far to the left or to the right in an array, touching memory that you shouldn't. Suffice it to say, I should not go blindly touching 50,000 bytes away, because who knows what's there. And indeed, in your computer, when a program is running, the computer segments it into different segments of memory. And if you get a little too greedy and you touch another segment of memory that technically was not allocated to you by Mac OS or Windows or Linux or the operating system, bad things happen, and you get a segmentation fault. And that means it's a bug in your code. So you can now do this. And this means hackers, too, can do things like this. If they can somehow inject code into your C program, maybe they can poke around the computer's memory. And indeed, this is kind of the technique whereby maybe a really sophisticated hacker can jump to this memory, this memory, this memory, looking for something like your password or your financial information or anything that's in the program but at some other address. There's nothing stopping an adversary, at least right now, from poking around, if they can execute code on your computer, from doing this kind of thing. So there, and again, is the power of C, but also the danger. And you'll absolutely suffer more seg faults in the coming days. But ultimately, the goal is going to be to help you solve them ultimately and fix things. But for now, I think that was quite a bit. So let me propose that we go ahead and take our longer break here, maybe 10 minutes, and have ourselves some whoopie pies in the transept. We'll be back in 10. All right, so we're back. And to recap where we left off, you now have this new capability in code to do pointer arithmetic, like treat addresses as numbers, which they really are in hexadecimal or otherwise, and like add them together and kind of poke around a computer's memory. And it was asked during break, actually, how we might further harness this in the context of strings. So I didn't change the code we wrote just before break. Recall that we last broke the program by checking out bytes 50,000 bytes away. But let's not do that, and let's actually try printing out not individual characters like I did per the %C, but why don't we try printing out strings and substrings, if you will. So let me clear my terminal window. Let me change all of these %Cs to %S, 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 and then let me rewind to what we've been doing since week 1 with strings, which is just print them out. For instance, with that first line. And the only difference at the moment is that now I took off the training wheels. I got rid of CS50.h, wherein string is typedef to char star for you. Got rid of that. So now on line 5, I'm declaring s as being a char star, which just means the address of a character. And printf is smart enough to know that the end of a string is wherever that null character is. But now that I can do pointer arithmetic, notice that I could do something like this. If I want to print out s, I just print out s. Suppose I do s plus 1 here and s plus 2 here, again after changing %C to %S. Any intuition around what this code will now print on the screen, line by line? Yeah, thoughts? OK, reasonable conjecture. Maybe the memory address of H, that of I, that of exclamation point. But other thoughts? Yeah, I think it's actually going to do the latter. It's going to print hi in the usual way, because honestly, line 5 is this, line 6 is the same as like week 1 stuff, except we took off the training wheel of string and we're calling it char star. But I think line 7 is indeed going to print out I, and line 8 is just going to print out because it'll be just the exclamation point. Printf will still be smart enough to know where each of those substrings, portions of the string, end by the same logic as always. But let me go ahead and zoom out, run make addresses, enter, compiles OK, /addresses, and now, indeed, this is all a string is. It's a sequence of characters identified by its first byte. If you then start poking around and tell printf to print at what's at the next byte or the next byte, it's going to do its same thing, printing out that character and everything after it up until that null character. So again, even though there's like a lot going on, we've introduced these two new operators, like there's nothing that's happening today that hasn't been happening for weeks, but hopefully through this week, this week's lecture, this week's problem set and beyond, you'll start to realize that now you just have more tools via which to harness those lower level implementation details. So last week too, recall one other implementation detail. I claimed that you could not compare two strings quite as easily as you could compare two integers, for instance. And I told you to use a different function instead that you probably used one or more times with the past problem set. How are you supposed to compare strings, apparently? Yeah, so string compare, strcomp, that additional function that we said, you just have to use it for now. But you might have a little intuition already as to like why we have to use str compare and we can't just use equals equals to compare strings. Like any intuition for this already? Why was str compare necessary last week? Perfect. Equals equals would compare literally the two memory addresses instead of the actual strings character by character. And unless the memory addresses are literally the same, so you compare that exact same memory address, two different strings probably are not going to be considered equal, even if to us humans they indeed look equal. So let's see this. Let me go ahead and close addresses.c. And actually, before I do one last mention, one of the powerful things about pointer arithmetic, as an aside, is that C, and really the compiler, is smart enough to know how many bytes to keep adding and adding. And by that I mean this. Right now we got lucky because a string is a sequence of characters. And by definition, every character is a single byte. You can poke around and do s plus 1 to get the next byte, s plus 2 to get the third byte. However, if we weren't dealing with strings, suppose we were dealing with integers that were in an array back to back to back. If you wanted to get at the next integer, you could still do plus 1 or plus 2 to get at the next or the next integer. You would not start to get into the weeds of doing plus 4 and then plus 8. You don't have to know or care how big the data types are in the computer. C and the compiler will figure that out for you based on the data type in question. So keep that in mind if ever doing this on a different data type than chars. All right, so let me go ahead and open up a file that I wrote in advance most of. And let me hide my terminal window and show you this. So here's a program called compare.c, whose purpose in life is to compare two strings. I'm back to using the CS50 library because at least for now and probably a couple more weeks, it is so much easier to get input from the user using CS50's function, getInt. But we'll conclude today by taking off those training wheels as well so you can see how you can actually get user input with nothing CS50 specific. So lines 6 and 7. Pretty boring, week 1 stuff. Get an int called I, get an int called j, and store them in two variables, I and j respectively. If I equals j, print out the same, else print out that they're different. Let me just stipulate for time's sake, I'm pretty sure this code is correct. This will get two integers from the human. It will compare them and tell me correctly if they're the same or different. And I'll prove as much by running make compare /compare, and I'll type in 50 for I, 50 for j, and they're the same. And now I'll do how about 50 and say 13, and those are different. So let me just stipulate this code is indeed correct. Would have worked in week 1, also works now in week 4. But let me now change it to compare not two integers, but as I hinted, maybe two strings instead. So let me go ahead and change this line of code to maybe be string s equals get string, asking the user for s. Then let's change this second line here to be string t, just to keep the variable name short for now. And t is a good choice after s for something like this. Get string, prompt the human for t. And then let's change our I and j here to do the wrong thing. Per the intuition earlier, if s equals t, then print out the same, else print out that they're different. Now, if I want, I could take off at least some of the training wheels. I could change this to char star. I could change this to char star. Either's fine. I still need the CS50 library, though, because I'm using get string, because it's actually hard, as we'll see today, to get strings manually without using a library. But I'll keep it using string just for now with the library. All right, make compare again. /compare, and now let me go ahead and type in, for instance, hi, exclamation point, enter, and hi, exclamation point, enter, and they're different. All right, they're obviously not visually, but they are underneath the hood. And you probably do have the intuition for this already, whereby what's going on underneath the hood is that we're comparing accidentally the two memory addresses. So in fact, let's go there. Let's consider the memory. And let me zoom out now so I can just have more bytes to play with. So the squares are a little smaller than before, just so we can fit more in them. And let me propose that when I declare s on what was line 6, a moment ago, it ends up somewhere in memory, like the top left-hand corner of my picture, for discussion's sake. And when I execute that same line of code and getString is called, and I type in hi exclamation point, we know from week 1 that getString puts it somewhere in the computer's memory, and I'll propose that it's in like the bottom left-hand corner of the screen here. What happens after that? Well, I know, even though I don't generally care, that hi exclamation point in the null character exists at some address, like 0x123, 124, 125, 126, for discussion's sake. And what's in S? Same as before break, 0x123. So that's all that's happening again on line 6, which is pretty much the same as when we were getting an S earlier. But notice now with line 7, when I get a second variable called t and I call getString again, and by coincidence, as the human, I type the same thing. Well, what happens here? T gets its own chunk of memory, maybe at the top right. That second version of hi gets somewhere else in memory. You know, the computer could be smart and notice it's the same, but C doesn't generally do that for you. It just plops it somewhere else in memory. And maybe it's at address 0x456, 457, 458, 459, or wherever. But you can perhaps see where this is going already. T now, of course, contains the address of that first byte. And so in my code on line 9, when I compare S and T for equality, suffice it to say, they are not equal. Because of the way the strings are laid out in the computer's memory, it indeed looks the same values are there. But if we abstract away further, you can really see that S and T are not the same themselves. And so how did we fix this? Or really, how did we avoid this last week without spilling the beans and going down this rabbit hole of explaining like why you have to use stir compare? Well, if I go back to my code here, let's do it now the right way. Let me go ahead and include a line of code that says string compare of S, comma T, both as inputs. And then, if you recall, what does stir compare return when two strings are equal? There's 3 possible return values. So 0. So 1 is for if it comes alphabetically or ASCII-betically first or second. But for now, I just want 0. If I want to use stir compare, I do need string.h. So string.h does exist. That's not a CS50 thing. There's no keyword string as a data type. That's a CS50 thing. But string.h does exist. So I think now, with that change on line 10, if I do make compare and /compare, and then run again, type again, hi exclamation point, hi exclamation point, I think now they're the same. And just as a second check, hi in all caps, maybe hi in lowercase, those are in fact different. Why? Well, stir compare, which was written by some other human decades ago, is just smart enough to know that it should go to S and go to T, start comparing them left to right, stopping once it hits one or both null characters, and return 0 only if everything in S and in T are exactly the same. Are any questions then on this here? Any questions on why we're using stir compare? All right, if no, yeah, in the middle. Yeah, so why is it not the case with integers? So it turns out it's not the case with integers, with floats, with bools, with doubles, with longs. Like literally every other data type works correctly. Strings, though, are special. They're useful enough in programming and have been for decades that the authors of printf and the authors of stir compare and bunches of other functions, Sterling for that matter, just kind of treat strings special because they're just useful, right? We humans interact using language, be it English or anything else. And so it's just useful to have into the language C just sort of first-class support for this notion of strings of human text. So the short answer is just because. Like it just is necessary. Strings are different. They're implemented with this address and the null character. Everything else, though, is just a value. But a string, again, is a white lie. It's an address. It's not a thing unto itself. Good question. Yeah, in front. Oh, really good question. So in my code here, in VS Code, what if I do this? Instead of stir compare, and instead of if s equals t, what if I start playing around using star s and star t? Really interesting case to consider. Let's go back to our sort of deductive logic here. So star, the asterisk operator today, means go there. So when I've typed in hi once and then hi again, both uppercase, for instance, what is at the address S literally? Someone else. What is at the address S? Yeah. So not quite. At the address. Not what is the address. What is at the address 0x123? H. And what is at the address 0x456? H also. And so here, you're kind of cheating. Like you're comparing the first character of both strings, but not every other one. Now, you could be really pedantic. And here, again, this is not like a good use of code. But you could do this. If that, and how about this craziness? So star s plus 1 equals star t plus 1. And you could do this for every character manually. But that's why stir compare exists. It does all of this for you. But that's why. And that's the intuition. So I would encourage you to, anytime there's something kind of weird going on, I realize we might be straining credibility now. We haven't told you that many white lies. And so most everything that we've seen thus far can explain pretty much all of the behavior up until now from week 1 onward in C. So let me revert this back to the right way. If stir compare of s and t equals 0, this now is the right version of the code. And now here is again where you can play. So let me do this. Let me clear my terminal window just to tidy things up. Let me get rid of all of this comparison stuff. And let's just see what's going on. As you are welcome to in your own code, let's print out, for instance, as we might have in week 1, the value of s itself in a new line, comma s, and then let's just print out t just to make sure it compiles and I'm not doing anything wrong. But this is not going to be that interesting. And frankly, I don't need string.h anymore because I'm not using stir compare. So make addresses, /addresses. There's my, oh, sorry, that's fun. OK, not %t, %s here too. Ignore that. Let's do this again. Make address, oh, and that's the wrong program. OK, let's do make compare. /compare, and let's type in hi again, and now we just see the two strings. I'm not comparing. But now we can kind of play around, right? Instead of printing out %s, which prints the string, how do I print the address in s? I just need to make a slight change. If I want to see not what's at s, but I want to see s, the address. Yeah. Perfect. So change %s in both places here to %p. So now printf will treat it literally as an address. It's not going to do any fanciness with a loop from left to right looking for the null character. It's just going to print out s and t. So let me clear my terminal, run make compare. Whoops. Let's do make compare, /compare, enter, type in hi again, and now you see, oh, so this is interesting. It's not quite as straightforward as the other values, which were 1 byte away. They're almost the same, but this one ends in B0. This one ends in F0. So they're indeed separated by some number of bytes. Not just one, but a few, because these strings are indeed longer. All right, so once you've seen this here, how can we now maybe leverage this to solve other problems? Well, let me propose that we do this. Let me zoom out here. Let me close compare. And let me open up another program I wrote part of in advance called copy.c. So copy.c, in theory, makes a copy of a string. How? On line 8, I'm using the same thing as before, get string, storing it in a string or char star, and asking the user for it. Then I'm not asking get string again. I'm just making a copy, super simply, with line 10 here, string t equals s. Now, intuitively, I think that's how I would copy a variable, right? That's how we've copied variables every week thus far in C. But something's going to go wrong. In line 12, in English, does someone want to explain what you think line 12 does? Don't worry about finding any bugs or mistakes. But what does line 12 seem to be doing using toUpper, which is thanks to the C-type library, which I've included the header file for? Yeah. Yeah, right? It's kind of like ugly syntax, but this would seem to be capitalizing the first letter of t specifically and just changing it. So we have t bracket 0 here because we want to save the change, and we're passing to toUpper the first character here. So this is how we did uppercase in the past, and now I print out s and t respectively using %s. So this feels like it should work. I copied s and stored it in t on line 10, and then I change t and only t on line 12. But you can perhaps, if you're comfy thus far, see where this is going if I do make copy, /copy, and let me type in lowercase hi, exclamation point this time, just once. So I'm going to hit enter, and watch what we see for the value of s and t. The new value of s and t at the end of my program seems to be what? It seems to be the same. Hi is capitalized both times. So what's the intuition then for this? Why did this just happen? Yeah, and back. Yeah, I assigned S and T the same memory address. So it did copy S into T, but C takes this very literally. What is S? It's an address. What is T? It's a copy of that address. If you want to copy the whole string like a normal human would expect, hey, you or someone has to do a lot more work. You have to go to that address, copy this character, this one, this one, this one, and copy it to a new location in memory. That does not happen automatically here for you in C. It does in some other languages. Those of you who've programmed in certain higher level languages, this just works as you would hope, and that's one of the benefits of Python and other languages that we'll soon see. But for now, it literally takes at face value what this is. Copy the address into this address. And I'll make that more clear by getting rid of the string keyword, which again is just a type def. This is technically an address here. This is technically an address here. So what's being copied is the value of that address, not all of the characters that might very well follow it. So I should make one note too here. I'm going to start getting more in the habit of trying to avoid segmentation faults because things could go wrong here. For instance, on line 12 previously, I was kind of blindly, naively, dangerously assuming that there will be at least one character in S or T. That might not be the case. If the user just hits enter, there's no characters to uppercase. And so this is reckless of me and could theoretically create a seg fault. So I should probably start to be smarter and say something like this. If the length of T is greater than 0, OK, now it's safe to actually capitalize the first letter. And that will decrease the probability now of those segmentation faults by just not making any assumptions about what the human does. Almost always, your programs will crash when you've made a mistake, yes, but the user gives you an input that you yourself did not expect. So what does this all look like in memory? Well, let's go back to the big grid, this time focusing on the copying of values. And let's do this. Here's S, as in this new program, just declared to be a char star. Here is where my lowercase hi maybe ended up in the computer's memory. That's probably at 0x123, 124, 125, whatever, something like that. And that's, of course, what ends up in S as a value. When I declare T, I do get a second variable called T, just like before. But when I copy S into T, what happens? It's really just literally 0x123. Whatever the value of S is now also the value of T. And so if we abstract this away at a high level, get rid of all of those extra squares, this is what S and T now are. They're indeed copies, but copies of each other, not copies of the underlying characters. And so if you follow those arrows and try to print them both out after capitalizing one or the other, you're going to unfortunately end up capitalizing not just one of them, S, but both of them, S and T, because literally it's the same address. Any questions then on this visualization? Yeah? Good question. Is this pass by reference? We have not seen in detail an example like that. Right now you're copying by value. But references will come into play, and remind me in a bit if I haven't used that term yet. But this is just copying things by, could have ended poorly, value. Other questions? No? All right, so with this in mind, like how do we actually copy things properly? For this, we actually need another building block. So today we give you two functions, one of which is called malloc, one of which is called free. And these are used all of the time by like every piece of software you and I use on our Macs, PCs, and phones, whether it's written in C or some equivalent other language. Malloc is for memory allocation. It's a function that you can use to ask the operating system, Mac OS, Linux, Windows, anything, for some number of bytes. 1 byte, 100 bytes, a gigabyte of memory. You can ask malloc for however much memory you want in advance. It will return to you the address of the first byte of memory that it found free for you. Unlike a string, it is not null terminated. And so the danger with malloc is that it's on the honor system. If you ask it for 1 byte or 10 bytes, you, the programmer, in like a variable, have to remember how many bytes you requested, 1 or 10 or the like. Strings do that for you, not when we're getting now to this low level. Malloc's just going to give you some memory, and it's up to you to manage it. Free does the opposite. When you're done with some chunk of memory, you can free it by passing in that same address and just hand it back to Mac OS, Windows, or Linux and say, I'm done with this. You can let me use this for something else later. As an aside, if your computer has ever like frozen or hung, like the whole thing maybe just spontaneously reboots. Yet another reason for a bug like that might be if you write a program with a bug that keeps mallocking, that is asking for more and more and more memory, but you make a mistake and you never free it, well, eventually the computer is going to literally run out of memory and something's going to go wrong, and that's often when computers freeze. Like they're just out of memory. It has the memory there, but the program was trying to use too much of it endlessly. So this too will be a mistake that some of us will surely make in the coming weeks, but hopefully you'll now see the solution. So let me go back to VS Code here, and let me propose that we do the following. I'll hide my terminal window for a moment, and I'm going to introduce another header file up here. And I promise there's not going to be too many more of these, but this one is called standardlib.h for standard library. And in this file are the declarations, the prototypes for malloc and free and a bunch of other stuff as well. It lets me now manage my own memory. So let's focus now on line 11. Line 11 is where I went wrong before, because conceptually I want to copy the whole string, but of course I'm only copying modestly the individual address. So how do I copy the whole darn thing? Well, what I need to do is this. When I declare t to be the address of something in memory, why don't I set t to be the address of a free chunk of memory? So let me ask the operating system, give me this many bytes, tell me what the address is, and I'm going to store that in t initially, just so I know where there's free space for me. So how do I do that? Well, quite simply, I call malloc, and then I pass in the number of bytes that I need. Now, for hi exclamation point, I think I need 3, although wait, no, I really need 4 because of the null character. But I don't think I should be hard coding numbers like this, because who knows what the human's going to type in. So I can actually use strlen of s and then +1. This will ask malloc then for however many bytes corresponds to the number of characters the human typed in, +1 for, again, the null character. So it's just being smart and defensive rather than choosing a number myself. But now all t is a pointer, if you will, to some random chunk of free space. So there's nothing there yet, or there's bits there, but who knows what value they are. They're certainly not identical to what the human typed in. I now have to do this. So how can I copy one string into the other? Well, let me do this. Instead of capitalizing something just yet, let me do this. How about for int I gets 0, I is less than the length of s, and then I++. So I'm going to iterate for the whole length of the string. And in here, I'm just going to do this. The ith character in t should be identical to the ith character in s. So I'm just literally copying from right to left each and every character in s. And I can trust that there's enough memory in ty because I asked for that many bytes +1. Now, there's technically a bug here. I actually should probably do this. I should do +1 here. Or, if you prefer, I should do less than or equal to the strlen. But I think it's a little clearer to do the +1. Why do I, for the first time, want to go just beyond the boundary of s and copy one more byte? Yeah, I need the null character. Like, I could technically manually add it with some additional line of code, but I might as well just copy it because \0 is \0. So this time, and probably only this time, it's reasonable and correct to go just beyond the boundary of your string. So you copy the null terminating character so that the computer also knows where t ends. And now I think what I can do a little more safely is this. Let me go down here and say t_0 equals 2 upper of t bracket 0. So same line of code as before. If I actually want to be really safe, I should probably do this. So if the strlen of t is greater than 0, so there's at least 1 byte there, OK, now it's safe to blindly capitalize the first character. And I think that now puts me in better shape. So let me try this now. Let me open up my terminal, make copy, /copy. I'm going to type in hi exclamation point in all lowercase, crossing my fingers this time. And now if I zoom in, it indeed capitalized only t and not s in this case. So pictorially, let me switch over here. Here is, as before, the variable s pointing at hi in all lowercase. When I call malloc, though, that gives me a chunk of memory that I'm going to store the address in t of. So if t is some other variable, as it is in my code, and there's some other available chunk of memory, I don't know where it is, but let's assume, as always, it's at 0x456, 457, 458, 459, so 4 bytes total. What is now happening? Well, t is defined as pointing to that, because that's what malloc gives us, the address of the first byte of the free memory. And now with my for loop, I'm just iterating over it, copying the h, then the I, then the exclamation point, and then for good measure, the \0 instead. Questions then on this process here? A really good question. If I omitted in my code the +1 and I didn't do less than or equal to, so that I'm copying the 4th byte, odds are in this program, because it's so short, you wouldn't notice that there's an actual error. But what could happen is when I call printf on t, if there's no null byte there, it might print h, I, exclamation point, some random value, some random value, some random value, some random value, until it gets lucky and there happens to be a 0 byte, a null byte by chance, for instance. So if you don't include the \0 some way, that's going to happen. And I say some way, I could even do this. I could technically just copy the length of the string s, and at the very bottom here, I could do something like t bracket strlen of t. I could do this, but this is just not necessary. Like, I could manually add it at the end of the string. But again, I'd claim that it's just simpler to borrow, that is, copy the one that's already in s, because it's the same thing at the end of the day. Good question. Other questions on this copying correctly now? All right, is there any room for improvement here? Well, let me propose a slight optimization. This is kind of a throwback now to week 1. Turns out that arguably my line 13 here, wherein I have this for loop, now that I'm doing things in loops again and again and using a function like strlen, this is correct. It will iterate from 0 on up to the length of s plus 1. But it's kind of stupid of me to write this for loop in this way. Why? Well, here's my initialization on the left. Here's my condition in the middle. And in general, calling a function inside of your condition is probably not very good design. Like, why? Why is it bad for me to be calling a function like strlen in this condition in the middle of my for loop? Yeah. Yeah, you're just calling it again and again for no reason. Like, the length of s never changes. So, like, why are you wasting everyone's time by calling strlen of s again, 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 just to check this inequality, whether I is less than that value? So it turns out, if you haven't discovered this already, there's a slight optimization we can do here that has nothing to do fundamentally with strings or pointers, just with better design. I can actually define 2 variables at once. I could do this. Let me remove this whole condition. And let me add a comma after I equals 0, set n, or any variable, equal to the strlen of s plus 1, and then after the semicolon, just ask the question while I is less than n. So it's almost the same, but notice now my condition in the very middle of this loop is at least comparing 2 static values. N never changes. Sorry, 1 static value. N never changes. All that changes is I. But I'm not foolishly calling strlen again and again. Why? Well, how does strlen work? Similar in spirit to printf, strlen, given the name of a string, looks at the first character and then starts looking through the entire string, looking for the null character. And we saw this in week 2, counting up how many characters are there. So it's just a waste of time again and again.
Do you have to find n all the way at the top so that way you can use n again in the LT?
Totally. If you wanted to use n multiple times, you could absolutely take it out of the for loop, put it right after s is defined, and reuse n and again. Absolutely. But in general, consider this when designing your for loops. Even though modern compilers like Clang can actually fix this problem, this inefficiency for you, good practice would be don't call functions unnecessarily, especially if the answer is always going to be the same. All right, so what else should I perhaps refine here? Well, how about I do one last thing and just comment on what exactly could go wrong here? Well, a couple of things. Well, actually, this is just silly too. Like, surely someone before me in the world has had to copy a string before. Surely there's a function like called strcopy, maybe, like strcompare, like strlen. And indeed there is. So let me propose that we actually get rid of this whole for loop, and we actually just call a function called strcopy, no o, just strcpy, and pass in the destination, which is t first, and then the source that you want to copy into the destination, and that takes the place entirely of that whole loop. So again, I demonstrated the loop first just to be very pedantic about it, but that's wasting time. You're wasting time writing lines of code you don't need to. Strcopy is what you can use here instead. And so this has now always existed. And what more can I do? Well, as one final point, it turns out that there's actually things that can go wrong in this code, even besides the string being too short. Like if the human just hits enter and there are no characters, I don't want to blindly capitalize the first character that doesn't exist. That's why I added that if condition. But there's other things that can go wrong, and we introduced those to you today. It turns out that functions like getString and functions like malloc return potentially a special value. And wonderfully confusingly, it's also called null, but with two L's. All right, so left hand and right hand weren't talking so well like decades ago. NUL is a \0. It's a single character, as it always has been for a couple of weeks now. NULL is technically a pointer. It's an address, but it's address 0. It's like the top left-hand corner, if you will, of your computer's memory that just nothing is ever supposed to go in by convention. So null is a synonym for 0, but it's specifically an address. Now, why is this useful? Well, suppose that in my code here, something goes wrong with getString. Suppose you're being a little crazy and you type in way too long of a string. It's not just hi, but it's like an entire essay of text, and there's not enough memory in the computer. How does getString signal to the programmer, whoa, like that's way too big of a string. I can't fit it in memory. Well, we never told you this, but all of this time, it turns out that getString will return this special value called null if something goes wrong. So to be really careful now, you should do something like this. If s equals literally null, then you better exit the program entirely and return like 1 or 2 or 3 to signify that something went wrong. Don't go any further. Similarly with malloc. It's possible if you ask for way too much memory, that could fail, especially if you're asking now for double the memory after the human types something in. So if t equals null, then you know what? Let's also return 1 or some other value to just get out before something crashes or freezes on the human as well. So honestly, I tend not to do this always in class because the code just gets so bloated and complicated. But you absolutely, in practice, need to start doing this. Otherwise, you will be responsible for the freezes and the crashes and the reboots that users in the real world might actually encounter otherwise. Of course, if we get to the bottom of this program now, I should probably return 0 explicitly or implicitly to just signify that everything is successful. But there's one other thing I haven't done. We introduced malloc, but what did I claim also existed? So free. I'm also being a little reckless now. Here I am not practicing what I'm preaching. I'm asking the computer for memory via getString. I'm asking the computer for more memory via malloc, and I'm never technically handing it back. So really what I should be doing at the very bottom of my program too is freeing the memory I've asked for. So henceforth, it is a rule, a law, if you will, in C. Whenever you allocate memory with malloc, or certain other functions as well, you, the programmer, must free it when you're all done with it. Now, this is a bit of an overstatement because technically when programs quit, they'll free the memory automatically. So you're not going to break someone's Mac or PC because you necessarily have this bug. But for programs that are running all the time, like someone keeps a Chrome, their browser open, Microsoft Word or the like, bad things will happen if over time you never call free and the program keeps running. So always get into this habit here. You do not need to free memory that comes from getString because the CS50 library automatically frees it for you. But you, anytime you use malloc henceforth, as you did or I did here, you must free that by just passing in the same address you got back. Questions now on malloc and free? Questions? Yeah? A really good question. So free so what does free do? So free just lets the computer know that you are done with that chunk of memory, which means that if you have another line of code elsewhere, that same memory might be reused and can be used again and again. And that's going to be necessary, certainly for any long-running program. You can't ask for memory constantly. You'll eventually run out. So you need to free it in this way. Other languages, as an aside, Python, yet another motivation in a couple of weeks for it is going to be Python and certain other languages manage all this headache for you. But in C, the goal here is to really harness these capabilities ourselves. All right, so it turns out like almost everyone in the room, myself included, you're going to screw up when it comes to anything memory related if you haven't already. Seg faults are in your future, but hopefully there's tools via which you can detect these things and fix them proactively and not just use printf or debug 50 or rubber duck. We actually have another tool we can equip you with now that'll help you find some mistakes. So let me do this. Let me close copy.c. Let me open a program I wrote in advance called memory.c that doesn't do anything really interesting, but it's going to have two bugs in it. Notice that I've included standard.io.h, as always. I've also included standard lib.h, which is necessary now for anything related to malloc and or free and the like. line 6. It's a little weird what I've done here, but this is like the manual way of asking for enough memory for an array. In week 2, how do we ask for memory for an array? You very simply say int x3, and that gives you an array called x of size 3. But if you do it manually now using malloc, what you have to do is use syntax like this. You call malloc, you ask for 3 things, times however big an int is. Now we know it's 4, so you could literally write 12 here, but this is more generic. So 3 times the size of an integer will give you 12 dynamically. And what does malloc return? The address of the first byte you get back. What do I want to put that? Well, I want to put it in a variable. Now the variable can't just be int x, because that's a number. It's not an address per se. If I want to store this address in a variable, I could call it x, I could call it p. But int star x just means that x is now the address of a chunk of memory. Specifically, a chunk of memory that's big enough, not for 1, but for 3 ints in total. All right, now I'm just sort of naively putting our old friends 72, 73, and 33 at the first, second, and third locations in memory. But perhaps based on week 2 or week 4, I'm clearly screwing up here in a couple of ways. Someone want to identify at least one bug. What did I do wrong? Yeah, like this is now, amateur stuff. Like I should be 0 indexing, not 1 indexing. So this has got to be 0, 1, 2 ultimately. And other bugs that are maybe more week 4 specific? Other bugs. It's more subtle, yeah. I'm not freeing the memory, right? So I'm not practicing what I'm preaching by freeing this memory. Now, suppose these are non-obvious. And honestly, after like an hour or 2 of this, like this shouldn't be obvious yet. It will be over time. How could I find these bugs with software as opposed to just staring at the thing or asking someone for help? Well, let me propose this. Let me first go ahead and run make memory to compile the program. And it seems to look fine. There's no syntax errors, at least. /memory, notice, seems to work fine, too. Now, this program doesn't do anything interesting. There's no printf or anything like that. But it didn't crash. There's no segmentation fault. But that doesn't mean there aren't bugs latent in the software. And this is true, sadly, of all of today's software, like Chrome and Microsoft Word and other programs surely have memory-related bugs that people at Google and Microsoft haven't yet found. But there are tools, at least to find the most obvious of those bugs. And we're going to introduce you now to a program called Valgrind. So Valgrind, it's a fairly fancy program, but we'll use it for very simple ways. We'll look at your code and find memory errors as it's executing and try to help you understand where they are. So let me go back to VS Code here. Memory seems to be fine. I feel like, OK, I'm going to submit this homework. All is good. No error messages. That's no longer the case. Now you need to poke a little more at your code to see if maybe there's still some bug there. So let me do this. Valgrind. And then space /memory. So just like debug50, you run it on a program you already compiled. Valgrind, I'm going to run it on a program I already compiled. Let me zoom in on my terminal window so we can see more at once, and enter. All right, the output is crazy cryptic for no good reason. There's lots of numbers and equal signs. It's a lot of clutter, but there is some juicy information here. And let me start from the top down. Invalid write of size 4. So write means to change a value. Read means to access a value. And this is, again, esoteric like a lot of our error messages are. But it looks like after a block of size 12 alloc'd, and then there's these weird hex notation, there's some mention of malloc. But honestly, the juicy part here is memory.c, line 6. That's probably my fault. So let's look at line 6 per that output. Let me shrink the terminal window. Look at line 6. OK, 12 is now germane, right? If you did the mental math of the size of an int times 3, 12 is somehow involved here. But line 6 is now happening next here. That's where the memory came from. What is this? Let me zoom back in. Where is there invalid write of size 4? What's perhaps going wrong here? Invalid write of size 4. What does that mean? It's like a very technical way of explaining. The bug is actually one line later on line 7, as we already identified. Yeah. Indeed, and I misspoke a moment ago. The bug actually arises here with line 9. So after the allocation of memory, I'm somehow writing 4 bytes incorrectly. And unfortunately, the onus is kind of on you to sort of think through deductively, what could that mean? But I'm clearly touching 4 bytes of memory in these few lines of code that I shouldn't be. And hopefully here, as the light bulb already went off earlier, oh, I'm not 0 indexing. OK, that must mean that x bracket 3, as you note, is just too far past the chunk of memory. So I'm invalidly writing to 4 bytes that I shouldn't be. So again, it's not super obvious. This is not super user-friendly, but at least it does give you a clue as to where that bug is. So the fix there is going to be quite simply to change the 1 to a 0, the 2 to a 1, and the 3 to a 2. That'll fix that, but there's still a second error. And let me look at the cryptic output again. Heap summary, some stuff there. OK, this does not sound good down here. 12 bytes in one blocks are definitely lost in loss record 1 of 1. Very arcane output 2, but clearly related to line 6 again, our allocation of memory. Now here too, it's not obvious what the solution is, but memory is lost, aka this is a memory leak. And now the deduction's kind of up to you. What is leaking? Oh, wait, I didn't call free. And so the second solution here is probably to free x at the very end of the program. And if you really want to be pedantic, you should probably check, like I proposed earlier, if x is null, just get out now while you still can, and don't even touch those other lines of code. But if you get to the bottom, return 0. But really, the takeaways are, I fixed my 0 indexing of the array to avoid the invalid write of size 4. And now I'm freeing the memory that I asked for. So there should be no leak lost. All right, let's try this again. Make memory, /memory. No visible errors yet. But let me now increase my terminal window again, do valgrind of /memory, crossing my fingers. And now all heap blocks were freed. No leaks are possible. I don't see any invalid writes. There's still a crazy amount of output, but none of it is erroneous. It's not bad. Now I've fixed my memory bugs. And so now my TA, my TF, they're not going to find them either, because at least valgrind has proactively done that for me. Questions then on valgrind? Generally, it's those two types of errors you might trip over. There's not too much else in the way of arcane output. Questions then on this? No? All right. Well, what else might be going on? So someone alluded to this earlier. What happens when you, for instance, forget the null terminator? Or you generally start poking around memory that you yourself didn't ask for, or looking at values you didn't put there? Well, let me go ahead and open this. Code of garbage.c, in honor of Oscar the Grouch here of sorts. And here is a simple program. If I hide my terminal window, that just does something kind of arbitrary. I first declare an array called scores. But I made it crazy big, like 1024. Like that's a lot of integers, but so be it. And then I iterate over those integers, and I print each of those scores out. So I'm using week 2 syntax here. But based on this program, what have I clearly not done that I did do back in week 2? I've allocated the array. I'm printing the array, but. Yeah, I didn't initialize any values for that array. Back in week 2, we didn't do 1024. We did like 3, and I typed in like 3 test scores or something like that. Here, I'm allocating memory, even more than that, just because I really want to be dramatic with what I'm demonstrating. But I'm not initializing those values to anything. And so here it turns out in C, generally, if you do not initialize a variable, or you do not initialize an array with explicit values, there are going to be garbage values there, so to speak. Remnants of that memory having been used before, probably by some other function of yours, some library function, or something else while your program is running. Not a huge deal with a super small program like this, but for anything sizable, memory is going to be used and unused and used and unused. That is mallocked and freed again and again. There's going to be lots of garbage values in the computer's memory by default. So if I open my terminal window here, let me do make garbage. Let me zoom in on my terminal so we can see the output. When I run /garbage, theoretically, I should see 1,024 integers, but none of which have been initialized. Now, I'm going to get lucky with some of them. And it looks like, wow, OK, a lot of them are initialized to 0. And C does, in some contexts, initialize memory for you to 0, at least at the beginning, but not again and again typically. But if I start scrolling backwards in time at this array of size 1024, where did these values come from? So just random positive and negative numbers interspersed among the zeros? Well, that's because I'm literally poking around on a random 1,024 bytes of the computer's memory. Who knows what's there? So the lesson here is that garbage values are indeed this like term of art. It means that a variable that you might have defined, that you might have declared, if you don't give it an explicit value, who knows what's going to be there? And the lesson here is just don't do that. Always initialize variables to something, either yourself or prompting the human for it. Questions about garbage values? You'll see them sometimes if you print things you shouldn't or touch arrays beyond their boundaries. All right, so maybe to make this a little visual too, it turns out that a lot of things can go wrong, unfortunately, with pointers, and we've seen some of them. And here's another program that's a little contrived. It's very simple, and it just is about manipulating values. It doesn't do anything useful per se, except demonstrate some of today's concepts. So in main here, let me propose that we declare a pointer called x that's going to store eventually the address of an integer, apparently. Here's another one called y that's going to store the address of an integer as well. Here now, I'm allocating enough memory to fit one integer. Now, technically, it's 4. We know that. But size of int just gives me that answer dynamically. So it will work on all systems. And I'm going to store the address that malloc finds for me in x. Then I go to x and put the number 42 there. All right, why? It's the sort of meaning of life, the universe, and everything here. But star x, again, just means go to that address and put a value there. So why? I don't know. But it's just correct at this point. But what about this line here? Star y equals 13. Unlucky in this case. What's bad about this line here, star y? It's a combination now of today's primitives and that point here. Yeah? Yeah, we didn't ask the computer to allocate any space, so y was not initialized with an equal sign at any point to anything. And so what is inside y, so to speak? Like a garbage value. Maybe it's 0, which isn't bad because at least it's nice and simple. But maybe it's some crazy large positive number, some crazy large negative number. Either way, odds are if I go to this address or that address randomly with star y, bad things are going to happen. And so let me go ahead and propose, well, let's not do that. Let's actually do this instead. Assign y equal to x. And we've done that before. And then I can go to y now and change what was a 42 to a 13. Again, why? This is just for educational sake. But for now, this does not crash, because I only dereference y with star y after actually giving it a value, albeit a duplicate value, similar to our copy example earlier. So our friends at Stanford have put together a wonderful visual. It's about 2 minutes long. Allow me to dramatically dim the lights if we could and play with what happens with memory when you do bad things like this.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers? Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay. Well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay. Here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So are we going to switch places now? Oh, look, we're out of time. But
Our thanks to Professor Nick Parlante of Stanford for spending a huge amount of time doing stop motion animation for that. But hopefully now you have a sense of what too can go wrong when you misuse memory in this way. But at the end of the day, we really only have these 4 new building blocks today, like the star operator, the ampersand operator, malloc, and free. And really with that and the underlying understanding of what your computer is doing underneath the hood, we have this way now to really manipulate things in memory, for better or for worse, and eventually we'll see how we can build things. But we can also now use today's primitives to better explain some things that we've been asking you to take for granted over the past several weeks. So for instance, let me propose that we do a one volunteer up here if we could. Could we get one volunteer who's just, you want to come straight up? Yep, right in the middle. Come on. You'll have to take a left or a right there. All right, so we have 2 empty glasses here and 2 colors of liquid. And we have, let me give you the mic, if you'd like to say hello to the group.
Hello, I'm Moeen. I'm in Thayer and first year.
All right, welcome. Well, welcome here. I'm going to go ahead and fill these 2 glasses with this colored liquid, purple here on my right. Let's fill up a glass here. Yes, don't drink. And now we'll put some orange in here. And what we'd like you to do for the audience, if you don't mind, is swap the 2 values. We've got a purple value and an orange value, and I'd like the purple liquid in this glass and the orange liquid in that glass, please. Oh, OK, good intuition, but for the microphone.
Can I have another glass?
So you can, and just in fact, I brought one here for you. Why are you asking for this, though?
Because if I just pour this into this, then it'll get mixed up.
Right, so obviously we need like a temporary variable, if you will. So here's your temporary variable.
And you want,
Yeah. All right, so pouring the value of the orange glass into this temporary variable, if you will. All right, and now pouring the value of the purple glass into the former orange glass. And now the temporary value goes back into the original purple glass. And now I think we give you a round of applause for having done that very well. Okay. Thank you. All right, so it should go without saying that in the real world, like that's how you do this. And in fact, in code, that's pretty much how you have to do this. Although, ask us sometime for a super fancy way of doing it without a temporary variable. Turns out that is possible using bits. But for now, let's suppose that indeed this demonstrates what is the reality in code. If you want to swap 2 values, you need to have something like a temporary variable. So for instance, on the screen here is the beginning of a function called swap, whose purpose in life is to, as you just did, swap 2 values, call it a and b. So orange and purple, respectively, are now just a and b in integers to keep things simple. Well, here is the corresponding code, if I may, to what you just enacted as a human. You declared a temporary variable called temp in this case, which was like me handing you the empty glass, and you stored the orange liquid in it, aka a. You then changed the value of the formerly orange glass to be equal to the purple by pouring one into the other, and then you did the opposite there. Now at the end of this, you still have a temporary variable that's now empty, so it's temporary in literally that sense. Like you just don't need it anymore, but it was necessary along the way. So I dare say this code is correct logically. Like this will swap 2 values, a and b, thanks to the use of that temporary variable. Unfortunately, though, if I actually do this in practice, let me go over to VS Code here and open a program I wrote in advance called swap.c, which does this as follows. In here, notice I have my prototype for a swap function at the very top. And let me scroll down to the very bottom. There's that exact same code. So I'm the same code for swapping 2 values, a and b, which I'm claiming for now is correct. Now, if I go back up here, what is main going to do for us? Main is really just meant to be a demonstration of the correctness of your algorithm. So here I declare on line 7 and 8 2 variables, x and y, being 1 and 2 arbitrarily, respectively. I then on line 10 just print out what the value of x is and y is, just so I can see it on the screen. I then call the swap function on line 11, and then I literally print the exact same thing again. I print x and y. Hopefully, it'll obviously be the opposite. So I think logically swap is indeed correct. Let me do make swap and then /swap, and I should see x is 1, y is 2, and then hopefully x is 2, y is 1. Enter. But I don't. And it did work in the sense that the code compiled, the code ran. So it's not like some bug in that sense. But because I don't quite understand what's going on underneath the hood, at least as of right now or prior weeks, this code here is indeed buggy in some way. But does anyone have an intuition, perhaps based on today's discussion, as to like why this code, while logically correct, clearly works in reality, apparently does not work in C? Any intuition? Yeah. Perfect. And to summarize, here's that term of art I promised. When you call a function and pass in two arguments, like a and b, you're passing those arguments by value. So copies of those values effectively. And so when swap is actually called here, when you pass in x and y, we call them a and b, but that's just a convention. We could call the parameters anything we want. What a and b are indeed the values of x and y respectively, but copies of the values. So this code here is very successfully in VS Code 2 swapping the values of a and b. But as you note, because I'm passing them in by value, literally 1, literally 2, and not by another term of art, by reference, aka by their addresses, swap has no capability in C to go to those locations, swap the actual locations, just like we did successfully in reality. But I think we really have the syntax already for solving this if we consider that really this is just an issue of scope. And we've talked a bit about scope in the past, whereby scope refers to the context in which a variable lives. And generally, I've claimed that a variable exists between the most recent curly braces. And that's pretty much true for the swap function, because a and b, I now claim again, exist only in the context of these curly braces. They have no effect on main up top, which has different variables, x and y. But we can consider now what's really going on underneath the hood. And here's that same picture of memory as we've seen in the past. If we zoom in and see on these little black chips, this is a bunch of bytes of memory. If I create a grid out of it just to kind of highlight that we can address each of these bytes, throw away the plastic circuit board and focus only on those bytes, what's going on underneath the hood when functions are called in C, which you've been doing for weeks now? Well, this rectangle of memory, if we kind of abstract it away further, is generally broken up into different regions or segments, like I called them earlier, and different things get put in different parts of the computer's memory. And without getting too into the weeds, when you double click a program on your Mac or PC, or when you do /something on a Linux, you are loading your machine code into the computer's memory from the computer's hard drive. So all the zeros and ones that compose Microsoft Word or Chrome or whatever are loaded into the computer's memory or RAM. And by convention, it's put up top in the so-called machine code area. And that's how the CPU has access to them quickly at that. Below that are what are going to be our globals, so global variables, which we haven't used very much in C, but you can declare them outside of main at the very top of your files. If you have globals, they end up there as well, just FYI. And then there's this big chunk of memory that we saw Valgrind mention indirectly earlier called the heap. And it's kind of like heap, literally, like it's a heap of memory that you can use as you see fit. And the heap is where malloc grabs memory from. So initially, there's nothing in the heap. It's just a big chunk of free space. Anytime you call malloc, malloc kind of carves out from the heap area more and more bytes. And malloc keeps track of essentially which bytes have already been allocated. So initially, it looks empty, but different bytes, squares, if you will, keep getting requested again and again as a program runs, thanks to functions like malloc. And it grows, if you will, conceptually down. So the more and more memory you request from malloc, it starts up here, but then the next chunk you get is down here conceptually. The next chunk is down here, down here. So it kind of fills the available space in the computer's overall memory. But there's this other chunk of memory called the stack. And just like a stack of trays in like Annenberg or a cafeteria kind of grow upward, so does the stack of memory. And it turns out the stack is where functions have variables and have arguments stored temporarily. So whenever you call a function and it has variables inside of it or has arguments there too, this is the chunk of memory in the computer's overall block of memory that are used for functions. But anytime you call malloc, it's memory up here. Right? At the end of the day, they just had to pick a direction, top, bottom, and technically it's an artist rendition. You could circle this thing around any orientation you want, but you're just using a finite amount of memory in this conventional way. Malloc starts here, functions start here. Now you can kind of see where like bad things can happen. And indeed, one of the other reasons computers can crash is if you ask for way too much memory from the heap by calling malloc many, many, many times, or if you call way too many functions, or accidentally, per last week, you recurse infinitely many times, you might have a segmentation fault. And that's because you're using too much stack memory. So this is bound to be a problem eventually. And the onus is on the programmer to just minimize the probability of doing that and really avoid the possibility of doing that by just checking return values, like checking if malloc or getString return null, because you can proactively with conditionals make sure that these two things do not collide by just making sure that you get back non-null values. So let's consider the stack in the context of swap and what's really happening here. And Carter, if you wouldn't mind helping me animate the screen here, when I call the main function of any program, it is allocated a slice of memory called a frame at the bottom of this stack. So if Carter, you want to go ahead and advance here, here's like the first slice of memory that will always be used by main, whether it has command line arguments or local variables. It just ends up here in memory. Suppose now, per our swap.c program, that main calls swap. Well, where does the memory for swap end up? Like right up here. So swap had two arguments, a and b, and it also had a temporary variable. So all of those end up in here in memory. And if you want to go ahead and advance again, Carter, once swap is done executing, whether it just returns because there's no more lines of code, or you explicitly return, this memory is just freed up automatically. You don't call free, you don't undo malloc. This just all happens automatically. It has been since week 1. Now, technically, it's still there, even though we've removed it from the picture. And there's your first hint of garbage values, right? Like there's still zeros and ones there, and they're left in the previous configuration. And so the reason you get random values in the memory is because even though we haven't drawn swap here, there was stuff there a moment ago. It's going to be there the next time you use that same memory. Now, let's go ahead and step through this a little more methodically. Main has two variables called x and y, 1 and 2. So let's advance and represent x as 1, y is 2, taking up these two chunks of memory. When we call swap now, swap gets a new slice of memory that then gives us 3 variables, a and b, technically the arguments, and temp. So what happens? Well, because functions automatically pass in values by value, or rather pass in arguments by value, x gets copied into a, y gets copied into b, and then once we start executing the algorithm a la the watered glasses, well, what happens here? So if I execute the first line of code, temp equals a, temp gets a copy of a. What happens next? A equals b. So a takes on a copy of b. And now we do the final swap in the glasses. B equals temp. B gets a copy of temp. Now, we don't have to change temp because it's essentially empty, although there's the garbage value. 1 is always now going to be there until we reuse that memory. The important thing, though, is that a and b have been swapped. But what obviously has not been swapped, as is manifest, is when swap returns, x and y are untouched because copies thereof were passed in. So we need a solution to this problem. And if we advance one more time, if you don't mind, let me step over here, but then call you back in a second. This code here is logically correct. This is what you did, but this is now a detail of C. You can't just swap the things by value because you're only changing it in the scope of the swap function. But I think if we change it to this and add some annoying syntax, we can solve the problem. Just like you can declare variables as storing addresses, you can declare arguments to functions, aka parameters, as taking addresses. This new version of swap means that a shall be the address of an integer. B shall be the address of an integer. And now it gets a little cryptic here. Temp is the same because it's just an integer like it was in week 1. Nothing special about temp. But if you want to get the value at a, you do star a. And that goes to the address, grabs the number 1, presumably. If you want to change the value of a, you go to that address, you follow the treasure map to the other mailbox, and you set it equal to whatever's at the value of b. You go to b as well. Last line, you go to b now and change it to be whatever the temporary variable was, which happened to be the same as a. So that's where the final value gets swapped. But here, there's a lot more like crisscrossing metaphorically across the stage where you're going to all of these different addresses in the swap function to make these changes. So if we advance now to the pictorial version of this, here's the same story as before with main. And x and y are 1 and 2 respectively. When swap gets called now, notice, and I'll do it with arrows here, a is effectively pointing to x, b is effectively pointing to y. If we really get into the weeds, these are actually like addresses, but who cares about the specifics? It's really just the concept here. So now what happens? Int temp gets star a. Star a means start at a and go there. Follow the arrow, if you will, sort of shoots and ladders style. And then that's 1, so we put 1 in temp. All right, star A equals star B. So let's do it from right to left. Star B means follow the arrow. It's 2. And then what do? Follow the arrow. It's now 2 because you copy one to the other from right to left. And then lastly, star B gets temp. So start at B, go to B, and now store whatever the value is in temp. So just by having this basic new syntax of like ampersands and stars and so forth, we can actually now go to places and circumvent what is otherwise a feature of C, that these variables are locally scoped, but you can still access things in other functions as well. So thank you so much for helping step through this. So we now have an application of this that explains why now in this version of the C code, this would actually now work. So in fact, let me go back to my swap code here. And let me change the function ever so slightly in VS Code. So let me scroll down, leaving main the same. And let me change swap's prototype to taking in addresses. Let me go to A here. Let me go to A here. Let me go to B here. And let me go to B here as well. But nothing else changes. This change here in particular is enough of a clue to see that means when you call swap and pass in 2 values, I'm expecting addresses now, not integers. But now that I've made this change, I do need to go up to main and make one change. Does anyone have the intuition for what now needs change in main so that I pass in x and y by reference, that is by address, rather than by value or copy? Oh, yeah, in back? So close. So on the swap line, it's not star that I want in front of the x and the y. It's instead, what's the other one? It's the ampersand. Why? Because if I want to enable swap to go somewhere, just like Carter and I played this game with the mailboxes, I need to inform swap of the address of x and the address of y. And again, per the beginning of today's class, ampersand is the syntax via which we do that. So I add an ampersand here to get the address of x, ampersand here to get the address of y. And now this code lines up with the picture that Carter just helped us walk through. And so when I run make swap here, I have a mistake. Oh, what did I do wrong? Not intentional, but I guess worth pointing out. I screwed up here. It doesn't like ampersand x because of something on line 3, which is way early in the code. What did I screw up? Yeah, in the middle? Yeah, so this is why you should not copy paste, even though it's necessary for things like function prototypes. If I change swap at the bottom, I need to change its prototype. So let me add the star there, or just recopy paste it at the top of the file. Now let me do make swap again. Let me now do /swap, and I should now see x is 1, y is 2, and hopefully x is 2, y is 1, which I now do. So the logic is the same. The algorithm is the same. All the week 0 stuff is the same, except now in week 4, you just have a bit more expressiveness via which you can tell the computer exactly what you want to manipulate and how. Any questions then on this technique here? No? All right. Well, when we fix this, there's still going to be problems. And just so you've seen some terms of art here, this is bad whenever you have 2 arrows pointing at one another. Certainly if you might use and reuse more and more memory. And it turns out there's some terms of art that might suddenly now make sense, especially if you've programmed before. Bad things can happen by this design, but there's really only this kind of design because it's a finite amount of memory. So at some point, bad things are going to happen no matter what if a computer runs out of memory. So it's not that this was a poor decision. It's just sort of a necessary one given finite amounts of memory in a computer. But a heap overflow, so to speak, is when you actually overflow the heap and touch memory that you shouldn't up there. Stack overflow is when you somehow overflow the stack and touch memory that you shouldn't down there. So with that said, these are really just problems that can happen, and they're specific incarnations of what are generally called buffer overflows. A buffer, like in the YouTube sense, is just like a chunk of memory that in the case of YouTube stores like the next few seconds or minutes of video. But generally speaking, a buffer is just a chunk of memory that the computer is using for some purpose, be it the stack, be it the heap, be it an array in the computer. And so buffer overflows are what happens when you just have logical bugs in your code. But with these primitives now in mind, we wanted to conclude with the final revelations. And that's how some functions like these here work. The other thing in the CS50 library, besides the typedef for quote-unquote string, is, of course, all of these functions. And we give you these functions because, honestly, in C, it is hard, it's annoying, it's painful, it's difficult to get user input correctly. It's very easy when you don't know how much the human's going to type to write buggy code when it comes to it. And indeed, it's really hard to store it correctly without accidentally having some kind of buffer overflow. So for instance, let me show you a program here. I'm going to go ahead and write this one from scratch. So let me go ahead and open a file called get.c, wherein I'm going to go ahead and mimic the idea of getting integers manually without the CS50 library. So I'm going to include standard io.h only. I'm going to define main as not taking any command line arguments. And then I'm going to do something like this. Give me a variable x with no value yet. And normally, I would do something like getInt. But let me take that away. No more training wheels for getInt either. So let me just define the int x. Let me then just print out something like a prompt. And I'll just do x colon just to make it obvious to the human what we're waiting for. And now I'm going to use a built-in C function to get user input. I'm going to call a function called scanf, which sort of scans the user's keyboard for input. I'm going to scan it for an integer. So just like printf, I'm going to use %i because I expect an int. And then I want to tell scanf where to put the human's integer from the keyboard. It is not correct, though, to say x. Because if I say x, I run into the same swap problem. Scanf, no function, can change the value of x unless I pass it not by value, but by reference. So we're back to our ampersand friend. And now it has like a treasure map to the actual location of x and can therefore change it. And so now at the very end of this program, let me do something simple. Like let's just go ahead and print out with printf the value of x using %i as always, plugging in x. Not ampersand x. This is now week 1 stuff. I want to print the actual integer value of x. So the only change here is that instead of using getInt, I'm now using this new function that as of today exists called scanf. So let me go ahead and run get, make get to create this program, /get, and let's go ahead and type in a value for x, 50, enter. And it just works. So it turns out getInt is pretty simple to implement. However, notice what does not work. If I type in cat, for instance, cat gets converted to 0. And meanwhile, getInt, recall, will reprompt the user. If a human does not type an actual integer, you get automatically reprompted. So that's one of the features we, for CS50, added to getInt just to make your programs more user-friendly. But otherwise, getInt is pretty straightforward to re-implement using scanf. Unfortunately, that's not true for strings. Because how do you know when you write your code what word the human's going to eventually type in, how long their greeting, like hi, is, if their name is David or Carter or anything else? You just don't know in advance how much memory you need. So how might we do this with strings? Well, let me go ahead and declare a string s. Although, you know what? There's no CS50 library, so we do char star s today instead. And that gives me not a string per se, but a pointer that will point presumably to a string. Ideally, I would use this, get string. But again, we've taken that training wheel away. So now that I have a pointer s, suppose I prompt the human for a value for s, just like before. Let me use scanf now and tell the user that I expect to read a string, %s from the keyboard, and store it in s. Now, this is subtle. I don't technically need an ampersand here, even though I did for an int, and I would for a float, and a double, and a long, and a bool, and a char. Why do I not need an ampersand in this story to pass by reference? Because s it's already an address. Again, strings are just special. Strings now are always addresses, so you don't need to additionally add an ampersand here. That's the only subtle difference here. But now if I go ahead and print out at the very end what the value of s is, using %s as before, this program looks like it's almost the same as the int version. But let's do make get. And OK, so this is not good. All right, so it doesn't like an uninitialized value. So let me make it happy. I said earlier to always initialize my variable. So let's initialize it to null so that at least something is there. That's your good default value nowadays. Now if I do /get, now we're good. And let me type in something like cat. OK, cat is not x. Well, let me try another word. Maybe it's just cat is wrong. Dog. OK, let me try David. It just doesn't seem to be working. Moreover, it's printing it as a 0. What logically, though, is the bug here? Scanf worked a moment ago for integers, but it's not working for strings. And it seems to be forgetting CAT. It's forgetting DOG. It's forgetting DAVID. Why? What's happening here? Think back to our yellow pictures of memory. When yeah. It might be reading just the null itself because s is being initialized to null. And what step have I forgotten from just like a few minutes ago? What did I not actually request of the computer? like actual memory to store the CAT, the DOG, the DAVID, right? There's nowhere have I asked the computer for some amount of memory. And so technically, it might be reading it into some garbage location. And that's really the problem here. S is initialized to null now. And so in fact, it is printing 0 as null. But I'm not seeing any of the other letters because there was nowhere to put them. CAT, DOG, DAVID, because I didn't ask for 3 bytes, 4 bytes, 5 bytes, 100 bytes. There's no use of malloc. There's no use of an array. There's no memory allocated for anything other than the pointer itself. And this is where, honestly, life gets hard with scanf. Like, I could solve this problem in a couple of ways. Let me go ahead and do this. Instead of declaring S to be a pointer, let me declare S to actually be an array of 4 chars. And now, let me go ahead and recompile the code. So make get /get, and I'll type in cat now. That now works. Why? Well, I'm allocating an explicit array of size 4, enough for a 1, 2, 3 letters plus a null character. Here's where, to someone's question earlier, it turns out that in some context, you can treat arrays as though they are pointers themselves. C will sort of do the conversion for you. But for now, just assume that S is just an array of size 4. And if you pass it into scanf, that's like a treasure map that leads to those 4 bytes. So scanf can now successfully fill it with CAT, DOG, but let's try this again. Let's type in David. And here, OK, we got lucky, but I technically touched memory that I should not. And in fact, if I typed in a long enough string, and I don't think I could do it very easily, like without typing this thousands or hundreds of times, still OK. But you'll notice that it's forgotten the rest of it now. Right? So somewhere we went beyond the boundary of the array, and we just don't have enough storage space for that entire thing. So what do you do in your program? If you don't know how long the person's name or the animal name is going to be, what do? 40, 400, 4,000, 40,000? Like, at some point, you have to draw a line in the sand. And that's why, like, getting user input is so annoying in a language like C. And that's why getString exists. What we do, if you're curious, is we look at the user's input, and we take baby steps. We look at it 1 character at a time. And every time we see another character, we actually call malloc again and say, no, I need more than 1 byte. I need 2. Oh, wait, they typed in 3 letters. I need 3 instead of 2. Oh, I need 4 instead of 2. And we have this crazy loop, essentially, that keeps asking for more and more memory, but by taking baby steps. And honestly, if you all had to do that in week 1, my God, like, we couldn't even write hello world anymore. And so that's why these training wheels exist, at least early on. And that's why in higher level languages, like in Python, you don't have to do this at all. It just works as you'd expect. So what more can we do? Well, you'll see in problem set 4 this coming week, if I open up an example like this, phonebook.c, you'll see that you can manipulate files now that you have a vocabulary for pointers. It's going to be new quickly, but here we have an example of how I have a program using some familiar libraries here. But as I claim in my comment, this saves names and numbers to a CSV file. All of my examples thus far, I type in some words, I type in some names and some phone numbers, and they disappear because we only store them in memory. But if you want to store data in like a CSV file, comma, separated values, which is like a simple spreadsheet, like Excel and Apple Numbers and Google Sheets can open, you can actually do this yourself. So just as a teaser for this week, here on line 9, I'm using a new data type, not a CS50 thing. This is a C thing called file. But if you want to manipulate files, you need to use addresses, that is pointers. So here is me creating a variable called file that's going to point to an actual file on the hard drive, on the server or your Mac or PC. fopen is going to be a new function you'll use that will open a file. And it will return effectively a pointer thereto in memory. The file name I want to open is phonebook.csv. And in this example, it's going to be append mode. It will keep allowing me to add more and more names and numbers to this file. Here's some old getString stuff, because I'm not going to reinvent getString with scanf. But down here is a slightly new function. It's not printf, but fprintf. And it turns out it's very easy to print things not to the screen, but to a file with fprintf. And it takes an additional argument. Instead of starting with the quoted string, you'll have to like say what file you want to write to. And fprintf will figure out how to get the bits into that file, passing in something like name, comma, number. So if I run this somewhat quickly here, let me do this. Let me pre-create a file called phonebook.csv. And in phonebook.csv, I'm going to create a temporary row here, name, comma, number, just so that there's something in this file. And now let me go ahead and do this and split my screen here. If I have phonebook.csv on the right and phonebook.c on the left, let me compile, make phonebook, which is the C version, /phonebook. And now I'm prompted for a name and a number. So I'll type in David. And then, for instance, +1 949, what is it, 468 2750. enter. Oh, damn it. Bug. Pretend that didn't happen. I forgot to hit enter in the file. So let's do this again. If I run the program again, David, and +1 9494682 2750, enter, it's been saved now to the file. And if I close this file and I reopen code of phonebook.csv, you'll see that the file is persisting. And if I downloaded this to my Mac or my PC, I could double click the CSV file and voila, Excel would open up, or Apple Numbers or the like. And I've actually created an actual CSV file. If you're smiling because I keep repeating my phone number out loud, I would encourage you to call or text that number sometime. It might very well be an Easter egg of sorts. But via these functions here, do we have now the ability to write files, input and output. And among the goals then for this week, as we'll see, are to actually play with images in the spirit of something like Instagram filters or the like. And we'll introduce you, for instance, to a file format called BMPs, which, to come full circle to the start of class, are just maps of bits, but more than just single bits for white and black, but rather colorful patterns as well. And we'll give you images like this of the Weeks Bridge here across the river at Harvard. And you've run, after writing your own code in C and understanding how the data is stored in the computer's memory, you'll be able to apply your own Instagram-like filters to make things grayscale instead, or sepia in this case. You can even flip the bits around so that the thing is a mirror image. You can blur things further, or if you really are feeling more comfortable, you can even write code that finds the edges of the image and creates works of art like these. So all that and more in problem set 4. We will see you next time. This is CS50, and this is week 5, which is going to be our last week in C. But what that means is that we'll have, OK. But with this week, with last week, and really all of the weeks prior, have you been hopefully acquiring, if slowly and with some challenge, like some fundamental building blocks that are still going to underlie everything we continue doing in the semester, even as we transition to so-called higher level languages. Next week, indeed, we'll introduce Python, a very popular language that does not have pointers, does not have memory management at this very low level, but that's really just because someone else wrote the code that will do that for you, and it's going to make our lives easier because it means when you want to solve a problem conceptually up here to just get real work done or build something amazing, you don't have to really get into the same weeds as we have been deliberately this week and now last. But the goal ultimately is that you better understand and can better harness then all that a computer can do, even in those higher level languages. So today we're going to focus particularly on data structures, how you might structure your data in memory, which really amounts to building things digitally, stitching together ideas and concepts in memory using this new building block from last week, which of course are these pointers. Pointers allow you to store addresses in memory, like in variables. But with those simple addresses, we can sort of leave these breadcrumbs. We can point from here to there, and we can conceptually stitch pieces of data together. But there's going to be different ways of doing that. And today we'll focus first on what's generally known as an abstract data type. And similar to a type in C more generally, it does actually have some properties in it, but the underlying implementation details of an abstract data type are ultimately up to you. That is to say, an abstract data type can represent one thing and can do something, but how you implement it allows you some discretion underneath the hood. So for instance, in the world of computer science, a queue is actually a technical term. This is a type of data structure that we could theoretically build in code in C or really any other language. But a queue has properties just like queues in the real world. For instance, if you've ever lined up for something to get food in a restaurant, or go into a store, or wait for the airport to clear you, well, you've lined up in a queue being some sort of line. But what's noteworthy about queues are specific properties. They are first in, first out data structures, either virtually or in the human world, which is to say the first person in the line should ideally be served first at the restaurant, or the first person in the line should get through airport security first. By contrast, if it weren't first in, first out, you can imagine how frustrated you would be if you have this sort of inherent unfairness. In fact, if you've ever been in line at a store, a supermarket, or the like, and all of a sudden they maybe open a new line, and now the person behind you gets to kind of cut ahead and go forward, that's because they've broken the concept of the cube. So it has this inherent potential for unfairness unless you maintain this first in, first out property. This would be true, too, for like a to-do list, just for productivity's sake. If you're in the habit on paper or virtually making a to-do list, ideally, you probably want to go through that list top to bottom so that you actually get the first stuff you thought of done first, rather than always focusing on your most recent thought. Now, within the world of queues, there's generally two operations, two functions, if you will, that any queue would have, either in the real world or in the virtual. Enqueue is usually the technical term to mean adding something to a queue. But specifically, it means adding it to the end of the queue so that someone isn't cutting in line, for instance, to go up front. And then dequeue is just the opposite. When it's time for the first person in line to be served, the time for the first person in line to go through security, they are dequeued, so to speak. So a technical concept ultimately as it's implemented in code, but it's really just a real world concept. And these are in contrast to another abstract data type that we might call a stack. And a stack, much like a stack of trays in the cafeteria, has sort of fundamentally different properties. You can still add and remove things from them, but consider what happens. Whenever they clean all of the trays in the cafeteria or the dining hall, they put one of the trays down here, and then the next one on top of it, and then the next one on top of it, and so forth. But of course, which tray do you presumably take as a user of that physical stack? The top one, presumably, right? Like you're not going to futz down here and try to pull one out. And so that would seem to have an opposite property. LIFO, last in, first out, is what characterizes something like a stack. And that just makes sense, certainly in the physical world, of stacking all of those cafeteria trays, because it just makes more sense to grab the most recently added one, the last added one, first. And at least in that context, the trays don't necessarily care what order they're used in. But even then, you could imagine that maybe there's some old, dirty, nasty tray at the very bottom that like never gets used because you're constantly replenishing the stack. So there might very well be side effects of these kinds of features. You might be familiar with using Gmail, for instance, or really any email program. What you're looking at in your inbox is technically a stack, at least if you've left the defaults configured. Why? You get a new email. Where does it end up? Not like 5 pages of emails later, presumably right at the top, and the next one's right at the top, right at the top, right at the top. And so if you're like me, you're guilty of eventually losing track of some emails. Why? Because you've pushed so many more emails onto the stack that you sort of lose track of the things you got earliest. Last in, first out, though, is maintained. The most recent email you get might very well be the first one you reply to, but that's not necessarily good for responsiveness to everyone else out there. Similarly, if you store like all of your sweaters in a stack like this, like a pile of black ones below which is a red and then a blue, stack might be perfectly fine for keeping things organized. It's sort of the sane way to do it if you just have a shelf in your dorm room or home. But what's going to be a side effect of using a stack to store your sweaters if they're these in this way, as opposed to a queue? Yeah? It's harder to get the red and blue one. So presumably, you're going to much more often wear, for instance, if you will, black instead there. Now, the operations for adding things to a stack are similar in spirit, but just different vocabulary. You push something on top of a stack. even though it's more like in the tray world, you sort of place it or rest it. But pushing means adding something to the top of the stack, and popping means removing something also from the top of the stack. So it's not a matter of enqueuing at the end and dequeuing at the beginning. With a stack, everything's happening on top. You're pushing onto the top and then popping off of the top. Now, when it comes to actual code, how might we implement something like this? Well, let's just focus on really how you might implement the data structure itself, and we won't implement any functions. You might implement the notion of a stack like this. We've seen typedef before. It just means define a new type of my own. Struct means here comes a structure, aka a data structure of one or more variables within. And let's suppose, like last time we defined already like a person data type using a separate typedef, and every person has like a name and a number or whatever. Let me just stipulate that person exists already. So here you might have, to implement a stack, an array called people of some capacity. Maybe it's an array of size 10 or 100 or whatever. This is a constant here in this context, capacity. And every element in that array is a person structure. And I now have this too, size. Now this almost seems like a synonym for capacity, but maybe intuitively, anyone want to propose why I'm apparently maintaining separately the capacity of the stack, but also the size of the stack? Why these two distinctions here? Yeah.
Capacity is how high the stack could be.
Yeah.
Size is how high it actually is right now.
Perfect. The capacity is how high the stack could be, like how much room is there for those sweatshirts in my closet, for instance, whereas size is just literally at this moment in time how many sweatshirts are in the stack. It's either capacity or fewer, presumably, in total there. So what is capacity? Well, we could implement this in, perhaps a familiar way. I might just define a const somewhere else in my code of type int that just defines it to be capacity 50. But what perhaps is going to be the downside of implementing a stack in this way, of using an array inside here? Like, what's a downside now of implementing a stack using an array and this size variable within? What's a caveat here, perhaps? Any hands? Yeah. OK, so it's going to be harder to reach elements that aren't the last one. That is the most recently added one. So there could be some sweatshirts, so to speak, way down below. So we've seen that before, too. But at some point, too, a limitation of this design is what it's going to be finite, right? I can maximally fit, in this example, 50 sweatshirts or 50 emails or 50 cafeteria trays, which is fine. But at least it's indeed finite. And at least in the computer's memory, it might be nice to use more and more and more, maybe as more things are getting added to the computer. So maybe I make this 500, or heck, why don't I make it 5,000 or 50,000? Well, what's the trade-off there? If I want to have enough room to grow, it seems like I should just crank up the value of capacity endlessly. But why might I not want to change the 50 to 500 or 5,000 or 50,000? What's the trade-off there, perhaps, just intuitively? Yeah. OK, you don't want to touch memory that you're not supposed to be touching. And in this case, that wouldn't be a risk per se, unless you indeed overflow the stack. But there's a related issue in asking for that much memory. What would another downside be? Yeah, OK, exactly. So if you've got a capacity of 5,000, but you're only using one of those elements, it's awkward, to say it non-technically, which is just to say very, very wasteful, right? That's just bad design. It's correct. It will work for up to 5,000 elements. But my gosh, you're wasting 4,999 extra spots. And that's not going to end well, especially if you're using more data structures in memory. Like your Mac, your PC, your phone is surely going to run out of memory if you ask for that much. So it'd be nice if there was a bit more dynamism there, whether it's a stack or a queue, both of which might be implemented a little similarly in spirit. But let's conclude this abstraction by comparing, thanks to a friend of ours, Professor Shannon Duvall of Elon University, who kindly put together this graphical animation that's just under 2 minutes long that paints a picture of these two types of abstract data structures. And then we'll dive in underneath to how we might implement problems like these. If we could dim the lights dramatically.
Once upon a time, there was a guy named Jack. When it came to making friends, Jack did not have the knack. So Jack went to talk to the most popular guy he knew. He went up to Lou and asked, "What do I do?" Lou saw that his friend was really distressed. "Well," Lou began, "just look how you're dressed. Don't you have any clothes with a different look?" Yes, said Jack, I sure do. Come to my house and I'll show them to you. So they went off to Jack's, and Jack showed Lou the box, where he kept all his shirts and his pants and his socks. Lou said, I see you have all your clothes in a pile. Why don't you wear some others once in a while? Jack said, well, when I remove clothes and socks, I wash them and put them away in the box. Then comes the next morning, and up I hop. I go to the box and get my clothes off the top. Lou quickly realized the problem with Jack. He kept clothes, CDs, and books in a stack. When he reached for something to read or to wear, he chose the top book or underwear. Then when he was done, he would put it right back. Back it would go on top of the stack. I know the solution, said a triumphant Lou. You need to learn to start using a cue. Lou took Jack's clothes and hung them in a closet, and when he had emptied the box, he just tossed it. Then he said, now Jack, at the end of the day, put your clothes on the left when you put them away. Then tomorrow morning when you see the sun shine, get your clothes from the right, from the end of the line. Don't you see, said Lou, it will be so nice. You'll wear everything once before you wear something twice. And with everything in cues in his closet and shelf, Jack started to feel quite sure of himself, all thanks to Lou and his wonderful cue.
All right. So that paints a picture of these two abstract data structures. But if we really were to dive underneath the hood, we could implement them in a number of different ways. But we really, I think, need some building blocks via which we could solve problems like those. And we'll see today, too, some others as well. So let's rewind back to week 2, where we introduced you to your very first data structure. That is an array. And an array, recall, was just a chunk of memory whereby elements were stored by design back to back to back. It's an array of contiguous memory specifically. So with an array, we could certainly store not just one thing, but 2 or 3 or even more. And so, for instance, if we treat my computer's memory as this sort of abstraction here, and pictured here are 3 bytes or some multiplication thereof, suppose we're storing in the computer's memory an array of size 3, storing the digits 1, 2, and 3. Well, remember that if we zoom out per last week, there's other stuff going on in memory. So even if we want to add another number to this array that we didn't think of when we first started the program, like the number 4, ideally we would put it right here next to it. Otherwise, it's no longer an array. So by definition, if we're using an array, it's got to end up right there after the 3. But what else is going on inside of your computer's memory? Well, assuming your program is of any length and you've got other variables, other functions, you've been running it for a while, there's a lot going on and your memory is being used and reused. So for instance, somewhere in memory might be immediately adjacent to this, like hello, comma, world, \0, the null character, just because maybe you have another variable somewhere in there that is storing that particular string alongside your existing array of size 3. And all of these Oscar the Grouches here really just represent what we called last week garbage values. Like there's obviously bits there because they don't disappear. They're always going to be inside of the computer somehow implemented, but we don't really know or care what they are. They're the remnants of those bytes having been used for other older variables, previous function calls, or the like. But the problem clearly here is that, OK, 1, 2, 3 is there, but the h is here. And unless I want to start taking a byte out of my string by overriding the h with a 4, like we just can't fit it right there. And yet, even though there's Oscars all over the place, those are indeed garbage values. And therefore, we could use that space because it's technically unused. We just don't know or care what the values are. So where could I put 1, 2, 3, 4? Well, my gosh, like I have all this memory down here that's unused. I could certainly change those garbage values to be 1, 2, 3, 4. But to do that, I might need to do a bit of work here, right? It's not just a matter of just saying boom and it happens. Now with C and with code, I'd have to do this a little more methodically. So let me abstract away everything else that's a distraction. Let me assume that there is indeed at least 4 bytes available for 4 numbers just down here, though we could have put them in a bunch of different spots. What's involved now in moving the 1, 2, 3 to this new chunk of memory so we can add the 4? Well, I think conceptually we're going to have to copy the 1 from old to new, copy the 2 from old to new, copy the 3 from old to new, and then ultimately we can get rid of the old memory. Those 3 original bytes could now look like Oscar the Grouch and just be garbage values for all intents and purposes. But now I have room for a 4th byte wherein I can put the number 4. So this is nice, but what's a downside of this approach? What's a downside of solving the problem in this way, where the problem at hand is just to grow the array, so to speak, to increase its size, to fit 1 or more numbers? Seems pretty straightforward, but yeah. Okay, maybe it's out of order, but I think that's OK because the order is just matters that it's relative. So long it's still contiguous, back to back to back in a different chunk of memory, I think we're OK there. It's not like I changed it for 4, 3, 2, 1, but a reasonable hunch, yeah. Yeah, like I didn't really plan ahead here. Like if I have to add another number like 5 or anything else, well, I might have to jump through these hoops again. Maybe I get lucky and maybe there's space there, but not if I have other variables and other things going on. That too might be used at some point. Other thoughts? Yeah. Slow efficiency. Why? Yeah, I mean, it's just inefficient. It's sort of bad design, arguably. Why? Because I had to copy all of my original work down here. And as you note, if I want to add a 5th number, I'm going to have to copy it again and again and again and do things n times again and again. Now, maybe that's necessary. We'll soon see for sure. But it feels like this is not going to end well, especially if the array isn't of size 3 or 4, but 300, 400. Your computer ends up spending so much time just spinning its wheels. I mean, honestly, better might be this. Like if this is my same array, physically incarnated now, 1, 2, 3. It's literally on the edge of the shelf, so there's no room for the number 4. You know, maybe where we could take this story is, well, let's just find room for the 4. Like let's just put the 4, for instance, over here, replacing some available garbage value, some spare byte over here. But now, wait a minute. I've broken the definition of an array, right? I can't have 1, 2, 3, and then 4 over here. So maybe there could be a mechanism if I put this thing on again, where when you get to the end of the existing elements, maybe I just somehow digitally point to the 4th array. And maybe we can kind of stitch together all of these different values in memory so that if you follow the arrows, so to speak, we can reconstruct exactly what the order is, even without having to find or make room here or pick up all of these numbers and move all of them over there. So that's perhaps the direction in which we'll go here. So let's see how we might get to that spot as follows. Let me go ahead and open up, say, VS Code here. Let me open up a program called list.c in my terminal. And let me go ahead and whip up a relatively simple program that just demonstrates what we did back in week 2 when we introduced arrays as follows. Let me include standard io.h so we can print stuff out. Let me do int main void, no command line arguments for now. Let me give myself an array called list of size 3, and I'll just hard code it to keep it simple for lecture's sake, each of which is going to be an integer. And now just so we have some specifics to talk about, let me put it list bracket 0, the number 1, list bracket 1, the number 2, and list bracket 2, the number 3. So I'm just translating into code what we just had pictorially on the screen and also physically here with these numbers on the desk. Now let's just do something mildly useful for this. How about we do for int I gets 0, I is less than 3, I plus plus. Let's just print each of these numbers out just to make sure they're indeed in memory as I intended. So %i \n, comma I, and then a semicolon. And I think that's it for now. So nothing interesting, no problem solved just yet, just a proof of concept so that now when I clear my terminal and run make list, no apparent errors at the terminal. And so when I now do /list, I should see, hopefully from left to right, 1, 2, 3. But of course, if I want to add a 4th number now, there's no mechanism for such, certainly in the code that I just wrote. I could go back in here and change this to a 4. I could go down here and change list bracket 3 equals 4. I could just manually change the code, recompile the code. But of course, that doesn't give me any additional runway for the 5th or 6th number. So let me try to take a different approach, drawing some inspiration from last week. If I want to allocate memory dynamically, maybe because I don't know when I wrote the program how many bytes I want, we have another function as of last week that does not require that you commit in advance to a certain number of bytes. Via what function can you just ask the operating system for a chunk of memory? OK, so malloc, to allocate memory. Now, an array is just a chunk of memory. And even though since week 2, we've been using this syntactic sugar, this convenience of just using square brackets and indexing into it, it's just making it easier to manipulate a chunk of memory that's contiguous, all together, back to back to back. So today, just like last week, we can take those sort of training wheels off and maybe be a little more deliberate in how we allocate memory. Let me go, for instance, and do this. Let me delete my contents of my main function here, go back into main, and let me propose now that I declare, for instance, how about my list no longer as an array, but as a pointer? So int star list, and I'm going to go ahead and initialize this to be, how about a chunk of 3 integers for now? So I'm still going to hard code it, but I'm taking a step toward more dynamism for now. So let me allocate 3 times whatever the size is of an int, but it's usually going to be 4 bytes as we know. So this is really going to be 3 times 4 equals 12, but it's a little more dynamic. And now what can I do down here? Well, this is just a chunk of memory. So I can do literally list bracket 0 equals 1, list bracket 1 equals 2, list bracket 2 equals 3, and voila, achieve the exact same effect. Because again, an array is just a chunk of contiguous memory. But malloc gives you any old chunk of contiguous memory, so you can rather treat one like the other here. Now, if you really want to be cool, you could do something like this instead. You could dereference the address in list and go there. You could go down here and dereference list plus 1 and go there. But honestly, no one really writes code like this. It's just too cryptic. It's a little too far over the line, at least for most people. And so I think the syntactic sugar, as I keep describing it, just the more user-friendly square bracket notation, does the exact same thing, figures out the pointer arithmetic, and puts each of these integers in the right chunks therein. Now, just to be super pedantic, let me make sure if something went wrong. So if list equals null, that means that something went wrong, like my computer is out of memory, which we should check for typically. So let me just immediately return 1, signaling anything other than 0, which means success typically, just to get out of this program because something's wrong. But now let me propose that I've had a, well, let's do this. For int I gets 0, I less than 3, I plus plus. Though a better design would always be to use a const, but I'm just doing this for demonstration's sake. Let's print out each of these ints too, and just make sure I didn't mess anything up. And let me open my terminal window again. Let me do make list again. OK, implicitly declaring library function malloc with type void star something something, implicitly declaring is the operative words there. What did I mess up? Yeah. Yeah, I forgot the header file in which malloc is declared. I remember now, OK, that's in standard lib.h. And it's fine to look stuff like that up if you forget. So let me include standard lib.h. Now let me clear my terminal, run make list again. OK, now we're good. /list. And now what did I do wrong? Oh, OK. Not intended, but teachable moment. What did I do wrong? Yeah. Yeah, I'm printing the values of I instead of what is at location I in the array. So what I actually meant to do was print this out, thank you. So now let me recompile, make list, /list. And now, OK, those are the 3 values I was expecting, not the indices thereof. Now let me propose that for the sake of discussion that I regret having only allocated space for 3 integers. And maybe I really should have allocated enough space for 4. Now, this is not how you would do this in practice, because presumably if you have a change of thought, just go back in and correct the code. But let me propose that somewhere in here is a more complicated program and time passes, ... There's a lot of other interesting code there. But at some point, I might want to give myself more memory. So how can I do this? Well, let me just ask the operating system now for 4 new bytes of memory so that we can, at least in version 1, implement the idea on the board where I just copied the 3 bytes into the new 4 bytes and then added a 4th value. So I'm going to use malloc again, and I'm going to say here's a new pointer. I'll call it temp. TMP for short, which is quite common when you just need it briefly. I'm going to then call malloc again. I'm going to say give me 4 integers using size of. Let me again make sure. So if temp equals null, something went wrong. So let me just immediately return 1. And for good measure, before I return 1, let me free the original list so that I don't leak memory. So I'm not just immediately returning 1. I'm being a good citizen and remembering, well, if this malloc call did succeed, and indeed I got as far as line 18, but then line 18 failed, I should free the memory that I previously mallocked. So again, that's the rule of thumb. If you allocate it, you should be the one to free it, even before you're about to quit. Now, once I've done that, I think I need to do what we did pictorially on the screen, where I need to copy the 1, the 2, the 3 from the old array into the new. So how might I do this? Well, let me give myself a loop. So for int I gets 0, I less than 3, I plus plus, because the size of the original is still the same. Let me go ahead and treat the new chunk of memory called temp as an array itself. And so I can absolutely use these square brackets just like before. It's just a chunk of memory. I'm treating it like an array. And let me add to that value whatever's at the original list at location I as well. So this, again, is just this exercise of copying from old to new, step by step, the 1, the 2, and the 3. But I still need one additional step. If my goal at hand now is to have ultimately a 4th value here, well, I'm just going to hard code this for demonstration's sake. And I'm going to go to the very last location of temp, which is of size 4, which means the last element in temp is temp bracket 3, because it's 0 indexed, but there's 4 total spaces there. And I'm just going to arbitrarily, for the sake of discussion, put the number 4 there. And that is what happened when we proposed changing the final garbage value there to that 4. But now I need to do what the slide did for us sort of magically on the screen. I should now do a couple of final things. I should free the original list, which I've not done yet, because I only called free earlier in cases of error, and that was just to be safe. I can now free the list. And now if I want to inform the computer that I want list, quote unquote, my variable called list, to point at not the old chunk like it originally did, but the new chunk, I think I can just do this. List equals TMP. And again, that's just saying that if list is a pointer, which it was, because look at the very top line here. On line 6, I declared list to be a pointer to a chunk of memory. Temp, meanwhile, is a separate pointer to a chunk of memory. So down here, this line 33 is just a matter of my saying, OK, now, henceforth, because I've already freed the old chunk of memory, my list variable should point not at this chunk of 3 bytes, but this chunk of 4 bytes, or really 12 in total now. Or rather, 16 now, because we have 4 such bytes. Questions now on this code, the point of which was quite simply to demonstrate how we could implement in code this idea of fairly correctly but inefficiently allocating a new array of sufficient size and then populating it with a new 4th value. Questions on what we've just done here? No? Yeah. Good question. At this point in the story, with line 33, do I not have 2 different variables pointing at the same chunk of memory? Short answer, yes. But here's where the semantics are perhaps compelling. List is the variable that I intend to use longer term and keep around in memory. And again, assume that there's even more code going on here that we just didn't write yet. So it's useful to have that variable. Temp was just kind of a necessary evil, because up here, it would not have been correct to do this. It would not have been correct to say list on line 18 equals the new chunk of memory, because this would have represented a memory leak. If I prematurely change temp to point not at the old chunk but the new chunk, at that point, no one's pointing at the old chunk, and so I've lost those 3 bytes. Valgrind, for instance, would yell at you for having lost as many bytes in memory. So in this case here, I do leave this as temp. Yes, it's duplicative at this point, but it's not a huge deal if it was just meant semantically to be a temporary value. But down here, at the risk of one more line of code, I still want to be a good citizen, free list, and maybe just for good measure, return 0 explicitly. But notice, it's not doing it twice per se. On line 31, what am I freeing? The original address of list, the 3 integer version. Then I change what list points at. So it's pointing at a completely different chunk of memory, this one of size 4. So eventually, when I'm all done using this memory for this demonstration, I still need to free list. But at this point in the story, line 40, it's pointing at the new chunk of memory, which I similarly need to hand back to the operating system by free. Yeah? When would temp equal null? So let me scroll back up slightly. This is being a good citizen and a good programmer. Whenever it comes to using malloc, malloc can return null if the computer is out of memory. So this is maybe a much bigger program. You've got other things going on in it. And so you just don't have enough memory available to be handed. Malloc needs to signal to you that there's some error. And so it will, by convention, per the documentation, per the manual pages, return null. So this is just me being a good citizen. Otherwise, here's another error that might cause your program to crash with a segmentation fault. If you get back null, but you assume that it's good memory, going to address 0, aka null, will crash your program intentionally. Yeah? Correct. If I were to change my final line 40 here to be free temp, this would also work as well. And here, this is really a matter of design. It's a very nitpicky thing. We could probably debate it. But because at this point in the story, my main variable for remembering where the list is called list, this is sort of the more responsible way to do it, freeing the list, just so that my colleagues, my TA, doesn't sort of wonder, why are you freeing temporary memory that you already freed? Like, it just is a semantic thing at this point. But good instinct. It would also work, correct? Maybe just not good design. All right, so it turns out that this gets annoying quickly, as it did in the picture of doing all of this duplication. And even though technically it's necessary to copy those values if you need a newer, bigger chunk of memory, there is at least a function in C that simplifies a lot of this for us. And in fact, let me go ahead and do this. Instead of using malloc this second time on line 18, in addition to the first time I used it on line 6, I'm actually going to try and introduce another function called realloc, which, as the name suggests, tries to reallocate memory for you. And it works a little differently from malloc. Realloc expects 2 arguments. The first one is, what is the chunk of memory that you want to try to grow or shrink? That is, reallocate to be a different size. And then you specify what size you would want. And indeed, in this case, I want 4 times size of int. And that will now give me, hopefully, a new address of a chunk of memory that's big enough to fit all 4 numbers. But what's wonderful about realloc is that it will handle all of the copying for me. So in fact, I'm going to go down here. I'm going to get rid of all of this extra for loop. And what I'm simply going to do instead is this. Once I can trust, after lines 18 through 23, that realloc worked and it didn't return null because I'm out of memory, I can just say, OK, just immediately remember that the new list points at this new chunk of memory instead. And then I can still now do this line, but I can tweak the semantics here and just say list bracket 3, the new final location in the new list is 4. I don't need to free this here. I don't need to do this. All I need now at the bottom is the final for loop to just print out these values. So in short, even though that was somewhat quick, using realloc just moves the entire copying process that I implemented myself a moment ago using a for loop. It just moves it to realloc and lets it deal with the copying for me. It's no more efficient, but at least means I'm writing less code, which is more pleasant. And hopefully the people who wrote malloc or realloc are smarter than me, and they just will introduce bugs with lower probability too. All right, that was a lot. Any questions? Good question. Why do you still need to make list equal temp as I did on line 24? So ideally, I would do this. Ideally, I would just change this line 18 to be list. That is to say, or actually, even better, ideally, I would just say realloc this list to be of this new size. But again, things can go wrong when allocating memory. You need to check a return value to see if it was successful or not. And so we need to use a return value. OK, so let's not introduce temp. Let's just use list. But here's where a memory leak might happen. In the off chance realloc fails and doesn't have enough memory for your 4 bytes, therefore, it returns by definition null. You can't overwrite the original value of list with null to then check it. Why? Because now who remembers where the original 3 bytes were? If you prematurely change the value of list, you've lost. You've leaked memory in that sense. And so that's why, let me undo this change, I declare a temporary pointer for the sole purpose of making sure I can check the return value. And then once it's good, now I'll update the value of list. So it's sort of doing a switcheroo by making sure first that you have a new value to swap with the old. Other questions on this code? Yeah? Indeed, realloc automatically frees the previous memory for you. And better yet, it's even smarter than that. If you get lucky and there happens to be space right after your existing chunk of memory, so 1, 2, 3 garbage value, instead of 1, 2, 3 hello world, realloc won't even bother copying things from old to new. It will just say, OK, I'm going to now reserve for you more bytes than you originally asked for, so it doesn't have to waste time doing that copying. And so in that sense, this version is now not only still correct, it's even better designed because we're not wasting time with that for loop. We might have to resort to it if there is, in fact, hello world or something else in the way, but hopefully we'll get lucky and save those steps. Other questions on this manipulation of code here? Yeah, in the middle. What if you want to resize a two-dimensional array? So very similar in spirit, whereby you can use the same trickery. Let me wave my hand at that for now, just because I think that's going to sort of significantly increase the complexity, but very same primitives. Ultimately, a two-dimensional array is essentially just a doubly long or quadratically longer list of memory that, using square bracket notation, is doing some of that mental math for you. But it's fundamentally no different of what's going on underneath the hood. All right, so with that said, and that code under our belt, even though that's not going to be something you'll frequently need to code yourself, let's propose now how we might go about building some actual data structures ourselves. The new ingredient here being this reality that if you want to resize a chunk of memory so as to make room for things, we now have that ability. Memory addresses and pointers just give us the ability to point around at things and move things around in memory. But now that we have malloc and even realloc, you can imagine maybe rewinding, and you could implement that stack, that queue, using not an array per se, because you have to commit to an array size in advance, but if you implement your stack or your queue using a pointer, and then malloc and realloc, and maybe someone else writes all that code for you, perhaps now you can imagine that, OK, now the stack can grow or shrink by using realloc accordingly. You don't have to preemptively say, give me 5 bytes or 50 or 500 or 5,000. You can say, just give me 1 initially. And if I need more, I'll realloc, realloc, realloc. And if you keep popping things off the stack, you can realloc in the other direction and ask for fewer and fewer bytes. And the operating system can take that memory back as well. So we now have this building block. Let's see what we can do with it. So we've had a few pieces of syntax in recent weeks, all of which we're going to combine now in just a slightly more clever way. So struct is this keyword in C that lets us build our own structure in memory, like a collection of 2 or 3 or more variables, like a person that we've seen before. The dot operator, recall we've used when you do have a struct, like a person, and you want to go inside of it. So like person.name or person.number. We did this a few weeks ago now. But the dot operator just allows you to go inside of a structure and get the individual variables within. And then the star operator, unfortunately, has a lot of uses now. One was multiplication. My God, that was easy back in the day. Now it's used to declare pointers. It's also used to dereference pointers, so to make one exist and then go to that address. Unfortunately, it's the same symbol for all of those, but it's all related. But with these 3 symbols, it turns out you're going to get one last one today. And my God, it finally looks like the concept. It turns out there's a clever way anytime you want to use the dot and the star together, that is to go somewhere and go to an address and then look inside of a structure, you can actually literally use an arrow symbol on your keyboard. It's not a single keystroke. It's a hyphen and then an open angle bracket. But at least it looks like an arrow. And we'll see indeed in code today, the things I was drawing pictorially on the screen last time with yellow arrows, you can actually now express as well in code. And so here we have our next data structure called a linked list. And this is one of the most useful, powerful concepts in C. It's the kind of thing that you can take for granted in Java and Python and higher level languages. But today we'll see how we or others can actually build these things just using these same primitives. So a linked list is going to allow us to actually do what we used a foam finger for last week, allow us to link together, for instance, these 3 values, maybe with that 4th value over there. And then if there's a 5th, maybe this other foam finger points even farther over way to that 5th value. The key being that you can stitch together fancier data structures without having to pick all of these up and find new space. you just have to at least connect the dots somehow. We just need to somehow point from one to the other. And that's going to make things much more efficient, it would seem. So how do we get there? So here's my computer's memory as always. Suppose that I'm storing the value 1 somewhere in there, and it's at 0x123 address, whatever. And I'm storing the number 2 somewhere else in memory, 0x456, and number 3 at address 0x789. This is not an array by definition. Why? Even though it's the only 3 things on the screen, what makes this not an array? It's not contiguous. So this violates the definition of an array. But you know, especially since they're sequential, it kind of looks to a human like a list. So it would be nice if there were a data type called list. And there isn't in C. There will be in Python. But you know what? If I could somehow like stitch together these 3 values so I can get from one to the next, then I think we could achieve the idea, the concept of a list, without this really annoying constraint that they all be contiguous as in an array. So how do I do that? Well, at the end of the day, I only have memory at my disposal, right? There's no more training wheels to take off here. This is what we've got underneath the hood of a computer. So if all I have is memory, I think the solution to this problem of stitching together those values in a list must be to spend a bit more memory. That's literally the only resource we have right now. So let me propose that if we want to create a list conceptually out of 3 values that are in random, although pictorially pretty, positions in memory, let me just add a little bit more memory to the picture. So in addition to storing the 1, I'm going to leave myself some room, a little scratch pad, if you will, to use some other bits as well. Same for the 2, same for the 3. And you can perhaps see where this is going based on last week. If I want to somehow connect the 1 to the 2, any instincts as to what I should write in this box here that would lead me effectively from 1 to the 2? What could go here? Yeah? We could store the address of 2. And so specifically, what would you have me write here? Perfect. Ideally, I would just put in this box another integer, one that happens to be represented in hexadecimal. But that's just a base system. It's just a human thing for us to look at. I'm going to put the value 0x456 here. So let me go ahead and reveal that. 0x456 goes there. You can perhaps see further where this is going. Well, if I want to get from the 2 to the 3, I think I need to put below the 2 the address of the 3, which gives me 0x789. Now, if 3 is the end of the list, I don't want to let it be some garbage value, because that would imply that who knows where it's pointing. I need some definitive value. And just what would your instincts be? If I want to make clear with some special sentinel value that the buck stops here, what do I put? What might my options be? Yeah, so null, not NUL per se, but NULL, which was the new keyword we introduced last week, which just represents an empty pointer, if you will. Technically, the address 0x0. So literally the 0 address. And what humans did years ago, they just decided, you know what? Nothing should ever live at address 0 in memory. We're just going to reserve that one special byte to be a special signal, a sentinel value, such that if you ever see a 0 address in a pointer, it just means it's invalid. It does not exist. Now, we write that, though, a little more pleasantly for the eyes as just NULL in all caps. And that's a keyword in C as well. But of course, last week I claimed that who cares where things are in memory? And honestly, like, this quickly gets tedious even worrying about these values. So let me abstract this away and propose that if we want to remember where all of these numbers are in memory, let's give ourselves one final piece of memory that just allows us to start the whole process. Let me allocate on the left-hand side here, not room for a number like 1, 2, 3, just room for a pointer that henceforth I think I'll call list by convention, and then store in that one additional pointer a value that just kickstarts the whole process. This is the sort of treasure map, if you will, that you get handed. And this has the address of the very first actual node in memory. Now, technically, we could just start with this. But it turns out, we'll see, it's just a little cleaner to use a simple single pointer that leads to the things you care about, as opposed to just starting with the first element. Why? Well, if you ever want to get rid of this element, it'd be nice if you could at least still hang on to an empty sheet of paper that indicates that the list is empty, would be one argument for that. So again, who cares about these addresses now? Now, with a wave of the hand, let's just abstract it away. And there are our pointers. Each of those addresses in the squares at the bottom are simply pointing to the next element in the list. The jargon to introduce here would be that now that we have these integers, 1, 2, 3, but they're in these like wrappers, if you will, these structures that have metadata, that is additional data that is related to, but not the data you actually care about. This is data, this is metadata. This thing here, rectangularly, we'll call a node, N-O-D-E, and it's just a term of art that means it's like a container in code for storing some values. This then is a linked list, and this then is the sort of graphical incarnation of like one node pointing to the other. In this case, they happen to be, by chance and by design of this desk, contiguous initially, but there's no requirement that they be such. The 1 could be over there, the 2 over there, the 3 over there. I would just need more foam fingers to point at one to the next. Questions on this concept of a linked list? Yeah, and back. Can you say that again? A good question. Do traditional arrays start with a pointer that's outside of the structure? Short answer, no. Arrays are special in C and certain other languages. And the name of an array is technically a symbol, if you will, that the program knows maps to a specific location in memory. It's just a label, a synonym for a memory address. It does not take up space. So to be clear, the name of an array does not take up space like that extra square on the left, but you do need that extra square on the left when implementing a linked list so that you can determine if the list is of size 0, there's nothing being pointed at, or size 3 in this case. We're sort of taking on more responsibility ourselves. Yeah? How do you point to the next element? Can you elaborate?
Each element is pointing to the next one. How does 3 per se like point to like the first or the next?
Good question. If each of these elements is pointing to the next, how does 3 point to the others? Short answer, it doesn't. At least in this design, we have more technically what's called a singly linked list. And as the arrows imply, it only goes in one direction. So if you somehow find in code, maybe a for loop, maybe a while loop, somehow you're sort of in code over here, you have no way in code to go backwards unless we change this to a doubly linked list where I add another box that lets me have arrows in both directions. Or maybe I just kind of make it circular and I connect the 3 back to the 1, which you can totally do, but that tends to make life harder because now you have to figure out when you're stuck in a loop in your data structure, but it's doable as well. But as is, it's a dead end by design. Other questions on this design here? All right, well, how might we implement this structure in code? Well, let me just connect the dots to something like we've seen before here. Like this is how, a couple of weeks ago, we introduced the notion of a person, and we claimed a person might have a name and a number. Last week, of course, we took off some of these training wheels, and a string is really technically a char star in both cases, but really there's no conceptual difference beyond that. But let's use this same paradigm to implement a node as I described it in that picture. So let me get rid of the name and the number, because that's related only to a person. And let me rename this structure, for discussion's sake, to node. That then invites the question, well, what needs to go inside of a node? Well, minimally, an integer. But this is now where we need to think a little harder, just conceptually, even if you have no idea how to type it at the keyboard, what else needs to be part of a node based on these rectangular pictures that we've drawn? What more do we need? Yeah? Yeah, we need a pointer to another node. So if I don't know how to implement this yet, it could be something like, pointer to another node. How do I do that? Well, you know what? It turns out you would ideally say this. If you know that the next node is itself a node by definition, well, anytime we've needed a pointer, we just use the data type and a star. And I'm going to arbitrarily, but I think reasonably, call this second square at the bottom of those rectangles next as the name of my attribute here. But node star just connotes that the next variable is going to be not a node per se, but the address of a node. And that's exactly what we did. You had me put 0x456, 0x789 in that box, which is the address of another node. So the way we would express this in code would be node star next. But we could call the variable anything we want. Now, this is a bit of a white lie. but we'll fix this right now. This code won't actually compile. C takes you pretty literally, recall. And if you use some term at the top of your file that you don't define until later in your file, you're going to see some error message, right? We've seen this when I've messed up and I forgot to include the function prototypes at the top of my code. This is related in spirit. I seem here on my 1, 2, 3, 4th line of code, I'm trying to use this new term of art that I invented here in my code called node, even though it's a CS term as well. But nowhere above this, it would seem, did I even define what a node is. It's not a data type in C. Every computer scientist knows what a node is, but it doesn't come for free with the language. So I need to do something else. Like I need this word here to come first so that I can use it here. And so we have this sort of catch-22. Like how can a structure be self-referential, that is, point to another version of itself if the word doesn't yet exist? So the solution to this in C, which we didn't need for a person because there was no notion of listing, connecting as a list, we need one more keyword here that we didn't need for a person, and we reuse that keyword here. So kind of an annoying detail, but if we preemptively call this whole thing struct node, you can now refer to the thing on the inside as a struct node star, but then you can shorten the name of the whole thing from struct node to just node. Sort of an annoying sequence of steps, but in short, anytime you're building a node, a linked list in memory, this is just the paradigm. You use typedef, struct, the name of the thing you want to define, like node. You use that name on the inside if you want to point from one to another, and then you can shorten it down here to just be called node. Questions then on this code here? Questions on what we just did? Well, if I rewind just a moment to that final picture, what would be the upside, to be clear, of having jumped through these hoops and added this complexity, if you will? What problem did we just solve by linking together these three values, to be clear? Yeah? Making lists that are not contiguous, if you will. So making lists that are not contiguous in memory, the upside of which is that if I want to add the number 4 to this list, it looks like I could choose from any chunks of available memory on the screen. I just need to sort of point from the end of the current list to wherever that other one is in memory. What I don't need to do, to be clear, is copy the 1, the 2, or the 3. Everything can just stay put, which means time-wise, I can do this much more quickly, it would seem, without copying things again and again, and even without using realloc to let it do all of the copying potentially for me. All right, but as we'll start seeing even more in the coming weeks, every time we benefit and solve some problem, we pay a price. There's a trade-off. What is a downside, as you might perceive now, of using a linked list instead of an array? Yeah? Yeah, I mean, we use twice as much memory because now, in addition to storing the integers 1, 2, 3, I also need to store a pointer for each of those. And honestly, even this picture is a bit of simplification. Technically, in most systems today, each int would be 4 bytes. Technically today, most pointers, though, would be 8 bytes. I just didn't want to draw this weird shape on the board where the bottom square is even bigger than the top square. But technically, we're using even more than twice as much space for these pointers. So there's that trade-off. Now, thankfully, decades after C was invented, memory is generally much cheaper nowadays. And so it's OK to sort of spend more of it if you need to. And it depends on what you want to optimize for. But that's absolutely here a downside. What's another downside of having transitioned to a linked list? You can't index into it. Now, I haven't even tried in code, but when you have a linked list, you can no longer use square bracket notation. Because why? Well, square bracket notation just assumes the contiguousness of memory. Location 0 is here. Location 1 is literally 1 to the right. Location 2 is literally 1 to the right, 1 to the right. These things, even though I've drawn it from right to left to just keep things pretty, there are gaps here. And this is just my interpretation of this. These gaps could be big. They could be narrow. They could be down here, up here. They could be anywhere so long as we're linking things together in this list. The computer can't just use bracket 0, bracket 1, bracket 2 anymore because it can't do simple arithmetic and jump to like the middle. And now here's perhaps the worst price we've paid. If you don't have square bracket notation, or really you don't have contiguousness, what algorithm did we just sacrifice for this dynamism? If you rewind even back to week 0, and we gave it a name in week 3, what algorithm can we not use now if we can't assume that the memory is back to back to back to back? Binary search. Why? Because binary search, just like the phone book back in the first week, requires being able to arithmetically jump right to the middle, right? Take the total length of it, divide by 2, and boom, you're right there in the middle with some simple arithmetic. Here, they might be laid out, again, with these big or small gaps. There's no simple math I can do to just jump immediately to the one in the middle. And in fact, again, if this TV were bigger, the 2 could technically be in memory, be way down here or even way over here. The foam finger could be pointing in any number of directions depending on where Malloc put the thing. There's just no way to do binary search. And so it would seem that we've paid another price, indeed, in terms of its performance. We're now talking about linear time again. So that's a regression. Now, that's also a lot. Feels like a good time for some muffins and fruit out in the lobby. And when we come back, we'll try to solve the problem we just created. So see you in 10. So we are back, and let's see if we can't now take some of these higher level concepts of like stitching together these nodes in memory and translate it to some actual code. But we'll do it step by step first before I actually start writing it in VS Code. So if Carter, you wouldn't mind helping me step through with some visuals, let me propose that line by line we solve some of the problems that we've just created for ourselves in building this thing in memory. So let's go ahead and first consider how we could build a linked list containing the numbers, indeed, 1, then 2, then 3. And let's translate each of those steps to code, and then we'll put it all together into something that actually runs. So how about the first step here will just be this, to declare a pointer called list that initially has no value, at least at this point in the story. List is the name of the variable. Node star just means that this is essentially going to be our little square over here that points to the beginning of the list. Of course, it's ideal if it ultimately has a value, because when we initially call this line of code, it just gives us, indeed, that square over here on the left, but it's got a garbage value because there's no equal sign on the other side there. So let's propose that we do one more step here and actually initialize it to null, so that if only we know that it's not garbage, it at least has some known value. And null is a good way of signifying that at this point in the story, the list is empty. Indeed, null indicates there's no nodes in the list. So that picture would now look like this, whereby let's just draw, instead of writing null everywhere, I'll just leave the squares blank when it's not a garbage value per se. It's literally OX0 or null. All right, so that's it for building a linked list of size 0. Like, we're sort of done then, but we want to now add a 1, and then a 2, then a 3. So next step here might be this. If I want to allocate the first of my rectangles on our previous picture, I'm going to call malloc, and I'm going to ask for enough memory to fit a whole node. Now, technically, I think that's going to be like 4 bytes for the int and 8 bytes for the pointer, even though I did not draw it to scale on the board. So that's technically going to be, what, 12 bytes? But again, size of node just figures out how many bytes I actually need dynamically. That's going to return to me the address of that chunk of memory, which apparently I'm going to store inside of a temporary variable called n for short for node. But let's see what this does pictorially. So when this line of code is executed, I first get on the left that variable n. It's got a garbage value by default because I haven't executed the whole thing from right to left. Meanwhile, on the right-hand side of the expression, I've got now a node somewhere in memory. It happened to be free here. This is where malloc put it for me. But it does have 2 garbage values initially. But because it's a node, per my type def earlier, every node I proposed is going to have a number and a next pointer. So we can see those labeled here. But they've got 2 garbage values initially. But all I care about initially is that ultimately n is pointing at that chunk of code. So initially, if we could back up 2 steps, we have 2 steps. So we have one step forward. We have this line of code gives us this variable here, which has garbage. When this side of the expression is executed, that allocates the memory. And then when we copy from right to left the address of that chunk of memory, that's what gives us conceptually this arrow, and the garbage goes away because that's a valid pointer now. Of course, there's still 2 garbage values there because we haven't set this node to store a number like the number 1. So let's go ahead and execute one other line of code like this, which, while cryptic looking, is just an application of ideas we've seen in week 4 and prior. Star n means to start at this variable and go there. Follow the arrow is what the star or the dereference operator does for us. And then the dot operator, recall, when we first introduced structs, like for a person struct, allows us to go at the number field or the next field. So if I do star n, and then in parentheses to make sure order of operations is preserved, dot number, and then assign it the actual number 1, which puts the 1 in the top of that rectangle. Now, admittedly, this syntax is not very user-friendly. It's annoying to remember. You have to have the parentheses. So there's another syntax for this. Whenever you're doing 2 things like this in code, dereferencing a pointer that is going to an address, and then further using the dot notation to go inside of the structure you find that. Wonderfully, C gives us this syntax whereby you can just change the star and the parentheses and the dot to just be an arrow. And again, it's not a single character on your keyboard. It's a hyphen and then an open angled bracket. But I kind of like the semantics of this because this code now pretty much matches the picture. N arrow leads you to the value that you want to access or ultimately change in this way. There's one step, though, we've forgotten, of course, which is that we can't leave this garbage value here because the garbage value is some unknown value that effectively is pointing who knows where. And we don't want to accidentally misinterpret that garbage value as being a valid address and risk going there. So, of course, what value should we put here instead? Our old friend null, just to signify that this is indeed the end of the list. And we could do that with a line of code like this. And again, we'll connote as much by just leaving that empty box blank. So now we have a list of size 1. Let's go ahead and add the second number to it, as with these lines here. List equals n allows us to remember that indeed we have this list here. So if we can step one step forward, here's what the picture now looks like. And technically, let's go one step further here. This is now really what's going on in memory once my list of size 1 exists. My main variable called list is pointing at exactly that first node. At this point in the story, I don't need to know or care about the temporary variable that I called n, even though it might very well still be there. But indeed, this now represents that linked list. Let's now indeed add the number 2. So with the same line of code as before, I'm going to allocate another node, size of node. Ideally, I would be checking for null here, but we're doing the juicy parts only on the slides. Let's now go ahead and depict that. So what happens with this? This brings back our n pointer, which might have been there the whole time, but we're doing this step by step. It's a garbage value, though, because we haven't yet copied from right to left. Malloc, of course, gives us a second chunk of memory, which maybe ends up there with 2 garbage values by default. I've omitted the labels now just because they're still going to be number and next, respectively. Once we copy from right to left, the garbage value indeed becomes an arrow. Oscar disappears because it's now indeed a valid pointer pointing here. Now, the values themselves, number and next, are invalid garbage values. So here is where we can now start using our new syntax, like the arrow notation, or the star and the dot if you prefer. And we can change the value of n, follow the arrow, to number, and that becomes 2. Similarly, we can do this again and set n arrow next. So start at n, follow the arrow, access the next field, and set that equal to null. Now, we're not quite done yet because we haven't actually linked things together. So here's now where things get interesting. How do I combine these two? Well, let me propose this. Let me propose on our next line here, we actually update for now list equal to n. That is to say, whatever address this is, whatever it's pointing at, change list to be the same address. That is, point at the same thing. So if n is pointing here, let's change list to point here. And go ahead and do that, Carter, if you could. I don't like this. Can you go one further step? This is bad. What is wrong about my sequence of operations here where I updated list to point at my new node? Yeah. Yeah, we lost the pointer to the other node. So I don't even care about the ordering, 2, 1 or 1, 2. The bigger problem now, as the lack of arrows over there suggests, is that I have a memory leak. I have orphaned my original node in the sense that nothing is pointing at it anymore. Now, absolutely, I could fix this by adding some temporary variables. I could add it to the mix. But at this point in the story, I have not done any such recollection thereof. So let me back this up, and let's go forward in the slides. This is where we left off a moment ago. I think I need to take into account order of operations. And I'm going to keep this simple. I'm not going to care about the order of the numbers for now. I'm fine with a list that is 2 and then 1. So with that said, let me go ahead and update, I think, this box here to point at my original node. So let's see how we can do this in code. OK, n arrow next. So n arrow next should equal the current list. And this is a little weird again, but recall what list is. List is this pointer here that just contains the address of the original address of the list. Or, equivalently, it contains this arrow, whatever it's pointing at. So what this means in this line of code, n bracket next means start at n, follow the arrow, access the next pointer, and set it equal to whatever list equals. So if list is pointing here, then next should point there as well. This, I think, is safe because now we have redundancy. Now we've got 2 pointers pointing at the original list. And now I think we can do another step whereby we update list to equal n. Same line of code before that got us into trouble, but I'm doing it second now instead of first. When I execute list equals n, this now sets list equal to the same thing that n equals. And so now I have successfully inserted my new node containing 2 into the list. And in fact, if we advance one more, we can just clear up the clutter, assume that the temporary variable is gone from the story. Now we have a linked list where, admittedly, ordering is wrong. It's 2, 1 instead of 1, 2, but at least it's linked correctly, and I didn't orphan or leak any memory. Questions on this sequence of steps here? Yeah, and back. Yeah, spot on. So this would fall under that category of a stack, if you will, although I've not called it that by name because I just pushed the number 2 onto this data structure, if you will. And indeed, it ended up at the beginning of the list instead of the end. And so here's where we see a distinction between an abstract data structure, which is where we began. A stack is a thing like the pile of sweaters that just has push and pop properties and LIFO access, last in, first out. How do you implement something like that in memory? Well, it would seem that you could implement the notion of a stack here, not for sweaters, but for numbers, using a linked list, so long as you implement insertion, aka pushing, by prepending new values to the list, by prepending again and again. And if, Carter, you don't mind hitting the keyboard one more time, if I wanted to add the number 3 now, you could imagine prepending it to the list. Why? Well, honestly, especially as this list gets longer and longer, I kind of like the appeal of prepending these elements. Why? Because even if this list gets crazy long and way, way out here, you didn't notice me following all of the arrows earlier to do the insertions. If I want to insert a 4th number, a 5th number, a 6th number, all I have to do is like insert it here, if you will, point it at the original start of the list, then update this pointer, and done. And I would say that's like 2 steps, give or take. It's not going to be n steps, as it would be if I had to append the new nodes to the end of the list. Now, of course, we've sacrificed ordering of these numbers. They're literally in the opposite order, or whatever order they were inserted in, but that might very well be OK, depending on the goal at hand. All right, thank you to Carter for stepping through this. What if now we wanted to translate this? Oh, sure, thank you. It's all for you, none for me in this example. So here we have perhaps a way of translating this now to some actual code. And this will be the last of like the sort of intense code here, just to give you a sense of how we can translate this idea now to actual steps. So this is list.c in VS Code here. Let me go ahead and make a couple of changes up top. Let me go ahead and how about declaring a node using typedef, struct node using our new framing as before. I'm going to give every node a number, as I proposed, and every node a pointer to the next element, which is going to be implemented just as before. And I'm going to simplify the whole name as just node. So all of that is the exact same typedef that we proposed earlier. Now, let me go ahead and get rid of all of this code, which we wrote earlier, and recall that this was the most recent version that was not a linked list. This was just an array that we allocated and then reallocated. So this is sort of the old way of doing things, but it was inefficient because we might have to lean on a for loop or lean on realloc to copy everything around. We're now going to re-implement the notion of a list as an actual linked list, not as an array. So my main function now might do something like this. And I'm going to really just copy the lines of code that we just stepped through on the board. So let me give myself a special variable called list that's going to be initialized to null. And this is just my pointer, the square on the left-hand side of the screen, that represents the start of the list. And if it's null, it means the list is empty. So done. I'm done implementing a linked list of size 0. Well, now, how do I want to run this code? Well, let me propose, for the sake of discussion, that this version of the program will take command line arguments. So I want to be able to do something like this. I want to run this program ultimately and type in 3 command line arguments like this, 1, 2, 3. And I want my program in a couple minutes to allocate 1, 2, 3 nodes and stitch them together, just like the visualization on the board. I could use getInt, but it's just going to be faster if we use command line arguments. So again, I'm just borrowing some concepts from week 2. But none of that's possible yet until I change my code here. So let's do this. Int argc string argv. But you know what? We know that strings are not actually a thing anymore. So I can change my command line argument definition to be what it really is. It's really char star. But it's the exact same thing as in week 2. Just strings are no more, at least without the training wheels on anymore like last week. And now let me do this. For int I equals 1, I is less than argc, I++. So what I'm doing with this loop is I just want to iterate over the command line argument. So I have one number at a time from the prompt. What else do I want to do here? Well, let's go ahead and how about do this? Let's get a number. So int number equals argv bracket I. So a couple of notes here. One, I'm starting my for loop at 1 instead of 0, but I'm going up to argc. Argc is argument count, how many words are at the prompt. Why am I starting at 1 instead of 0, though, given my goal? Why am I starting at 1? Yeah. Yeah, so the first value in argv is actually the name of the program. That's obviously not a number, so I want the second value. So I'm going to start iterating over those command line arguments at I equals 1. So that's all. I just want to get the actual numbers at the prompt. Unfortunately, argv bracket I is a string, aka char star. That is not an int. So this line of code won't work. But can anyone think back to like week 2 where we had a function for converting strings to integers? Anyone? Yeah, so a to I is a function that converts ASCII to an integer, assuming what you give it as an argument looks like a number, like 1 or 2 or 3. So let me fix this. Let me actually do the conversion. If I were really being careful, I would error check this, make sure that there's no digits, just like you might have in problem set 2. But for today's purposes, I'm just going to assume the honor system that the user, me, is going to run the program correctly. All right, so now that I have a variable containing the number from the command line, let's just allocate a node for it. So let me do node star n, just like we did in the visualization. And let's malloc enough space for the size of one such node here. I now need to just be super safe. So if n equals null, like if I'm out of memory, you know what? Let me go ahead and just immediately return 1 here. Otherwise, if that's not the case, let me go ahead and update the number field of this new node, which at line 24 does exist because it did not return null. So I did not exit early with return. And let me just store whatever number the human typed in first. So the return value of a to I, which per line 17 is in my variable called number. And then let me go ahead and just prepend this to the list. Let me go ahead and say that this next field first has a known value null, just so that we get rid of that second garbage value. And let me go ahead and now prepend it to the list. So if I want to prepend it, that means this new node must have a next field that points to the current beginning of the list. And again, the goal here is to prepend. So whatever the current list is, let's change it so that this new node points to that existing list. And now, step 2, as before, was to update the actual list to point at this node. So recall in red on the screen before, I screwed up originally, and I only did this line by moving the pointer too early, if you will. But I fixed that once Carter helped me rewind, and we got rid of the red line, which indicated error. And I just do n arrow next to change the next field of this new node to point to the existing list. So I'm not orphaning anything. All right, at this point in the story, I think my code is correct. Not batting very well, though, today. But I think my code is correct. But the program doesn't do anything interesting. So it would be nice to kind of now iterate over this linked list in memory, whatever its order is, and print things out. Well, how do we do that? Well, it turns out if you want to iterate over a linked list, the general paradigm is to do something like this. To define a temporary variable, I could call it temp, but another convention that you might as well see is called pointer, PTR, for short. But you can call it anything you want. And you can have a temporary variable first point at the first node in the list. And then in some kind of loop, like a while loop, you point it at the second node in the list. And then you keep iterating. You point it at the last node in the list. And then eventually you iterate too far, effectively pointing at null, at which point your while loop can presumably terminate. So how do I implement that idea of allocating a temporary pointer that just points at each node in the list and lets me print out, ultimately, each of those numbers? Well, let's go back to my code here. And let me do this. Let me go ahead and declare this temporary pointer, which is going to be a node star also. Why? Because it's the address of a node, the first, the second, the third. And I'm going to set that equal to whatever the beginning of the list is. So that is going to be equivalent to this version of the picture here, where pointer is just temporarily pointing at the first node in the list. It's not pointing at list per se. it's pointing at the first node in the list, which list is also pointing at itself. All right, once I've done this, I think I can translate this to code that's a little new, but it's conceptually familiar perhaps now, while that pointer does not equal null. So while I have a valid pointer, like my finger or that arrow is pointing at an actual node in memory, well, let me go ahead and print it out. So let me print out with %i\n whatever is in the current node at the number field within. And again, this is going to have the effect, hopefully, of first printing the 3. And I think I just need to now update the pointer so that on the next iteration, it's pointing at the next value. So if this is where the story is, how do I update pointer to point at the second element of the list? Well, I want pointer to point at the 2, and I want pointer to eventually point at the 3. Well, how do I do that? Well, the way in code I can follow these arrows is as follows. If I currently have pointer pointing at this node, but I want to point it at the next node, I can borrow this pointer here. So whatever this address is in the first node, aka the next field, I can copy that into pointer, because then pointer will point at whatever this is pointing at by just setting one equal to the other. So once I've done that, the picture will become this. And how do I translate that to code? While new syntax is surprisingly straightforward, all I need do is say pointer after printing it equals whatever pointer currently is, but grab its next field instead. And this is a very common paradigm when iterating over a linked list and you're using some temporary variable like pointer, you can simply set pointer equal to pointer next. And what that means here is as follows. If this is pointer pointing from here down to here, pointer next is follow the arrow, grab the next field. So if you set pointer equal to this thing, that's the same thing as pointing this at this same box. And indeed, if I advance to the next slide, even though the arrows are technically pointing at different parts of the rectangles, that's just for graphics' sake, pointer is now pointing at the second node. And when I do this again on my next iteration, it points at this. And then this last step, notice, when I keep doing pointer equals pointer next, this will become eventually this value. But what's this value in this linked list? It's null, technically. So this arrow will eventually take on this value when I set pointer equal to pointer next. And at that point, PTR, my temporary pointer, is going to be null. So it might as well look like this pictorially. And what does that mean for my loop? Once pointer is null, because you've walked off the end of the linked list, what's going to be true of this loop here, started in line 32? Any observations here? What's going to be true? What will happen now as soon as we hit the end of the list? Yeah, sorry. The loop is going to break out. Why? Because line 32, which is constantly asking, while pointer does not equal null, well, if pointer finally equals null 3 steps later, the while loop is now done. And so what I can do at the end of this program, once I've printed out those values, well, first let's go ahead and open my terminal window. Let's make list. OK, compile /list, and let me try the same values, 1 and 2 and 3. That's going to, again, allocate 1 node, 2 node, 3 nodes by prepending each of those values. And it's then going to iterate over them from left to right. And so when I hit enter now, what should I see on the screen if my code is correct? What will I see? Feel free to just call it out. 3, 2, 1, because I've prepended presumably. And here we go. I indeed see 3, 2, 1. So the list is backwards, but all of the elements are there. Now, technically, if I ran Valgrind on this, Valgrind would not be happy because I have never freed any of my memory. So I should probably now have a second loop here that does something like this. Let me again set pointer equal to list. I don't need to redeclare it because I've already created this thing on line 31. I just want to reset it to be the beginning of the list again. And now I can do the same kind of thing. While PTR not equals null, go ahead and do this. Well, I don't want to just do free pointer and then do pointer gets pointer next. Why? My goal is to free all of my memory, but I think this is going to get me in trouble. Pointer equals list just gives me a temporary pointer that points at the 3, and then eventually the 2, and then the 1. How? Well, while pointer not equal null, I'm freeing the pointer. So this is like saying to malloc, free that node, free that node, free that node. But what's the problem with what I've just done here? This code is technically buggy. Yeah. Exactly. After you call free on pointer, you are, by social contract with C, not allowed to touch pointer anymore. It is invalid. Now, it's still going to be a number. It's still going to be a pattern of bits, but it's invalid. And you'll very often get a segmentation fault if you tempt fate in that way. So I can't free the pointer and then use it literally the next line. The solution here, kind of like our swapping of the liquids last time, was to maybe just have a temporary variable. So I can do a switcheroo. And so a common way to solve this problem to get the order of operations right would be to do something like this. Give yourself a temporary pointer like node star next. Set it equal to the place you want to go next. So one step ahead. Now you can free pointer. And then you can update pointer to be that next value. So essentially, you need like two hands now. You create on line 41 another pointer that if this is pointing at the first node, the 3, your new pointer is pointing at the 2 temporarily. So now you can tell malloc via free, release this memory, but I haven't forgotten where I want to go next. And so I can now continue on. So a common paradigm for just iterating over these nodes and then freeing them. A couple of observations. Strictly speaking, I could have consolidated this. I don't need 2 loops to print the nodes and then free the nodes. I could do that all at once, but let's assume that there's other stuff of interest in my program, and I don't want to just immediately free it. There's one other bug that I should probably address here. There is still a potential memory leak up here, and this one is super subtle, though Valgrind would help you find it. Notice that in this loop here, when I'm calling malloc, this line of code is fine if the first line of malloc fails and returns null, because I immediately return and I'm done. But what if the second call, but not the first, or the third call, but not the first or second fail? This line of code has me returning immediately. You really need to do some garbage collection, so to speak, whereby you really need to go in and free any nodes that you did allocate successfully earlier. Honestly, that's going to be a pain in the neck. We won't do that here. But probably what I'd want to do is write a function called freeList or something like that, and call that function to free any nodes I had previously created. So it's not quite at the finish line, but the building blocks are indeed here. Questions on this code? And I think it's safe for me to promise that it won't escalate further from that. Questions on this? No? Well, let me show you one alternative that you might prefer. And I'm pretty sure this isn't an escalation. It's just an alternative formulation. Another way you can iterate over nodes in a list could be this. Instead of a while loop, for instance, let me actually show you one other piece of syntax here. You could technically use a for loop. You could give yourself a node pointer here that is initialized to the list. You can then check in your for loop that it's not equal to null. And then you can do your update as usual like this. Either of these are equivalent, even though this one I suspect looks scarier. It's doing the exact same thing in one line instead of 2, but there's no reason we can't use for loops instead of while loops to achieve the same idea. But I'll leave these two as demonstrations of one approach or the other. But that's just like in week 1, for loops, while loops, whatever looks simpler to you, even though admittedly neither of these probably looks super clean. All right, so let's take things back to things more conceptual here. Up until now, we've been inserting elements into this linked list by prepending them. Let's consider what the running time then is of these operations. So if I've got a linked list of size 3 or size n more generally, time has passed and I've added a lot of things to it, what's going to be the running time, for instance, of searching a linked list for some value? And I'll tell you already, it's not log n, because again, binary search is off the table as per before break. So what might the running time be of searching a linked list for some value, like 2 or 3 or 1 or 50? What might the running time be? Oh, O of, I heard it over here, O of n, and y. Who was that? Oh, in the middle here? Why O of n? Exactly. You're going to have to go through every item in the list, starting from the left, from the beginning, which is how we've been drawing things and connecting the dots. And in the worst case, the element might very well be at the very end, so it's going to be big O of n. What about insertion? How many steps in terms of big O notation has it been taking me to insert elements into the linked list using this prepend design? Yeah, so it's technically constant time, big O of 1. And again, 1 is just representative of any constant. It could technically be 2 steps or 3 steps or even 10 steps or 100 steps. But if it's always finite and fixed, then indeed you can say it's in big O of 1. Now, why is that? Well, again, no matter how long this list gets, so long as there's memory available for me, I can just kind of create a little splice at the beginning of the list to put in the new node, update the original list, and I'm on my way. And it keeps getting longer, even though it might not be spread out in memory. So big O of 1 is possible with these linked lists if I indeed prepend things. Of course, if I prepend things, everything's going to get out of order, potentially. And we're going to have maybe the stack property instead of a queue property. So we might want to do things slightly differently. So instead of doing this, whereby we kept prepending, 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 suppose we append to the end of the list instead. So if we now insert the 1, the 2, and the 3, as we might want to for a queue to maintain that fairness property, we might start with an empty list. We might add the 1. We might append the 2, append the 3, and so it just is sort of laid out differently in memory. And again, if I can come to you in the middle, what's the running time of search? Again, when the linked list uses this append implementation. Yeah, still big O of n, because in the worst case, you're going to have to go through the whole list just to find it. And notice, it doesn't matter if you have an intuition now that the bigger numbers might very well be at the end. You have no way to jump to the end. You have no way to jump to the middle or do anything resembling binary search. Every search has to start from the left and follow the arrows again and again. All right, so I don't think we've done any better there. And in fact, what is insertion's running time now in big O? When we're appending to the list in this way, as we might to implement a queue instead of a stack. What's the running time of inserting a new value? Big O of? So not big O of 1 in this case, but big O of n, because if I'm appending, by definition, I have to start here and traverse the whole thing looking for the end. Now, this is a bit of an overstatement, right? You could obviously optimize this slightly by maybe adding another variable that always points to the last element, sort of a cheat sheet, a shortcut that gets you all the way to the end. That's totally fine. It doesn't really fit the traditional definition of a singly linked list, but there's absolutely smart engineering solutions to these kinds of problems. But as designed, it would indeed be big O of n to insert to if you've got to go all the way to the end and you're not using a little extra memory to get yourself there quickly. Well, what if we want to take things one last step and not just append blindly? Because even though I inserted 1, 2, 3, if I inserted them in random order, they would end up in random order. What if you want to maintain a sorted list from smallest to largest? Well, then you might want to insert numbers like this. Starting from an empty list, we might have a 2. Then we might try inserting a 1, but we want to keep it sorted. So now we're going to prepend in our code. But then you might want to insert a 4. So you would append the 4, because you're probably going to look for the right spot to insert it. Then we're going to insert a 3. And this one's getting a little annoying, because now you have to iterate over the list, look for the right spot, and then do a little smarter of a splice. But it's possible. But you don't want to orphan the 4, for instance. And then ultimately, we get back to this question. What would the performance be of your linked list if you're trying to maintain sorted order? Well, search, I think, is going to be big O of n for the same reasons as before. What about insertion? Big O of what? For inserting into a sorted linked list. Yeah, in the worst case? Yeah, it's still big O of n. So it's no worse than, but it's not really any better than appending. But we gain the additional property of maintaining a sorted list, which might very well be useful if you're sorting your contacts in your phone or something like that, where it just makes sense to maintain sorted order. Now, in the code for online today, if you take a look at some of the final versions of code, like list6.c and list5.c, as we'll post on the website, you can actually see code that will solve all 3 of these problems. The prepend version that we wrote live, the append version, which we talked through, as well as this sorted order one. But I think I'll avoid showing it live just because I do think that starts to escalate quickly. But I think we have enough of a building block, if we're comfortable with prepending, to at least solve some real world problems with these linked lists. Questions then on linked lists, which we'll now leave behind on their own, but now use this technique to solve fancier problems, but much less code. Questions on linked lists? All right, so to recap, we've kind of taken a sidestep with linked lists. Like we have this dynamism now where we can grow and shrink our chunks of memory without over-allocating or accidentally under-allocating, as in the world of an array. We don't have to worry about copying values endlessly, because once you allocate the node, it can just stay wherever it is in memory, and you can just maintain, you can just stitch it together somehow. But unfortunately, we've sacrificed what we started the class with in week 0, which was like binary search, divide and conquer, which was like gave us that log n running time, which was really compelling if you think back to the demonstrations and the visuals. Can we get the best of both worlds? Can we get the sort of speed of binary search, something logarithmic, but the dynamism of something like a linked list? Well, we can actually, I think, if we start to think not in a single dimension, just the x-axis, if you will, but 2 dimensions, such that our data structures can maybe now have width and height, if you will. And so a tree is perhaps the right term here, much like a family tree. If you have sort of your elders up here in the tree and then the branches below them for their children and grandchildren and the like, that's actually what a computer scientist means when they talk about trees. Not a tree that grows up like this, but really one that typically is depicted growing down, although this is just an artist's depiction no matter what. But there are certain types of trees in the world called binary search trees that are structured on paper and visually like a family tree, but they have a special property that lends themselves to exactly that feature, binary search. So for instance, here is an array back from week 2, and I've sorted a whole bunch of numbers herein from 1 to 7. We know we can do binary search on this structure if it's implemented as an array, but what feature do arrays, to be clear, not have that linked lists do? Today's kind of a seesaw. Like, what did we just gain by adding linked lists that arrays do not allow? Yeah. Yeah, you can insert more elements without having to copy or moving everything else around. Like right now in this single dimension, if these values to the left and or right are already used, then you have to move everything. And that's where we started today's story. So arrays kind of paint you into a corner because you have to, by definition, decide in advance how big they are. Well, couldn't we have some kind of array that can still grow but still is contiguous so we can do binary search in some way? Well, yes, if we sort of rethink how we implement binary search. Let me propose that I've chosen these 7 elements in the array, much like the lockers from week 2, to be ordered from smallest to largest. I've highlighted now in yellow the middle elements here. And if we were telling the story of week 2 going left or going right, let me highlight in red the middle elements of the left half and the right half. And then let me further highlight in green the other elements in between those. And there's actually a pattern here, as you might notice, whereby there's 1 yellow in the middle, and then there's the 2 red and the 4 green. There's kind of an implicit structure there, if you will. And what if I do start to think in 2 dimensions, and instead of laying out an array of lockers like this on the x-axis only, what if I kind of like slide the 4 up and pull the 1, the 3, the 5 down, and kind of draw this in 2 dimensions instead? Well, let me do that as by separating these things like this, such that now let me propose that each of these squares, maybe it doesn't have to be contiguous. It can be anywhere in the computer's memory. But I can't have these crazy gaps among them. How could I perhaps keep these things connected conceptually? What should I add to the picture, if you will? Yeah. Say again? So branches, metaphorically here, and more technically in the language of C, maybe just some arrows, some pointers. So I won't bother drawing things as rectangles constantly. Let me propose that we're now just abstracting away what a node is. But let me claim that each of these squares now is a node. And a node might have a number, but it might also have a pointer. Heck, maybe even 2 or more pointers. And let me draw those now. I don't care about addresses like 0x1, 2, 3, 4, 5, 6, 7, 8, 9 anymore. Let's just draw our pointers with arrows. But now let me propose that we could very well think about this as a tree storing what was previously array data, but now each of these nodes can be anywhere in memory. And moreover, even though I've kind of painted myself into a corner visually on the screen, so long as there's more memory in the computer, I could put the number 0 over here. I could put the number 8 over here. And if I'm smart, I could probably, if I want to insert other numbers like 2.5 or 1.5 or values in between, I bet we could kind of make room by swiveling things around and just kind of hanging things things off of these branches slightly differently. And so what does this gain me? Well, if I instead start to model my data not single dimensionally, but in 2 dimensions, and I connect those nodes with these pointers, what can I now do? I think I just gave myself back binary search. Why? Suppose I'm searching for the number 5. How do I find it? Well, just like in a family tree where you might visually start reading from top to bottom, I'm always going to start from the so-called root of a binary search tree. This is just like the list pointer that kicks off the whole linked list process. This is the so-called root. All right, here I am at the number 4. I want to find the number 5. What decision can I make when I see that I'm currently at the number 4? Just like the phone book from week 0. Where is 5 not? It's not to the left. And if I had built a little mobile here or something, we could very dramatically snip off this branch. This is like very low budget animation. These nodes could like fall to the ground, and we're left with half of essentially a tree. But what do I now know? It's obviously the 5 to the right. So let me go to the right. 6 is obviously not the one I'm looking for, but what do I now know about the 5? Well, 5 is less than the 6. So I can sort of snip this off here because I know it's not going to be down there, and I can follow the remaining arrow here, and voila, I just found it. And now without getting into the weeds of the math, I've got here, 7 elements. That's roughly 8 if I round up. And if I do some log base 2, 1, 2, 3 is the key detail here. The height of this tree is 3 because I took a list of size 7 and I halved it and I halved it in order to let it dangle in these 2 dimensions, plus or minus 1 for rounding's sake. So what do I get back? I now have binary search, but it's not like the middle of the middle of the middle. I now follow these arrows in one of 2 directions. So each of these nodes now has an int and maybe a left pointer and a right pointer, but you could call them anything you want. And so I've gotten back binary search and dynamism, because if you want to add 0 or 8 or 9 or 10, we can just dangle them at the bottom of the binary search tree. So what would this look like in code, but we won't actually implement it line by line? Well, here was previously our definition of a node for a linked list, which was one-dimensional, if you will. Even though it might bounce up and down on the screen, it was still just a line, if you will. Well, let me get rid of the single pointer in the linked list. Let me make a little bit of room here in this type def, and let me propose that we just add 2 pointers, each of which is a struct node star. One will be called left by convention. One will be called right by convention. And so long as someone, not me, not today, not in class, writes the code that stitches together this data structure too, handling both the left child and the right child, so to speak, I think we can indeed stitch together that 2-dimensional structure. And moreover, once you have this in memory, you can translate pretty elegantly to code binary search itself using a principle we talked about recently too. Here is, for instance, a function that I'll write by just clicking through steps called search, whose purpose in life is to return a Boolean, true or false. The number I'm looking for is in the tree. This search function, therefore, takes 2 arguments: the number I'm looking for, called number, and then a pointer to the tree, the so-called root of the tree. Now, how can I implement binary search in code? Well, recall our brief discussion of recursion. It turns out recursion is a beautiful technique, and honestly, more obvious technique when you have 2-dimensional structures, which finally, after 5+ weeks, we now do. Here's maybe my first line of code here. If the tree is null, then obviously return false. You've handed me an empty tree. There's nothing going on. Obviously, the number you're looking for is not going to be here. So that's my safe base case to make sure I don't screw up and recurse infinitely. Well, what else might be the case? Well, if the number I'm looking for is less than the tree's own number. And now recall that tree is a node star. So even though I'm calling it a tree, it's really the current node that's been passed in. So if the number I'm looking for is less than the current node's number, then I must know that the number I'm looking for is to the left, so to speak. So how can I solve that? Well, this is where the magic of recursion. Just return whatever the answer is to calling search again, but on a subtree, if you will. This is the sort of equivalent of snipping off half of the tree. Pass in the left subtree, if you will, with the same number. Else, if the number you're looking for isn't less than the current node's number, but greater than, snip off the other subtree instead and just return whatever search says it finds in the right subtree here. And then there's a 4th and final case. What else could be true logically? Yeah? Perfect. If the number you're looking for equals the number in this node, then I'm just going to return true. And you might recall from our recurring discussions of design, I don't strictly need to ask that explicitly. Either there's no node, it's to the left, it's to the right, or you found it. So I can just whittle that down as usual to an else. And this now returns my true. So here too, this is where recursion, once you get comfy with it, sort of gets pretty elegant and cool in the sense that, wow, even though there's a lot of lines here, I mean, there's only a few interesting lines. A lot of it's like curly braces at that, which strictly speaking, I could get rid of. And so recursion lends itself to elegance when it comes to traversing these two-dimensional data structures as well. So that is in code how you might implement something like search. Questions then on these trees? We have dynamism. We can insert more nodes to them. They're faster because we get binary search back. But there's got to be a price paid. Any downsides or question or downside? OK, let me come back to that in just one sec. Downside, though, what price have we paid for this dynamism and for this binary searchability? Even though I've abstracted it away in the picture. Say again? We're using a lot of memory, right? I'm kind of misleading you now because I'm just drawing these little squares with the simple numbers. But there's actually 3 things in there: a 4-byte integer, an 8-byte left pointer, a 8-byte right pointer. So we're already up to 16, 20 bytes now to store individual ints. That's probably OK, though, if memory is relatively cheap and voluminous as it nowadays is. But these are the kinds of trade-offs. And here, too, you see a hint of why some people still do like and use C. And in fact, it's so omnipresent because when you have C, you can really fine-tune how much memory is being used, for better or for worse, under the hood. As we transition soon to Python, these decisions get made for you. And you have much, much less control about how much memory is being used by your program because someone else made those design decisions for you. Question? Is it bad if we don't know the parent node? Not necessarily. There's no reason why you need to have pointers in both directions. However, that can lend itself to efficiency. By spending more space and having arrows go up too, you can actually save more time when searching the tree in other contexts. This, though, would be the canonical way, the typical way to implement it. But absolutely, just like a doubly linked list, that could help you solve other problems too. All right, so turns out I'm kind of overselling binary search trees. There are perversions of them, so to speak, whereby they won't actually behave as advertised. For instance, here's a good situation. Suppose you've got an empty tree initially, and you insert the number 2. Well, it's got to go somewhere, so it might as well become the root of this binary search tree. And let's assume that someone wrote the code to do this. Now you want to insert the number 1, and you want to maintain the searchability of this tree. Well, it's important to note that binary search tree is different from tree. If you've just got a tree in memory, there is no social contract with where the numbers need to go. They can be completely random all over the place. Binary search tree means that you can do binary search. Means that any node here is going to be greater than every node here and less than every node here. And that's a definition. It's a recursive structural definition that must be true to be a binary search tree, or BST. So if we maintain that property ourselves, let me insert 2. Let me insert 1. 1 belongs there by that definition. Let me insert 3. 3 belongs there by that definition. But I kind of got lucky in that I, in the story, inserted 2 and then 1 and then 3. Let me propose a sort of perversion of the algorithm whereby we just get unlucky. Let me propose that we insert 1 first. And then we insert 2. Well, where does 2 go? Well, logically, it goes to the right because it's larger. All right, now the user inserts 3. Where does it go? OK, it goes there, logically. And how does this story unfold? The user inserts 4, 5, 6. It's wonderfully sorted in advance by luck. But this is a perversion of the structure in what sense? It's still technically a binary search tree. But what does it look more like? It really is devolving, if you will, into a linked list. And so if you, the programmer, don't implement a binary search tree with some kind of repairs going on, such that as soon as something gets, whoa, a little too long and stringy, I think I can fix this. It's going to be an annoying a number of lines of code, which we're not going to write here or in a p set, but we could kind of pivot this thing, right? And we could just rejigger things so that the 2 becomes the new root, the 1 becomes the left child, the 3 becomes the right child. But that's what, like 2, 3 plus lines of code. It's possible, it's doable, but it's extra work, it's extra code. So unless you write that code, though, and maintain balance of these trees, just because it's a binary search tree does not mean its height is going to be log base 2 of n. The height could be n, in which case you don't get those properties. So when it comes to looking up in a balanced binary search tree, yes, it's log n. But if it's unbalanced, if you don't add that additional logic and those repairs, so to speak, it could devolve into big O of n. And this is a whole category of algorithms and fanciness that you would explore in a higher level course on algorithms and data structures. There's lots of way to do that sort of fixing that I'm alluding to in the picture there on the screen. All right, a few other data structures, if you will, toward an end of a sort of computer science holy grail. So log n is repeatedly a really good place to end up. We started in week 0 when we got log n. We lost it earlier today by introducing linked lists, but we just got it back, albeit at the price of spending more space. But the holy grail, so to speak, when it comes to algorithms would not be big O of n, certainly. Definitely not n squared, like our bubble sorts and selection sorts, and not even big O of log n. What's better than all of those? It's big O of 1, constant time, right? That's the holy grail, because if we could store huge amounts of data but find it instantly in 1 step, or 2 steps, or heck, even 10 or 20 steps, but independent of the size of the data structure, that's pretty powerful. I mean, that's the secret sauce of the Googles and the Twitters of the world, trying to get back results really, really fast. Well, it turns out another abstract data type or abstract data structure might be something called a dictionary, just like the Merriam-Webster or Oxford English dictionaries that you might know, which associate, say, words with definitions. Well, you can think of a dictionary really abstractly as this, like 2 columns, maybe on a spreadsheet of sorts, where the left column represents something and the right column represents something else, like the word is on the left and its definition is on the right. And that's almost literally what a dictionary is on paper. You've got all the words and all the definitions right next to it. But more generally, in computing, a dictionary really just has not words and definitions per se, but key value pairs. This is a term of art, and we're going to see this again and again, especially as we transition to web programming, keys and values. Key is what you use to look for something. The value is what you find ultimately via that key. So that's the generic term there. We've seen key value pairs really in the past. In week 0, we talked about your contacts in your iPhone or Android phone being an app that has a whole bunch of contacts, presumably alphabetized by first name or last name or the like. Well, one of those contact cards ultimately has someone's number, for instance, like John Harvard in this case. So in that type of application, the keys is the name, like John Harvard, that you use to find information, and the value is the number that you find there. Or if there's more information, like where he lives and email address and the like, the whole contact card could be the value thereof. The key is what you use to look up John Harvard. Now, back in week 0, and rather, the corresponding table then, if we draw this in 2 columns, wouldn't be word and definition or key value generically. It would be name and number, for instance. So we're just slapping some new terminology on this old contacts problem. Well, this is the picture we drew way back in week 0, whereby I claimed that log of n was really, really good. And indeed it was, and has been since. But the holy grail would indeed be something more like this, in this dashed green line, constant time. And maybe not literally 1 step, but a fixed number of steps that even as the problem gets huge and you go way, way out on the right of the x-axis, the problem does not depend on the the time to solve the problem does not depend at all on the size of the problem itself. You can have 1,000 contacts or 100,000 contacts. Constant time means it takes the same number of steps no matter what. Well, how can we get to that point? Well, there's a couple of final building blocks today, and there's one called hashing. And this is something that will recur a few times, but for now, hashing is all about taking as input some value and outputting a simpler version thereof. So for instance, here's a gratuitously large deck of cards, which are all the more visible as a result. And in a deck of cards, typically you've got like, what, 52 cards, plus maybe the jokers and whatnot. And each of those cards has a number of sorts and a suit on it. And here are literally 4 buckets on the stage. And how might I go about sorting these cards? Not just by number, but also by suit. Well, you could certainly like spread them all out and sort of make a mess of things and just kind of reason your way through it and get everything in order according to suit and ordered by number. But most of us, even if you don't have 4 buckets at home, probably are going to do something a little more intuitive, feels like an optimization, where if I find like the 9 of hearts, I'm going to put that into the hearts bucket. The king of spades, I'm going to put that into the spades bucket. The jack of diamonds over here. And I'll do this with the queen of diamonds and the ace of clubs here and the 3 here and the 10 here. And even though it's still going to be 52 steps, why am I, and maybe at home, like why would you perhaps do this step first? What's the value of bucketizing the values in this way? And that actually is kind of a term of art. What's the value of doing this first before you sift through and try to sort the numbers? Yeah. Yeah, it's easier to make sure you're not missing anything. And it's taking a problem of size 52 and shrinking it into 4 problems of size 13, if you will. And so that just kind of helps simplify things, maybe reduces the probability of errors or the like. And what I'm doing here, to give it a technical term, is that I'm hashing the values. I'm taking as input a card like this, and I'm reducing it more simply from a larger domain to a much smaller range, if you will. So here's a domain of like 52 possibilities. I want to map that to a range of 4 possible outcomes: the diamonds, the clubs, the hearts, or the spades here. And by doing that, I'm just shrinking the size of the problem. So hashing does that. It's like literally an f of x type arrangement, whereby you pass something in and you get back a simpler known value. Well, a hash function, more technically, is the algorithm or even the math or even the code that implements that idea, converting something bigger to something smaller to this indeed finite range of values. And it turns out that hash tables are a wonderful application of arrays and linked lists to try to leverage the best of both worlds. The goal being theoretically to achieve that holy grail of constant time. And that's going to be a bit of an overstatement because you're not always going to achieve it exactly, but at least we can get a little closer there too. So with hash tables, you have something that looks like this. This is just an array. This is an artist's rendition of drawing it vertically instead of horizontally, but that's just a detail graphically. And this array, for instance, maybe is of size 26. And where am I going with this? Well, how does Apple, how does Google store your contacts alphabetically in your phone and search for things quickly? Well, they probably alphabetize, at least in English, according to A through Z. Or if we convert that to numbers, it's like, what, 65 through whatever. Or really, 0 through 25 suffices. If we're using an array of size 26, we start counting at 0, and we count up to 25. But let's abstract that away as just letters of the alphabet. So maybe what Google and Apple are doing in your phone is storing all of the A's up there, all of the Z's down there, and everything else in between. And so this works pretty well if you start adding your friends and your family. So for instance, and I'll get rid of the letters so as to not distract, Albus might go in that first spot because A, you subtract the 65, maps to 0. So we put him in the first bucket, the A bucket. Maybe Zacharias ends up all the way at the end there. And then in the middle might here be Hermione. And if we do this dot, 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 you keep adding all of your classmates, you might get a contacts database that has all of this data herein. Now, each of these nodes, they're drawn differently because this is just another artist's rendition. These rectangles, these long rectangles, represent a contact card, like John Harvard's that's got the name, maybe email, definitely phone number, and things like that. So this seems great. Why? How can I find Albus? Well, I go to the A bucket. How do I find Zacharias? I go to the Z bucket. How do I find Hermione? I go to the H bucket. But, I've done this very deliberately. What problem will arise eventually, assuming you have enough classmates? Yeah, there'll be too many people, too many contacts for all of the available spaces in the array. There's still some room here, but I'm pretty sure if I think back to this particular class, we've got not Hermione, but also Harry, who's also an H, Hagrid, who's also an H. So where do I put them? I could just put them arbitrarily in any of the open spots, but then you lose the immediacy of jumping right to the H, right to the A, right to the Z. But now that we have linked lists, we can kind of combine these ideas, right? Use an array to get to the first letter of the name you care about. And then if you have a collision, so to speak, whereby someone's already there, you don't do something stupid like put Harry down here just because it's available, or maybe Hagrid down here just because it's available, because then you're losing the immediacy of the lookup. Why don't you just kind of stitch them together in a linked list? Now, what does this mean? This means for most of the characters here, you have constant time lookup. You look up Albus, boom, you're done. Zacharias, boom, you're done. OK, Harry, Hermione, Hagrid, it might be 1, 2, or 3 steps. So that's actually devolving into something linear. But here we make a distinction today between theoretical running times, which we keep talking about, and honestly, clock on the wall running times that actual humans care about. This is way faster than a linked list, because you don't have to search every name. It's even faster than an array, because you don't need to do binary search. You can literally, for most of the names, find them in constant time, 1 step. And again, it's not theoretically constant, because if you only befriend people who have H names, it's going to be a crazy long linked list anyway. So again, it really kind of depends on what the nature of the data is here. But this is pretty close to constant time. And in fact, how could we get even closer? How could we reduce the probability of collisions for the H's or any other letters? How could we avoid putting too many H names together? Say a little louder. OK, yeah, so we could add another dimension, if you will, but let's not add a third dimension per se. But let's indeed look at not just the first letter of everyone's name, but the first and the second. And in fact, let's see if that gets us a little further along. So let me go ahead and propose, if you go through the whole Harry Potter universe, there's actually a lot of collisions if we keep going. And so we've got the L's here, the R's, the S's, and so forth. Well, let's clean this up here. Hermione originally went to the H location, but let's decrease the probability of collisions there and everywhere else. Instead of putting Hermione, Harry, and Hagrid all together, let's go ahead and do this instead. Instead of labeling these buckets A through Z, let's just give ourselves more buckets. So in fact, this might be H. Well, instead of H, maybe this should be HA. And then this should be HB, HC, HD, HE, HF. Now, some of those are a little nonsensical, because I can't think of names that match most of those. But it's deterministic. At least we know the bucket will be there, which is important even if it's empty. And now we can put Hermione here. We can put Harry here. But uh-oh, we didn't do this perfectly well. Hagrid still collides. So let me come back to you. How can we reduce the probability of Harry and Hagrid colliding? Yeah, so we could look at the third letter. OK, so let me try that. Instead of HA, let's look at HAA, HAB, HAC, dot, 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 HAQ, dot, 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 HEQ, HER, HES, and so forth. And now I think those names, and probably all of the others we saw, are now much more cleanly distributed. There's much lower probability of collisions, unless two people have like almost the same names, or one is like a prefix of the other. But, even though we're now closer than ever to constant time, because the odds that we hit a collision and have to devolve to a linked list are much lower, what's the downside? That's not completely obvious from how I've depicted this on screen. What's the price I'm paying here? Yeah. This is a huge amount of memory. The number of cells here in the array is now, what, 26 times 26 times 26 for the first, the second, and the third possible characters, all combinatorically combined here. That's a lot. I didn't even draw them. I have the dot, dot, dot to evoke that instead. That's a huge amount of memory. This is a very sparse data set now, and odds are you're going to waste so much memory, even for the names like HAE, HA, like HEQ. Like, I can't even think of names. So many of those buckets are going to be empty, not to mention the AAA and the ZZZ and everything else in between. So it's a trade-off, and it might be too expensive a trade-off, and so you might have to tolerate something like the collisions we had earlier, whereby even though they might very well happen, at least you are decreasing the probability by perhaps having more buckets like this. And in fact, if I rewind now to where we might have gone with this, here's how we might represent these nodes in the tree. Previously, in the past, we've had a person who had a string name and a string number, aka now char star. And so here now might be how, in this hash table, we represent someone's name and number, as well as a pointer to the next element in the list. Let me rewind just to the picture here. We keep drawing different shapes because, again, these are abstractions. Who really cares if they're to scale now? We've got enough room for the person's name. Not pictured on the screen is Hermione's number, but that's somewhere in this rectangle. But yes, pictured here in this little square is a pointer to the next node in the list. So by storing name and number, maybe her address, maybe her mailing address, whatever, in addition to a pointer, allows each of these nodes to be connectable, just like the nodes in a linked list. But where they're starting is in an array. So the array gets us like 1/26, or gets us narrows the problem from size 26 to 1, gets us to the linked list in question. Hopefully it's a single person, or perhaps it has more than that. Meanwhile, what is the hash table itself? The hash table, the whole thing, is literally just an array. I've hard-coded the simplest version of size 26, but what do each of those boxes in the vertical array represent? Just a pointer to potentially a node in a linked list. And if there's no one there, if there's no one in location y or x or the like in that universe, well, it's just a null pointer, signifying there's no one there. But if there is, it's going to be a pointer to a valid node, from which we can get to any of the others as well. And that so-called hash function, just like the one I did with the greeting cards, well, it's just a black box, if you will, but implemented somewhere in code, like in C. And so if you pass in albus, what is the hash value of albus? Well, in the first version of the story with 26 buckets, it should be a 0. If you pass in Zacharias, it should be 25. And so just as my cards were being hashed to one of 1, 2, 3, 4 values, now these names are being hashed to one of 26 possibilities, or 26 times 26, or 26 to the third power, if you have more and more granularity than that. Questions on this implementation now of this idea of a hash table? If you say that again with the null? Oh, a good question. So if there's so much sparseness, there's all of these empty cells in the array, couldn't you just go in and free them or delete them or just kind of shrink the array and not have AAA and AAB and AAC only have the prefixes, 2 or 3 characters that you need? You absolutely could do that. But now what you lose is the arithmetic benefit of being able to map each letter to a number. If you start freeing up unused space, you don't know that Zacharias is necessarily at location 25. Albus is still going to be at location 0, but if you've deleted some of the elements in the middle, Zacharias could be at 24 if you've deleted one, 23 if you've deleted another. And so you don't have that arithmetic immediacy that you need in order to index into the array with constant time. And the same is going to be true if it's 2 letters or 3 letters. You need to be able to trust that you can do some quick math and jump to the right index in constant time. And that's, again, the appeal of these arrays. So when it comes to the running time of a hash table, inserting values into it, searching for values therein, at the end of the day, it technically is big O of n, because in the craziest case, you might have a huge, fancy hash table, but everyone in the universe has a name starting with H. And then it just evolves into a really long linked list, just like a binary search tree could do the same. But if you choose a smarter hash function, maybe you mitigate that and you don't rely only on the first letter, but on the second or the third as well, or some other combination of that input, and make your hash function smarter. Odds are, if you get a good hash function, you want to get it to be more of like order of n divided by k, where k means constant mathematically, and so k is the number of buckets. So ideally, you want like a uniform distribution. You want like this many people here, this many people here. You don't want there to be some or no people. You want a uniform statistical distribution. And maybe you get that from human names, maybe you don't, but that's kind of the challenge of a hash function. Of course, big O of n over k is not a thing, because we always throw away constants like k, so it's still big O of n. But again, the distinction today is that, OK, yes, academically, you learned in CS50 that, sure, it's big O of n. But my God, it's 26 times faster if you do the hashed function well and you spread everyone out over the hash table. And that's the appeal of these kinds of structures. And we've got one more for you, if I may, and that's something now known as a trie. So it turns out that a trie is even cooler, if you like this kind of thing, in that it does not devolve into big O of n. It is truly constant time. But there's going to be a price. There's going to be a gotcha. A trie is sort of a fancier tree. And it's short for retrieval, but pronounced trie for weird historical reasons. But a trie is a tree, each of whose nodes is an array. Right? So this is all like crazy mashups now. People started inventing data structures just by combining different ones. So unfortunately, a lot of the good ideas are taken, but you just have benefits from certain aspects of those data structures, and combining them ideally gives you the best of both worlds, so to speak. So here might be the root of a trie. It's literally a big node, a big rectangle, but it's actually an array. So there's like 26 locations in this picture here. And here's how you use a trie, for instance, to store names just like the hash table. You treat each of the elements of that array in that node as like a letter of the alphabet, so A through Z, or 0 through 25. And if you want to store someone's name in here, you do so as follows. If you want to store like an H, you index into the H location. And if you want to store the second letter of someone's name, like an A, well, you add another node below it, and such one is connected to the other. And you then identify the A in that array. And then you go on and maybe put a G, if the goal is to store, spoiler now, Hagrid in this data structure. And then the R and the I and then the D. But when you get to the D, the end of the name, you have to somehow flag that this is the end of a name that we've embedded into this data structure. So whereas all of these are called out in white just to make obvious what we're connecting to what, green has to be like a bool that's true, that just indicates like the buck stops here. Like D is the last letter in someone's actual name. And what's kind of cool now about a trie is that we can repeat this for other names as well. So for instance, here's where we might put Harry as well. And notice they share a common prefix, HA for Hagrid, HA for Harry. So we're reusing some of these nodes, some of these arrays. We can even slip Hermione in here too, borrowing only the H, but she gets the H, then the E, then R, R-M-I-O-N-E, and so forth. And we mark at the end of her name too that she's in there. Now, what's the takeaway here? Well, what is the running time of a trie? How many steps does it take to find someone in this data structure? And let me zoom out so that it sort of suddenly becomes a massive data structure with even more in it. Maybe it looks, sorry. No, I'll keep it on this one. Maybe it looks a little something like this with just these three names. But how many steps does it take to find Hagrid or Harry or Hermione? No matter how many names are in this data structure. There's 3 at the moment, but it takes what? H-A-G-R-I-D. So 6 steps to find Hagrid. H-A-R-R-Y. 5 steps to find Harry. H-E-R-M-I-O-N-E. 8 steps to find Hermione. But notice that those steps are only dependent on what? The lengths of the humans' names. And let's assume that no one's going to have a infinitely long name. It's going to max out at what, like 8, maybe 18, maybe 20, 30. There's actually some pretty long human names out there, but it's going to be finite. You know it's bounded, whereas most contexts, n could grow forever. So what's compelling here is if you assume that the longest name is, I don't know, 50 for the sake of a theme here, then you know that finding anyone in this data structure will take you no more than 50 steps. 50 is thus a constant, which means you have big O of 1 running time. It doesn't matter if there's 1 million people in this phone book or 1 billion people in this phone book. That's going to definitely add more nodes to it, but it's still going to take you H-A-G-R-I-D, 6 steps to find Hagrid, H-A-R-R-Y, 5 steps to find Harry, even if there's 1 billion other people in that data structure. So now we actually do seem to have constant time if you assume that there's going to be a bound on the length of the name. Why don't we use tries for everything then? What's the price we're paying for this data structure, even though we've represented just 3 characters here? Yeah? It's a lot of memory, yeah, and you can see it even with these three names. Most of the squares on the screen are empty, like bytes and bits that are there and are allocated, and they need to be there because you need to be able to do that arithmetic thing of this being 0, this being 25. So you can jump from boom, 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 boom based on each of the letters. But it's a hugely sparse data structure, which means it takes up a crazy amount of memory. Now, maybe that's tolerable, especially for short names, but that's going to be the trade-off as well. And this is such a tension in computing. Almost any time you want to improve time, you want to speed up the efficiency, the speed of your algorithm, you're going to spend space. If, by contrast, you want to decrease the amount of space, you might very well have to increase the running time. It is indeed this seesaw back and forth, and you, your colleagues, your company need to decide what resource is the most precious. Heck, it might be just much harder to code one of these data structures than another. You're a human. Your time is valuable. Do you really want to spend hours implementing a trie when, hey, in 30 minutes I can bang out an array nowadays, or a linked list even? There too, development time is going to be yet another resource, and why sometimes there's good code or bad code, it depends on what you're prioritizing. So what do each of these nodes look like in a trie? Well, we can keep calling it a node. This is a very generic term for just a container in these data structures. In this story, though, let me claim that everyone has a number, like a phone number, a string, aka char star. Every node has 26 children, or technically an array of size 26 that can point to more of these nodes. Notice that I don't need to store the name of someone in a trie because it's implicit in the path that you take to find them. So that's a minor optimization, but it saves us some space. But this would be just a different data structure we could use to actually solve this problem as well, albeit at a very expensive cost. And what do we need our variable to be that stores the trie? Just like before, we just need a single pointer that hangs on to the root of this structure that's null if it's empty, or non-null if it's actually pointing at something. Any questions then on tries? And if it's feeling like a lot, the fire hydrant, it is. We started with arrays, then linked lists, then tries. But questions on how we've just assembled from these basic building blocks? Yeah?
Why isn't the root of try have a size of 26? Why isn't that an array?
A good question. Why is this not size 26? It's just like with the just like with the linked list before. It just tends to be in code convenient to have a separate additional pointer that's small that just points to the beginning of the data structure, because that way it can be null, thereby clearly indicating there are no nodes, the whole structure is empty. If you allocated one of those nodes, you absolutely could, but then you'd be just wasting space even if it's empty, and it creates an ambiguity. So just having a single pointer linked to the beginnings of all of these things is a good thing. Other questions now on tries, or trees, or hash tables, or arrays? So what problems might arise? Well, here's a counter example. What names are manifest in this trie here? Feel free to just call it out. What do you see? Danielle and Daniel. So presumably, if these are two names here, one of which is a prefix of another, notice that the data structure still works. And I chose, a friend's name and then appended a couple of more characters to it that's also a name, because we have here D-A-N-I-E-L, and the green technically is implemented as a bool or something like that that indicates a word stops here. But we don't want to preclude storing Danielle as well, who's a superstring, if you will, of Daniel. And so that's OK too, so long as the structure allows for the pointers to keep going. So even that works out OK, whereas it might not have otherwise. And in terms of the running time, just to be clear, at the end of the day, tries do give you actual constant time for insertions, lookups, deletions, and the like, because it's dependent only on the length of the input, the key, if you will, and not on how many other people are in your phone or address book. And now thought we'd conclude with a visual. If you've gotten out into the square, anyone recognize this? OK, Sweetgreen, a local salad place. What are we looking at here, and what's its connection to today? You're about to become all the geekier in the real world, because you will start to see data structures everywhere. What is this? Or how does this work maybe in salad form? Who's been to Sweetgreen? OK, either of you. So how does this work? OK, good. So if you order a salad for someone named L, when it's ready, they put it in the L section here. And so this is kind of a set of key value pairs, right? If L is the first letter of someone's name, the value hopefully is the salad. And so what you kind of have here is a dictionary, key value pairs, where it's not words and definitions, it's names and salads. And you can think of this, too, as kind of a hash table. Why? Even though it actually doesn't fit on one long shelf, because the store is only so big, this is really an array. And apparently, A is missing, or maybe it's around the corner. But this array just happens to wrap onto multiple lines. But it's still conceptually a single dimension. But suppose two people have the name L. What do they do typically? Yeah, so maybe well, if they put that much effort into it, they might look at the second letter and then the third letter. Odds are this is not that interesting a problem to solve optimally in that way. But they probably do start stacking the salads on top of each other, or maybe scooching it over just a little bit. And so what do you have there? Well, now if you start to view the lens through like CS50 glasses, like, OK, you have an array, and then you have like these linked lists that are sort of growing here. But even then you run into a problem. Why? Because it's not really a linked list, because at some point you're going to hit the boundary here. So it's kind of like an array of arrays, because you can only fit, what, like 3 or 4 salads here. And so long story short, we started today deliberately talking about real world things like stacks and queues. And even though it did escalate quickly into binary search trees and hash tables and tries, even those things are everywhere, even though they don't call them as such. These are just solutions to problems. And now, with this final week of C under your belt, you have all the more of a technical toolkit via which to implement these things in code. Next week, we'll be able to trust that someone else solved all these problems. We'll introduce Python, and lines of code like this will finally become lines of code like that. So that's the promise ahead, and we'll see you next time.